popularity of the Python programming language has been increased significantly during the past 10 years. Python appears to be a new language that caught the attention of its target audience and received a boost as a result. Here's an interesting side note. Python is older programming language than Java. Java was first introduced in the year 1995, whereas Python was introduced in 1991. Thus, Python has been around for almost 32 years and is still going strong. Hello everyone and welcome to SimpliCode's YouTube channel. I hope you guys are doing well. Today, we'll be taking you through the Python Advanced full course. This Python full course will cover all the advanced level topics of Python. In this video, you will see how and why Python is used today. By the end of this tutorial, you guys will be able to understand and deploy certain projects using Python, and you guys can also prepare for interviews. But before we begin, let me tell you guys that we have regular updates on multiple programming videos. So if you are a programmer and want to learn something new, then consider getting subscribed to our YouTube channel and press that bell icon to never miss an update from SimpliCode. Let's go through the agenda of this full course tutorial. We'll start this video with an introduction to generators in Python, followed by list comprehension and regular expressions in Python. We'll then move on and cover topics like serialization, partial functions, closures, and decorators in Python. Maps, filters, and reduce functions are some of the most important topics we'll cover in this tutorial. Moving on, we'll cover Python Lambda functions, NumPy, Matplotlib, and scikit-learn in Python. We'll also see scripting and web scraping using Python. Towards the end of this tutorial, we'll go through data analysis using Python, where we'll understand the detailed concept of analyzing data with multiple examples. Before we start with the first topic for today, if you haven't watched the previous videos on Python basics and intermediate courses, we'll suggest you guys to go through them in order to have a good understanding of the topics we are going to cover in this tutorial. The link is mentioned in the description box below. Now, we'll start with our first topic. Over to a training expert.
So Python provides a generator, which is like a function where we can create our own iterator. In a generator function, we use the yield statement instead of the return statement that we use for standard functions. So let's look at a simple generator first of all. So out here I have defined a generator called myGenerator, where I'm doing there are three functions or three tasks that I'm doing. First one is when I'm printing the first item and I'm yielding a value 10. Then I'm printing second item yielding 20. Then I'm printing last item yielding 30. So let's see how do we use this. Now, since we know myGenerator is the function, it uses the yield keyword. Every time we use the next keyword, we will keep getting what is next in this function. So let's store the generator in mygen. So now we have stored the iterator in this function variable called gen or gen. Now let's see when we do next and we use gen, what happens. So the first task is performed, or the first iteration is performed, where we get this, the first yield command is done. Alright, let's see what happens when we do next again. Next gen. Now, as you can see, we get second item and we get 20. Let's do it for the next. Let's do it once more, since there is one more task. There's one more iterable inside. You can see this. Now, a valid question is what will happen if we do next gen again, since there is nothing after this. Well, let's see what happens. We should get an error. As you can see, stop iteration error. This is another built-in exception that happens when we have reached the last object of an iterable. So we get a stop iteration error. So now a key difference between a generator and a function is that when we execute a function, the moment we hit the return statement in a function, or when we execute a function, like whatever variables that were stored inside are lost and they're destroyed unless they were defined as global. And the function is completely done executing and we leave the function completely. Whereas when it comes to a generator, when we hit the yield function, we don't actually completely leave this function. So the first time the yield is found, we get 10, but the generator remembers its position inside this function. So the next time we use the next, we actually move on to the next iterable, and then we move on to the next iterable. So you can think of a generator as it sort of has memory, if that makes sense. It's a way to like create iterables in Python or create iterators in Python. So to understand what the difference between the yield command and the return command does, let's take the same function. Alright. And let's put a return over here after this particular, the second yield. Okay. Let's do the same thing. We say gen is equal to my generator, and let's start doing next gen and seeing what's there. So the first yield will be standard, first item 10. The next one is going to say second item and then 20. But now if you notice, there was a return I put over here. So technically when I did the second next, it's not only yielded 20, but it's also executed this return function or this return statement. So let's see what happens if I do next again. As you see, I have gotten the stop iteration seemingly earlier than I did before. And that's because I have used the return function and return statement. And what that's done is that we've completely left this function, so as to speak, and there is nothing next, so as to speak. So we get the stop iteration, and that's the difference between yield and return. Now in the next example, I'm going to show you how we use a generator function in place of the for loop, or for a for loop. So let's take this, what I have over here, and I have defined a function called getSequence up to x, and what this will do is basically it will keep printing the printing numbers up until whatever we have entered in place of x over here. So if I said, say, sequence is equal to, let's copy this, all right, and say I want sequentially, I want every number up until 10. Well, not including 10, of course, because Python starts with 0, right? So let's do this, and now let's see. So the first number will yield 0, and now if I did this again, it should give me 1, 2, and I can keep going until I will stop at the value 9, as you can see here. So 8, 9. Now I should get the stop iteration error, because that we have reached the end of our iteration. So this is a way of using generator functions for loops. So another neat example where we're going to use a generator is in the case of Fibonacci numbers. So let's use it. Let's see how we can generate a Fibonacci series using generator. So I've defined a Fibonacci function called Fibonacci where I'm passing max. So max is basically the max value that I want, like up until where I want the sequence, right? So this is basically the code which will return me the subsequent values of my Fibonacci sequence. So let's pass this to fib and say I want all the Fibonacci numbers until 10. So I will pass 10 over here. Let's see what happens when we do next fib. Well, it should start with 0. Then when we do this again, we get 1. Then we do 0 plus 1. It should be 1. Next number should be 1 plus 1, which is 2. Then we should have 2 plus 1, 3. And then 3 plus 2, 5. Then 3 plus 5 should be 8. Now 8 plus 5 is 13. And since 13 is greater than what we passed for our max value here, now when we try this, we should get the stop iteration error, as you can see. So yeah, this was a brief video into generators in Python and how we can use generators to create our own iterator function. So of course, it's very important to note that generator functions use the yield statement instead of the return statement, and that's how we differentiate a standard function from a generator function. Now, list comprehension it's a neat way of creating a new list based on values that are already there in an existing list. So you can think of it like creating a new list using a much shorter and cleaner syntax compared to what you might traditionally be thinking. So let's go through some examples, and through those examples we will see how list comprehension makes creating these new lists much simpler and much easier for us. So in our first example, we will be creating a new list which will contain fruits that contain the letter A in their name. So we already have a list of fruits over here, as you can see. It has apple, it has banana, cherry, kiwi, and mango. Now we want to create a new list which has only the fruits that have the letter A inside them. So apple would be one of them, banana would be one of them, and mango would be one of them. So traditionally, if you look at this piece of code, this would do what we want to do, but this contains a few extra lines. But yeah, it does do what we want to do. Now what if there was a way of doing the same thing by just writing one simple line of code? And that exists, as you can see here. So I take the same list. Now this is where you need to follow. So now my new list is equal to, so I'm creating a list over here, as you can see. Now within this list you have this line. This is what we call a list comprehension. So as you can see, it says each fruit for each fruit in fruits if, now it's checking for the letter or the character A inside each fruit. And what this each fruit is, that we're checking each object in this list one by one. So first, in the first iteration, each fruit will contain the string apple. Then in the next iteration, it will contain banana. And in each iteration, we're going to check if it contains the character A. And if it does, then we store that each fruit in the new list, as you can see here. So if I execute this line, you see my result is the same. I have my whatever I wanted. And this was a much cleaner way of writing or creating this new list. Let's look at some other examples now. So my next example, what I'm going to do is I am going to iterate through a string. So I have a string. It can be anything. In this case, I am using a string called human. Alright. So I have a string called human, right? Now I want to store each character of this string into a list that we call h_letters. So if I use the for loop, this is how we would do it. If I execute this, as you can see, the list contains h and then u, m, a, and then n. Now what if I wanted to do the same thing but by using list comprehension? So what I would do is, let's create a list over here, h_letters, and so as we know, list comprehension will you just basically need one line. In this case, it'll just be like this. Now this is my string. Now let's see, when I check what's in h letters, let's see what is the output. So as you can see, I have the output as what I needed. So this is a much cleaner way. Let's go through some more examples now. Now we can do more list comprehensions. We can even use, so we've already seen one case where we checked for the character A. We've seen a case where we went through, where we did a sort of a loop through a string. We can also use list comprehensions in conditionals. So let's look at an example where we use the list comprehension with an if statement. So what if I wanted to store, say, the first 10 even numbers? So this would this is an example that I'll be using. So in my list, I want to store the first 10 even numbers. So this would be a way to do it. So I have in range 20. So what this is going to do is x is going to take the value of 1, 2, 3, 4, and so on until 90. It'll actually take it from 0, 1, 2, 3, 4 until 19. So when we do range 20, we're creating an iterable where we're going to loop through or iterate through the values 0 to 19. So if I do this, and this what this statement does is basically it checks if it's divisible by 2. So if this is equal to 0, that means we have an even number. And if this condition is met, that means we store the x into our number list. So let's see what happens when we execute this. This should contain 0, 2, 4, 6 until 18. So this is the first 10 even numbers, as you can see. So this is a neat way of using if statement. We can also use an if else statement. So what if I'm checking each, okay, so I'm going to create another list And in this list, I'm going to basically see if each of my numbers are the even or odd. The first, let's say 10 natural numbers. So let's write this statement down. So I want it to be even in case the I that I'm checking, I being every number between, like say the first 10 natural numbers, as I said. Now let's check if it is divisible by 2. Well, if it is divisible by 2, of course, it's going to be even, right? Else, we say that it is odd. And then we check for I in, say, let's say the first 20. Okay. So now when we do this and we check what's in the list. So as you can see, the list contains like even, odd. It's basically saying the number 0 is even, then the number 1 is odd, then number 2 is even, and so on and so forth. So this is an example where we used the list comprehension with if-else statements. So another neat thing that we can do with list comprehensions is that we can use it along with functions. So let's look at this function. In this example, we have a function called double x, where we define this double function to take an input, to take an argument x, and what we return is the square of the argument. So let's use this in our list comprehension. So what we do over here is that we're checking. What we're doing is for every x bit in range 10. So we're taking the value 0, 1, 2, 3 until 9, and we're passing it to this function double x, and we're going to get the square of them, and we're going to store that in a list, as you can see here. Let's call this list x. Let's just call this list let's call it y. So now let's see what's in y when we check. It should be 0, 1, 4, 9, and so on. So wait, let's check again. Does this square? No, this is actually 2 times. So let's make it square, as you can see. So you can see 0, 1, 4, 9 for the first 10 natural numbers. Now what I've shown you is obviously list comprehension, but we can also do set and dictionary comprehensions. In fact, set comprehensions work exactly the same way as list comprehensions. The only difference is the set comprehensions will make sure that there are no duplicates inside the set. So you can't have like duplicate items, which you can in the case of list comprehensions. So let's just take a look at an example. So here in this example, what we're doing is we're going to check. So we have this string that we're storing in the variable text, and the string is something like life finds a way. So whatever this is. Now what we're going to do is we're going to iterate through this string character by character, and we're going to check if we're going to check for vowels essentially. So we're going to see if the character A, E, I, O, or U is present in the string, and if it is, we will pass it into our set. Now if you look, you will find there are multiple I's, right? And there are multiple A's as well. So if we did this through a list comprehension, each time that we find a vowel, it would be added to our list. But since this is a set, and sets do not allow duplicates, so you will only have one copy or one particular object for each of the vowels. So of course, now set comprehension is defined using curly braces, so let's keep that in mind. So now if I check what's in this, I will see A, E, I, and U. Even though there are multiple A's or multiple E's or I's and U's, since this is a set, we don't have duplicate copies of any of these. So this was just a small example for showing you set comprehensions. Similarly, we can do the same thing, this comprehension for dictionaries, and we call it dictionary comprehensions. The only thing that we have to worry about when it comes to dictionary comprehensions is that we have to define a key when it comes to this. So let's look at an example. In this, what we're doing is, again, dictionary comprehensions are also defined using curly braces, just like sets, except in this case, we will define a key, and that separates it from a set comprehension. So in this case, what we're doing is that I'm checking, I'm going through a list of numbers from 0 to 9, right? This is what the range 10 function does. And what I'm going to do is, I'm going to create a key, which is going to be like 0, 1, 2, 3. And the value of each key would be its square, as you can see here. I'm doing I times I, or just to make it a little more clearer, as you can see, I'm doing I square over here for every value from 0 to 9. So what I should get is like a dictionary where the first key is 0 and the value of that key should be 0 as well, because 0 square is 0. Then for 1 it will be 1, and then for 2, 4, and then 3, 9, 4, 16. So let's see what happens. As you can see here, this is the result that I wanted. So just to summarize, let's go through some key points to remember when it comes to list comprehensions. So it's obviously an elegant way to define and create lists based on existing lists. It's more compact and faster than normal functions and loops. But we should also keep in mind that we shouldn't write like very complicated list comprehensions, because the idea of a list comprehension is to be user-friendly. And also it's important to note that every list comprehension can be written in the form of a loop, but every loop cannot be written in the form of a list comprehension. And that is probably a very key point to remember. Now, a regular expression is simply a sequence of characters that defines a search pattern. For example, if you see this example here, you can see a symbol called the caret followed by P and then 5 periods, then an N and a $sign. And what this regex pattern does is it's searching for a 7-letter string that starts with P, ends with N, and has 5 characters in between. Let's look at this example now. This is a regex pattern that is looking for a 5-character string that starts with A, ends with S, and has 3 characters in between. Now, if we had to match this with this string, with these strings as our test strings, the first one would not match because it's a 3-letter string and we're looking for a 5-character string. The second one would match because it's a 5-character string that ends with an S, starts with an A, and has 3 characters in between. This will not match because what our pattern would do is it would find the first S and it would find that the string itself starts with an A, and it would say, okay, there are only 2 characters between this first S and this A, and it would assume that this is actually just a 4-character string. To actually identify 2 consecutive S's, we would have to do something special, and what we would have to do is what we will see later on. So again, this is the same example. Since this is case insensitive, capital A is perfectly fine when we're searching for this, and it will also match. This is obviously 2 words, and it's not a 5-character string, so this will not be a match. Now, the regex pattern or the regular expression module in Python can be imported using this statement, import re. Now, once we've done this, we can actually use our regular expression tools and methods to do pattern recognition, character recognitions, and to identify different sequence of characters in our strings. Let's try to understand a bit more in depth about regular expressions now. So what you're seeing here is one variable called pattern, which stores something that looks like a regex, and another variable that stores our test string called abis. Now what we're going to do is we're going to use the match method of this module re, and we're going to check whether this pattern or whatever we are trying to search using this regex is in fact, does it match with our test string. And what we're trying to look for is, if you see here, very similar to what I just showed you, a 5-character string that starts with A and ends with S. So if you see our test string, it indeed is a match, and when we use this this command, we should get a perfect match. So we should basically it should say that search is successful if I execute this, and this is what it does. Now if I change the test string to this now, you will see that now this is no longer what we are looking for, a 5-character string with A and starting with A and ending with S, and you will see that the search will be unsuccessful, as you can see here. Now let's try to understand what exactly do we mean by when we use these special symbols, like for example this caret or this dollar symbol. These are, by the way, known as meta characters, and now we're going to look into all the or most of the different meta characters that are used in regex. So to put it simply, meta characters are simply characters that are interpreted in a special way by the regex search engine. Now here's a list of meta characters. Let's go through them one by one. Now the square brackets. Square brackets simply specifies the set of characters that we wish to match. So we want to match some combination of A, B, and C. It can be 1 A, 2 A's, 3 B's, 4 C's. We are not looking at a specific pattern. We just want to know if A, B, and C exists in any form in our string. So if we used it on A, the string A simply, we would find one match because the letter A is found here. AC would match twice because we have A and C present here. In this string, Hey Jude, we will have no matches because A, B, and C, none of them are found here. And in this weird string, we will have actually 1, 2, 3, 4, and 5 matches. So we would have 5 matches for this this bigger string because we have 5 instances of A, B, or C. Now let's use re.match to actually search for this and to see if we have our particular whatever patterns that we're looking for. Now in this input string, this is just some example string. I'm going to test this. I'm going to match whether my pattern that any of A, B, and C, is it actually found in this. So let's see what happens when I use re.match for this. So the format, the syntax is simply the regex pattern and then comma, whatever test string that we have. So let's see what object gets created when we try to do this. As you can see, it's none. Even though you might be wondering, like I can see an A over here, I can see a C over here. re.match actually gives us the result none. Now, if I try to do it on this test string, which is slightly different, instead of the film Titanic was released in 1998, what I'm saying here is all film Titanic was released in 1998. Now let's see if the rmatch works or not. As you can see, it actually does return. When I execute this, it returns us an object called re.match object with a span 01. The span 01 is basically telling us that we have found a match between the 0th and the first character, which is basically this character A, which is what it has found. And it's saying that the match is indeed the character A from amongst these options. So what this is basically telling us, and what this means actually, is that the re.match method will only find matches if they occur at the start of the string being searched. Once there is a space in our bigger string, it will not search for whatever comes after it. So what happened in the first instance was, it was actually only searching for matches in this particular word in my larger string. And since it found no match, it basically gave us the result none, which was not the case in the second example because it found a match immediately in the first letter A. Now, if we want to actually check the whole thing, what we would be using is the re.search. As you can see here, the re.search method will actually check the whole string and it will return us the first instance where it finds a match. Now let's see, this is the test string now, and we're searching again for we're searching for A, B, and C, any of these in our test string, but we're going to use re.search and not match. So now if you see, it returns us, when I execute this, it returns us a match object again, but this time it's saying the span of 9 and 10. Now the span of 9 and 10 actually exists over here. This is the 9th character and A itself is the 10th character over here. So what this basically is telling us, that the 10th character is where we found a match, which was the letter A, which was the first instance of either A or B or C in this whole string. And this is basically how re.search works. It will not only search the beginning of the string, but it will search the whole string and return us the first instance of wherever we find. Now what if we wanted to find out all the instances wherever A, B, and C were found and not just the first instance? Well, in that case, we would be using the method findAll over here. So when we use findAll, it will actually return us each and every case where it found A, B, or C. And you might not, it won't tell you the exact position, but it will tell you like, so if I execute this, you can see it gives us a list with A, C, A, and A. And what this basically means is it was looking for the characters A or B or C, and it found A first, and hence this for the first item in the list. And then it found a C, and then it found 2 A's successively. So this is actually how findAll works, where it will actually find all of the instances of our regex pattern. Now that you've seen how the square brackets work and how the re.search and re.match and re.findAll methods work, now we're going to go through all the other meta characters that we saw above. So the period. Now period matches any single character except the new line. New line is basically /n or a break. Now if you look at this picture, what it's going to do is this expression basically saying that do we have 2 characters, like sets of 2 characters in our string. So this is a single character string, and obviously a single character string is not a double character string. And this expression, this double dot, is basically asking us, do we have two characters present in our string? So if I had to match it with this A, it will obviously be a no match because A is one character. If we checked it with AC, it is a match because A and C are two characters. AC and D will also give us only one match because it will find AC and then it will leave D as a single character. But when we check A, C, D and E, or this string in particular, it will find two matches because it will consider A and C as one of the matches and D and E as one of the matches. So below is basically what we're doing. Basically the same thing, we're just using rd.search for each of these different examples. So if you see when I use find all on ACDE and when I'm searching for a two character match, you will see that it will return me AC and DE as you can see here. And similarly for something like this, it will return me again whatever like two character patterns it finds successively. So the next symbol, the next meta character is the caret symbol that you've seen earlier. And the caret symbol is basically used to check if a string starts with a certain character. So if you look at this picture, we have two expressions that we're going to check over here. One is one is checking if A is the beginning of a string, and the other one will check if A is the beginning of the string, but is it followed by B or not. So when we check this, what you can see is the first string will be a match because it's only the character A, and it will match here as well because this string starts with A, but it will not match here because this string starts with B. Now if I look at this particular expression, you can see that this is going to search for if the string starts with A and is followed by a B. So it will match in this case because it does start with A and is followed by a B, but it will not match in this case even though it starts with an A because it's not followed by a B. So out here is basically us using the re.search to basically find these patterns. The next symbol that we will come across is the dollar symbol. So the dollar symbol that you can see here is used to check if a string ends with a certain character, and we have already seen how this is used in one of the earlier examples. So this is going to check basically this expression will check if the string ends with A. So this string is basically the character A, so it will match. This also ends with A, so it will match. And this particular string does not end with A, so it will not match. And we are going to do that using the re.search over here. So as you can see, it finds a match in the first character itself here. In this case, it finds a match in the last character, but in CAB, there is no match, so it returns us a none. Another example is of the meta characters is star. So this is the symbol for star, and what the star basically is used is for checking if there are 0 or more occurrences of the pattern to the left of it. So now if you see here, what this will check for is there any form of M and A that occurs before N? And it's very important to note that the N has to follow the A in this case. So let's look at these examples and what will happen. So if I checked it with M and N, this is actually a match because N is followed by 0 occurrences of M and A, which is, it might seem a little weird, but it is technically the truth, because the star symbol doesn't check for the existence, it just checks for if N occurs, it must occur after an A, or the A should not be there itself in this particular string. So as you can see here, the N occurs after an M, and it's fine because there is no A. Now you will see when it will not work. So M, A and N is obviously fine. M triple A N is also fine because N follows an A and there's an M here. This, however, main will not match. Now why? Even though we have M and A and we have an N, you see the N is immediately followed by an I. N follows an I immediately, or the N is preceded by an I immediately. And this is a no match because the strict condition in the search is that N must precede an A if the A exists. Again, in woman it will match because N follows an A over here. So we're just going to use the re.search for these examples that we saw over here in terms of code using the re.search, as you can see here. Finally, we have the next meta character, which is the plus symbol. Yes. So the plus symbol matches one or more occurrences of the pattern left to it. Now this is very similar to what we saw earlier in terms of the star, except now in the plus, the key difference is we're looking for one or more occurrences instead of 0 or more occurrences that we were looking for in the case of star. So when we say one or more occurrences, now we need what is there to the left of the plus sign. A 0, no occurrence of it will not be allowed or will not cause a match. So let's see now what we're going to do here. We're going to use the same expression, except we're going to replace the star with a plus sign. So now what we're going to say is, okay, we need M and A, at least one occurrence followed by an N. All of these conditions have to be met. So again, if we took the first example, M and N, this time it will be a no match because there is no occurrence of an A over here for preceding the N. So it's a no match. M, A and N is a match because, well, this is perfectly fine. M, triple A and N is also perfectly fine. But if you look at M, A, I and N, much like earlier, the N is preceded by an I and not an A, so there is no match. And again, woman is perfectly fine. And we basically execute the same thing through the search function in this piece of code. The next meta character is the question mark. The question mark symbol matches 0 or 1 occurrences of the pattern to the left of it. So let's see what this does. So now we saw the star which was 0 or more occurrences of the pattern to the left of it. We saw the plus, which is 1 or more occurrences of the pattern to the left of it. Now we will see the question mark, which is 0 or 1. Only 0 or only 1, and not 0 or more or 1 or more, which was the previous cases. Only 0 and 1 or 1 occurrences of the pattern to the left of it. Again, we're going to see the same expression, except we're going to replace the meta character with the question mark. So now let's see what happens when we match. So if you see here, M and N is a match because there is 0 occurrence of A and 1 occurrence of M preceding N. So this is fine. This is also fine because there is 1 occurrence of A and M and then it's followed by an N. This will not be fine because now we have 3 occurrences of A which is followed by an N. We're only looking for 0 or 1. This again, main will be a no match for the same reasons that we have already gone through, and woman will be a match again for the same reasons. And we do the same thing using the search function in this piece of code. The next meta character is the braces character. Now the braces character is interesting because what we're going to do is we're going to see if there are, the typical syntax for a braces is n brace followed by some integer n, comma, integer m, and then close braces. So what this means is we're looking for at least n and at most m repetitions of the pattern left of the braces. Let's see through an example. If you see this expression, we're looking for at least 2 and at most 3 occurrences of the character A in our test strings. So let's see what happens in the first case. We have no matches in this case because this part of the string contains only one A, and even this part of the string only contains one A. We're looking for at least 2 and at most 3. This part will contain one match, the second example, because the second part of the string actually contains 2 A's. For two repetitions of A's consecutively. But this in the third example, you can see both the strings actually contain matches. So we get 2 matches because, as you can see here, there's 2 A's here followed by 3 A's here. Now when we look at this particular string, let's look at what happens now. So what we're going to find is that this thing is perfectly fine. So we have 2 occurrences of A. But now we have 4 occurrences of A, but what the search engine is going to recognize is these first 3 A's, and it's going to see, okay, so there are 3 occurrences of A and I already have a match. It's not going to consider this 4th A in the search. It will just look at the first 3 and it say, okay, there are 3 A's and my match is fine. So again, there are 2 matches in this case. Again, we're going to use the search function initially, and you can see in each of the cases there is a match except for the first case, which is this case. Now let's see the find all option and see what happens when we do the same thing using find all. So when we use find all, it basically gives us each of the instances where the match has occurred in each of these lists. Now let's try to use a slightly more complicated example where we combine different meta characters and we create a more sophisticated expression that we want to search in our test strings. So if you look at this expression, what we're looking for is 0-9. Now a dash symbol is valid in Python using regex because what this basically tells it is that it's looking for either 0, 1, 2, 3, 4, so on until 9. Basically any of the digits. We're looking for any of the digits from 0 to 9, and we're going to check if at least 2 and at most 4 occurrences of digits, if they are there or not in our particular code. So let's see what are the matches that happens when we use it on test strings. So if you use it on this string, you can see it'll find one match. This particular part of the string where it says 1, 2, 3. So this is 3 occurrences of digits, so it's fine. Now when we look at this whole string, 12 and whatever this is, you will see this will not find a match here. This obviously will not because these are characters. But if you look at this part, it will find matches in terms of the first 4 and then 7 and 3, the next 2. 1 and 2, again, there are no matches because there's only single occurrences of digits. We're looking for at least 2 and at most 4. So if I use a find all, you will see like what all it will return. So for the first test string, what it's going to return me is, it's going to return me 1, 2 and 3, as you can see here. But now if you look at this test string, it's going to return me 12, it's going to return me 3, 4, 5 and 6, it's going to return me 3, 4, 1 and 2, but not 7 because we're looking for at least 2. And then it's going to return me 4, 5, 6 and 7, followed by 8 and 8, as you can see in this list over here. Now if we use curly braces with only one digit, it's basically telling the search engine that we want exactly so many repetitions of the preceding whatever expression that we have. So when we do this example, for example, we are basically saying that we want x followed by a dash, and the dash has to occur at least 3 times in our particular expression, and then it should be followed by an x again, which will not match in this case because there are only 2 dashes, and it will match in this case because there are exactly 3 dashes, and it will again not match in this case because there are 4 dashes. As you can see here, none followed by an object match followed by none. Next we move on to the alternation meta character. And as the word suggests, alternation is basically looking for some alternate form of A and B. So A should be followed by B, and basically this pattern has to keep going on. So in the first string over here, this pattern will not match. In the second string over here, we will have a match because we at least find an A, even though there is no B. But this is still considered a match because we did find an A at least. Over here we'll have 3 matches because we have A followed by a B followed by an A again. So if we did a regex expression for this, we would basically find these many matches for each of these examples. The next meta character is the group. Now a parenthesis is basically used to group subpatterns. So let's look at an example to understand what we mean. Now if you look at this complicated expression, what this means is that I want some form of x and z. The x and z have to occur together. But before that, what I want is some form of A following B following C. Some sort of alternation between A, B and C. So this part, as you can see here, is kept in a parenthesis because I want this whole condition to basically occur before I find an x and z. So let's look at what happens here. In the first case, we don't have a match because this parenthesis condition is not being met. X and z is preceded by a space, or basically the A and B is followed by a space. So if the space didn't occur, we would actually find a match, as you can see in the next example. Here you can see A and B occur. Basically this initial condition is met, followed by x and z. So there is one match. So it's fine for us. Now if you look at this slightly more trickier one, what you can see is we have 2 matches in this case. First an A followed by x and z, and then we have C, A and B. Now this is perfectly fine because we are looking for a B followed by an x and z. We're looking for either of these things. We're looking for some form of alternation of these things followed by an x and z. And we can get that over here. We get B followed by an x and z. So you'll get 2 matches in this case. Now let's go through the concept of grouping constructs. Now that you've seen many meta characters, you've seen how parenthesis works. Let's look at grouping constructs. So grouping constructs break up a regex in Python into sub-expressions or groups. And this serves 2 purposes. One is the grouping part, which basically says that a group represents a single syntactic entity. And any additional meta characters apply to the entire group as a unit. And then there's the capturing part, which basically tells us that some grouping constructs also capture the portion of the search string that matches the sub-expression in the group. And you can retrieve captured matches later through several different mechanisms. So let's look at basically what we mean by this example over here. So if you see this expression has a plus sign. So we're looking for, as you know, a plus looks for 1 or more occurrence. So this will basically check for 1 or more occurrence of the character R only, because there's no parenthesis as in this example. So this plus is next to an R, and it's going to check for basically whether 1 or more occurrence of R happens preceding B and A. But if we actually put B, A and R in a parenthesis followed by plus, it will actually check for the entire string BAR, and it will check 1 or more occurrences of BAR together. So if you look at these 2 examples, when we use this on these examples, you can see that these are fine, like these matches are fine. But if I used this parenthesis, then these would be the acceptable matches. And like BA triple R would not be a match if I use parenthesis. as you can see here. So this is how grouping constructs work and how parentheses work. So look at some other examples. So what this will do is FOO has to be optionally followed by BAR, and BAR must exist together. And this is because we have a question mark here. This question mark symbol tells us that there should be 0 or 1 occurrences. Similarly, this particular complicated expression is checking for 1 or more occurrences of whatever we saw earlier. Basically, this whole thing is followed by a plus. So we're looking for this whole sequence for 1 or more occurrences of it. COW is simply just COW. We're looking for this pattern. And this is going to check for 0 or 1 occurrence of COW because of the existence of the question mark preceded by the parenthesis. So this was just the part 1 of regular expressions. In the following video, we will continue with regular expressions and the backslash characters and special sequences. Now that you know the basics of regular expressions, let's continue our discussion with special sequences. Now in an earlier video on strings, you might have encountered what is an escape sequence and how we use the backslash character to generate these escape sequences. And an escape sequence is basically, if you remember, something that we use to either give a certain special meaning to characters that are otherwise ordinary, or it is used to remove the special meaning that are inherently present in certain characters that we call meta characters. So let's look at what special sequences are in relation to regular expressions. So the first one we're going to look at is the backslash capital A, which is used to match if specified characters are present at the start of a string. So out here, if you can see, we are checking if the word D is present in these two strings. So we would get a match in the first case over here because this starts with the word D, but in the second case we won't get a match. And this is how we're going to check it for the same thing using the findAll function. So if you see in the first case, it returns us an object because we do find D in the beginning of the string. In the second case, we get us empty list because this string does not start with the word D. Now the next one that we'll look at is backslash B, small b. Now this is used to match if specified characters are at the beginning or at the end of a word. So when you use backslash small b and then you follow it up with whatever you're looking for, it will look for those particular characters or that pattern if it exists in the beginning of a word in a string. So if you look at the first example, it starts with FOO. And in the second example, you see this portion of the string or this word is actually also starting with FOO, so it will also match. However, in this string, which is very similar to the second one, we don't have a space between A and F, and it's basically one word. So this does not start with FOO, but it actually starts with AFO, and it won't match, as you can see here. Now similarly, if we wanted to check if something exists in the back of a string, at the end of a string, we type what we want to search for first, and then we follow it with a backslash small b. And then if you see here, it will match in this first case, it will match in the second case because this part of the string ends with FOO, but it will not match in this case because, well, we removed the space, so now this whole thing becomes the string that we're looking for, and it does not end with FOO anymore. And this is basically us just checking it through the findAll function. Now the next special sequence that we will be looking at is the slash capital B, which is basically the opposite of what we just saw. This matches only if the specified characters are not at the beginning or the end of a word. So if you see here, this is checking if FOO is not at the beginning of these strings. So in this case, there will be a no match. In this case also, there will be a no match. And in this third case, there will be a match. Similarly, if we wanted to see if something does not end with a particular string, we would type that whatever pattern we're looking for, followed by a backslash capital B. And then we can use the findAll function to generate us lists wherever we find such objects, find such matches in our particular test strings, like we have done over here. So the next one that we're going to look at is the backslash small d. And this matches any decimal digit, which is equivalent to doing a square brackets 0-9. As you must have seen earlier. So if we did a square bracket 0-9 and if we did a search or a findAll or a match, it would look for any of the digits between 0 and 9. So a similar thing can be done using a special sequence backslash small d. So as you can see, there will be 3 matches in this case because 1, 2 and 3 digits exist. Whereas in this case, for the word Python, there will be no matches. So these are certain examples where we are doing the same thing using the backslash d. Now we have another one, which is the backslash capital D, and this is just basically the opposite. It matches for any non-decimal digits. It's also equivalent to typing a caret inside square brackets with 0-9, which, if you remember from the previous video, is basically asking us to check for anything that is not the digits 0 to 9. So this is basically, we're going to check in these two strings if there is no digits and no non-decimal digits. So if you see here, we will find three matches, A, B, and the double inverted commas. And in the second string, we will find no matches because this is fully just digits. Next, we have backslash small s. Now this matches where a string contains any white space character. So this is equivalent to doing a check for all of these. So this is like backslash small t is a check for tab space, backslash small n is a check for break line, and then backslash r, backslash f, backslash v are their own checks for different sorts of white space characters that you can see by just looking it up, honestly. But yeah, so if you simply do a backslash s, it would actually be the equivalent of searching for any of these white space characters that we generate. So if you see here, when we do a backslash s on this string, you can see that there is one space over here. So it will match, it will give us one match because there is one white space, which is just the normal space here. And in the second example, there is no match because there is no white space here. Similarly, slash capital S now, as you might have noticed, is basically checking for a string which does not matches in a string wherever there is no white space characters. So it's basically the same as doing caret slash t slash n slash r slash f slash v in a square brackets. So this is basically a simpler way of doing the same thing using square brackets and a caret symbol. So if you see this expression, backslash capital S, now we're looking at A space B. So over here, if you see, it will match for all the non-spaces. So it's going to match for A and B. So we're going to get two matches here. Whereas an empty string does not contain, well, it does not contain any non-white space character, since an empty string is basically a white space character on its own. So this will give us a no match. So the next special sequence that we're going to look at is the backslash small w. This matches any alphanumeric character, which is the equivalent of doing A to Z in small and then capital A to Z, and 0 to 9 and also an underscore check in square brackets. It's important to note that the underscore is considered an alphanumeric character, hence why we include it over here. But yeah, this is this backslash w, small w, which basically checks for any alphanumeric character and matches it in a string. So if you see in this first case, it will find three matches at 1, 2, and also at the letter C. These others are not alphanumeric characters. Whereas in this string, none of these are alphanumeric characters, so we will get no match. Again, much like the other examples, there's a backslash capital W, which will check for any non-alphanumeric character, and it's the equivalent of doing whatever we did before in the square brackets, just with preceded by a caret sign. So if you see here, we have this string where we have a bunch of characters. Well, yeah, only one of them, this percentage symbol, is a non-alphanumeric character. So we will get one match over here. But in this case, in this string Python, we will get no matches because they are all alphanumeric characters. We're just doing the same thing here with a bunch of different examples using the findAll function. Now the backslash capital Z matches if the specified characters are at the end of a string. Now don't confuse this with backslash small b, because the backslash small b checks for a string and it checks each and every word in the string individually and checks if any of the words ends with a particular thing or starts with a particular thing, but it checks each word individually. But in this case, the backslash capital Z will check the string only and not each word. So if you see the difference here, when you use backslash capital Z, it will match in this first example, but it won't match for the next two. But if you used backslash small b over here, it would actually match not only in the first example here, but it will also match in the second example, because it would check this word individually and it will find out that, yeah, there is a match here as well. So it would actually match in the second example as well. So yeah, this was it on this was the second part of our regular expressions, and with this we will conclude our discussion. Now, object serialization is very simply put, when we want to convert a data structure or an object type, and we want to translate this into a form that is that can be stored in a memory, such as a file or a memory buffer. Later we could deserialize this particular file and reconstruct the original object out of it. Now in Python, This is done, object serialization is done by converting the state of any object into a byte stream. This byte stream can be further stored in any file-like object such as a disk file or memory stream. It can also be transmitted via sockets. Deserialization, as I mentioned earlier, is the process of reconstructing the object from the byte stream. Now in Python, we refer to the serialization and deserialization by the terms pickling and unpickling. So the pickle module, which is a module that is a part of the standard library of Python, it provides functions for serialization, such as the dump and the dumps function, and also for deserialization with load and loads. The data format of pickle module is it's very Python specific, and so programs that are not written in Python may not be able to deserialize the pickle data properly. And it's also considered unsecure to unpickle data from unauthenticated sources. So in this example here, what I'm going to do is I'm going to take the dictionary object, which is represented by DCT, and its byte representation will be stored in a file called pickled.txt, and we will also gonna enable the write and binary mode preemptively. So if you can see here, first I'm importing the pickle package, and then I'm opening a file pickled.txt and write in binary mode. Then I create this dictionary, and I'm going to dump this dictionary into that particular file, and then I'm going to basically close the file. So this executing this would do this. Now it's important to note a pickled file is not a human readable file. A computer can understand this, but it's so the byte representation of any object or data type cannot be read by a human in plain sight. So this next part is where I'm going to deserialize, or I'm going to unpickle the file pickle.txt. So again, I'm importing pickle. I'm opening this file in read and binary mode, and what I'm going to do is I'm going to load this into D. This will basically in a way deserialize whatever was there in pickle.txt, and once I have unloaded it in D, I'm going to print what's the content of D, which should be my original dictionary itself. So when I execute this, you can see that printing D prints my original dictionary that we had before. And it's important to note, since dictionaries are unordered, so dictionary objects don't retain the order of insertion of keys. So the way we enter the keys inside the dictionary when we create it is not maybe the same way that we will see the order of the key value pairs when we actually unload it. Now there exists a dumps function inside the pickle module that pickles Python data to a string representation. So we're going to do that in this next piece of code. So I'm importing the dumps function from the pickle module, and I have my same dictionary. What I'm going to do is I'm going to dump this dictionary into DCT string, and I'm going to print DCT string to show you like what exactly a string representation of this dictionary would typically look like. So when you execute this, you see this something very cryptic. So this is basically what we mean by the string representation. Of course, we can use the loads function again to unpickle whatever we just did and get the original dictionary representation of this particular string. So that's what we're doing in this piece of code. And as you can see, we get back our dictionary over here. So now in our second example, what we're going to do is we're going to create slightly more complex data structures, and we're going to do some serialization, deserialization on them. So we have this function called store data, where we initialize two dictionaries called Omkar and Jagdish with some certain key value pairs. Now we create another dictionary, empty dictionary called DB, which will be like a database. And now this DB has two keys again called Omkar and Jagdish once again. And now if you notice, my new keys are Omkar and Jagdish, but their values are these new dictionaries again. So we're basically storing a dictionary within a dictionary, so as to speak. So once we have done that, what we're going to do is we're going to create another file called example pickle, and we're going to create it in binary mode. Now once we've done that, we're going to dump this dictionary DB into this file called DB file, where we have opened basically where we're going to store the serialized representation of this dictionary called DB, and then we're going to close. So this is what store data will do when we call this function. And in load data, what we're going to do is we're going to print out what each key and what it represents. So we're going to basically deserialize in the load data function we're going to deserialize whatever we just serialized in the previous function. So when we execute this, we should basically get something like omkar followed by this sort of an arrow sign and whatever the dictionary that we have assigned to omkar is. Similarly for Jagdish as well. So when we do store data, it will basically do the serialization process. And when we do load data, it should do the deserialization and print out the original, the DB dictionary that we created in store data over here. So let's execute these two. Oops, I did not execute the load data. So now it should work. Yeah. So if you see now when I have executed load data, I get back. So basically from store data, I first serialized my whole file into a particular file called db file. And once I have done that, I have deserialized it using the load data function over here. Now partial functions allow us to fix a certain number of arguments for a function and generate a new function. The functools.partial module helps us achieve this. Now let's say we want to create a function that explicitly performs exponentiation. So we can get squares, cubes, and other power operations on any number. So let's look at an example. So we create this function called power where we have a base and an exponent. So what this does is it will basically print some number which is the base to the power of some exponent and the result which will be returned over here. So let's see now what if we want to create a dedicated square and cube functions that leverages this. So we can define a square function called with an argument called base where we return the power of the same base to the power of 2. So we're defining a square function with the help of this function that we defined already called power. For cube we will basically do the same power function but the exponent will be 3. So now when we do square 10, we're going to say, if we executed all of this, so now if we say square 10, what this will do is it will say 10 to the power of 2 is 100. And if you see the next one, cube 5 to the power 3 should be 125 as you can see here. Now this works, but what if we want to create, say 15 to 20 variations of our power functions? And what about, say 1000s of them? Defining a function for each case is obviously very repetitive, it's annoying, and this is where we will find partial coming into play. So as an example, let's do the same thing. Now what we're going to do is we're going to import partial from the module called functools. We have what we're going to define is this function called square, which is basically going to use the partial functions operation for the power function with the exponent of 2. So what we're doing is basically we're going to use the power. We're going to reference the power function that we defined earlier, but we're going to pass the argument for exponent as 2. And for cube, we're going to do the same thing, but exponent is 3. So once we've defined this, if we do square 2, you get the result as you can see. For cube 2, you get the result as you can see here. Let's look at another example. So we have this function where we define some function with 4 arguments. Now what we're going to do is argument a, b, c, and x, right? So we're going to return 1000 times a, 100 times plus 100 times b, plus 10 times c, plus x. Now we're going to create a partial function that calls this function, but it's going to use a as 3, b as 1, and c as 4 always, right? And so how we do that is basically g is equal to partial like this. So once we've executed these, now if we say g10, we basically get the value for 1000 times 3 since a is 3, plus 100 times b as 1, so 100 times 1, plus 10 times, well, c is 4, so 10 times 4, plus x. Now x we passed as 10, so the result of all this will be 3150 as you can see here. Now let's look at a final example where I've defined some function called add. I have 3 arguments, a, b, and c. What I return from this add function is 100 times a plus 10 times b plus c. So let's create a partial for using partial functions where b is 1 and c is 2. So we have this fixed. We can create a partial function called add part. So what this does is it takes the add function, it creates a partial function out of it using c is equal to 2 and b is equal to 1. So now when I print add part 3, what happens here is 3 gets passed in the form of a. So I get 3 times 100, and since b is fixed as 1 and c is 2, so I get 3 times 100 plus 1 times 10 plus 2. So it should give me 312. So when I execute this, you can see this here. So yeah, this brief video was on Python partial functions. Now before we understand what a closure is, we have to understand what is a nested function and non-local variables. Now a function which is inside another function is known as a nested function. Nested functions are able to access variables of the enclosing scope. So if I define this function called outer function, where I pass some argument called text and I store that in a variable called text again, and if I create a function within this called inner function, and I want to print whatever this variable is in text, when I execute this, it will be able to access this variable because it's within the enclosing scope. So if I said outer function hey, this gets stored in the variable text, and then the inner function will print that variable, which is basically the string hey, as you can see here. Now, inner function can easily be accessed inside the outer function body, but not outside of its body. So here, inner function is treated as a nested function, which uses text, this variable text, as the non-local variable. Now, a closure is a function object that remembers values in enclosing scopes, even if they are not present in memory. It is a record that stores a function together with an environment. It's a mapping, basically, that associates each free variable of the function, which are basically variables that are used locally, but are defined in an enclosing scope, with the value or reference to which the name was bound when the closure was created. A closure, which unlike a plain function, allows the function to access those captured variables through the closures, copies of their values or references, even when the function is invoked outside the scope. So let's look at an example to emphasize on what was just said. So again, I've defined this function outer function where I'm doing the same thing. Now I've defined the same inner function where I'm going to print the same thing. Now it's very important that when I return over here, what I'm going to return is inner function, but it's not going to be a function call. This is important to create our closure. So we return inner function, but without using the call as we do over here. And what this return will do is basically to create the closure, where the inner function will remember the values of the variables stored in the enclosing scope. So now I'm going to store this outer function in an object called in a variable called my function. Now when I call this my function, you can see there'll be two things that are happening here. So once I've defined this and I've executed this, what happens out here is this function has already executed, and then I'm storing it to this. But because I've done return inner function without parentheses, I've created a closure basically. And this closure allows the inner function to remember the values that were stored in text at any point, and at every point, even after the execution of this one time. So when I execute this again for the second time over here, it will remember the value that was stored in the variable text, which is hey, which was given over here. That's why you see when I execute it for the second time over here, the first time being in this line when I'm storing it in my function, when I execute it the second time, again it will give me the result of hey. As you can see, the closures have to invoke functions outside the scope. The inner function has a scope only inside the outer function, but with the use of closures, we can extend its scope to invoke a function outside the scope. So now let's look at this code. So this code, don't worry about what's going on here. Just know that what we are doing here is we have two functions which we defined called add x and y, which will return x plus y, and the subtract function, which will subtract x and y. So now we're going to execute these. Once we're going to execute the add over here and add logger, and we're going to execute the subtract function, and we're going to store it in sublogger. So technically we have already executed these two functions, but now since I've created an enclosure, basically if you see here, this is the enclosure that I've created. Now what happens is when I access this function from outside its initial scope, which is basically over here, this was the initial scope. When I access it outside, you will see that it still has access to these variables x and y. So if you see here, I first of all I've allowed the enclosing function to accept arguments of any numbers. So I can pass x, y, I can pass x, y, z also. But if you see here, I only have a thing for x and y. So when I want to access any value of x and y, even after the execution of this code initially, I have access to these variables x and y, and that is because I've created a closure out of that. So if you see, if I do add logger 3 and 3 over here, I'm able to get the result 6. If I do add logger 4 and 5, I'm able to get the result 9. Similarly, for subtraction logger 10 and 5, I will get 5 here, and 20 and 10, I'll get 10 here. And I can keep doing this. I can keep saying add logger, and if I say 4 and 7, so if I executed this, and now I'm going to say, let's say for example, add logger. If I set 4 and 7 here, so this still has access to my variables x and y because I've created the closure, and it should give me 11. Similarly, if I did sublogger, say 30 and 15, it should give me 15 because 30 minus 15. So let's say 30 minus 16, right? So it should give me 14 because again, I have created the closure and it has access to these variables already. So yeah, this was on closures in Python. So to start off with, let's first understand some basic concepts. Now in Python, we know that functions are first-class objects, and that means that functions are objects and they can be referenced to, and they can be passed to a variable, and they can be returned from other functions as well. Functions can also be defined in another function and can be passed as an argument to other functions. So decorators allow programmers to modify the behavior of a function or class. Decorators allow us to wrap another function in order to extend the behavior of the wrap function without permanently modifying it. Now, any generic functionality that you can tack on to an existing class or function's behavior makes a great use case for decoration. Some of these include rate limiting, caching, logging, enforcing access control and authentication, instrumentation, and timing functions. Now, you have to remember that function names are references to functions and that we can assign multiple names to the same function. So, for example, if you see here, I have defined a function called success, which does basically you pass an integer and it returns 1 plus that integer. So if I do success 10, it should give me 11, as you can see here. Now if I'm gonna say successor is equal to success, I've basically created another function called successor, which does the same job as the success function. So now if I pass 20 to successor, it should return 21, as you can see here. So as you can see that we have two names, success and successor, for the same function. An important fact is that we can delete either any of the functions, and you won't delete the other one. So if I said delete success, and if I tried to pass 10 to the other function called successor, it would still execute the whatever task the function is supposed to do. Now let's look at an example of a function inside a function. So I've defined a function called f, in which I have defined another function called g, which has two print statements that you can see here. The function f itself has two print statements, and at the end of the execution of function f, we call this function g. So let's see what happens when we actually execute f. So let's look at it on this side. So if you see here, this is where I've defined it. Now let's call my function f and let's see what happens. As you can see, first, when you execute function f, it will create this function, and then it will print these functions, and then it will do a call to this. And when we call this function g, it's going to do two of its own print statements, as you can see in this order over here. So this is an example of a function within another function. Let's look at another example of something similar. If you see here, I've defined a function called temperature, where I can pass some value for T, and I have defined another function within this called Celsius to Fahrenheit, and basically I'm doing the conversion. So when I execute this, what it should return me is I'll pass some temperature, and it will return me the temperature in degrees. So for example, in this case, I have passed temperature 20. So let's see what does it pass, what result does it give to me in degrees. As you can see, it says it's 68 degrees. Now let's look at another example of a function within a function, for a very common example for the factorial function. So if you see here, I've defined factorial n, and I'm saying if the value that is passed in n is equal to 0, return me 1. Otherwise, return me the product of that number times, and I'm going to do a recursive call back to the same function, except now I'm not going to pass n, but n minus 1. So what this should do is, if I pass 10, for example, it will basically check, okay, since 10 is not equal to 0, it will go here, and it will return me 10 times factorial of 9, and that will do 10 times 9 times 8, and then so on until we reach n is equal to 0, where it will just say, okay, return 1. So what you will effectively get is 10 times 9 times 8 times 7, so on until 1, which is basically factorial of whatever we have passed. So let's execute this. Let's see, I'm going to check what is the factorial of 5 here, and as you can see, it gives me 120. Now let's include a line, let's raise an exception by an else statement, which will basically raise a type error, and it will tell me that if I pass a number n which is not an int, and if it's not greater than or equal to 0, it should give me this error message. So I've included this extra statement in this just to check. So if I pass 9, as you can see, it should give me a valid result, which is 362880. Now what if I pass -5? So let's execute this. As you can see, I get the type error that I have raised over here in case I meet such a condition. And in this case, you cannot find the factorial of a negative integer. So that is why my type error gets raised over here. If you actually look closely at this program, you will notice that each time I call back my function factorial, so if I gave it 5 initially, it will check for the this condition, and since it will meet the condition, we can continue. But the next time when we call factorial for 4 and then for 3 and 2, each time is going to do this check. That's kind of redundant because we know that if we passed 5 in the beginning, until we decrement it to 0, we're going to only get the valid numbers 5, 4, 3, 2 and 1. So we don't need to do this check at every point. We just need to do one check. So a workaround for this would be in this code that I've written over here. And in this, I've basically defined a factorial function called n, where I'll pass my integer initially. And within that, I've defined the actual function where the actual results will be calculated, and that's called inner factorial. This is where this is basically the actual factorial calculating part. And if you see this if statement block, this is my check. So this will basically be the only check that will happen. So out here, it will check whether the n I have passed is a valid integer and equal to or greater than 0. And if it is, then we will perform this inner factorial function, where we won't be doing any more such checks. We will only calculate the factorial. And if it's not, then we will raise this exception just once, and we will exit the program in case we've given a wrong number. So let's look at an example for 3. So as you can see, at each step of my calculations, I'm going to return whatever value I have at that point. So basically, if I give 3, you will notice that you will get 0, 1, 2, and 6 if you multiply it in the right way. So let's do this. As you can see, factorial 3. One second. So I have to execute this. Now if I execute this, you can see I first get, because initially it will check, when I move into inner factorial, it will check if n is equal to 0. It will basically return whatever value I have at that point. So basically this is the order of calculations in a backward way. So you can see here it will first be 1, and then 1 times 2, and then 2 times 3, which is 6, which is what we get. So don't worry about the order in which we are returning these values. This is basically just a reverse way in which the program will fetch our values. So yeah, this was basically how we reduce the redundancy in the check part of our function. Now let's look at some examples where a function will be returning another function. So as we know, the output of a function is also a reference to an object, and therefore functions can return references to function objects. So out here, if you see, I've defined a function called f, which will take a parameter called x, and then within it I've defined a function called g, which will have a parameter called y. And this g will basically return y plus x plus 3, and the function f itself will return the function g. So if I pass 10 in function, so what this will do is it will create a function called g. I will create an instance of a function called g, and that object is going to be returned to us because we basically return g when we call function x, right? So if I execute this, you will see that when I say f10, it will give me some object location of a function called g. Now if I want to see the result of what I get for this function g, I have to pass something within g itself. So out here, what I'm going to do is I'm going to store this function object in a variable called nf1. Once I've done that, I can pass another parameter for this nf1 object. And since we know this nf1 is a variable name for the function g, so when I pass nf120, I'm basically passing this y parameter. So since now I have passed 10 for x and I have passed 20 for y, oops, one second, yeah. So what I will get returned is 20 plus 10 plus 3, which is 33. When I do nf1 and I pass 20 as the parameter here, as you can see, I get 33 over here. Now let's look at a function where we will implement polynomials of degree 2, and then we will actually extend that to polynomials of any degree. So I have created a function called Polynomial Creator. where I pass three arguments which will represent the coefficients. So A will represent the x square coefficient, B will represent the x coefficient, and C the constant. So I have defined, within this I've defined a polynomial function called x, where I will pass my value for the variable x, and I want to get returned the value for this polynomial. So as you can see here, initially the first function will return this object, and then for this object itself I will have to pass another argument where I'll pass the value of x. So I'm going to create two instances of this polynomial function. In the first instance, my coefficients are, as you can see, 2, 3, and -1. In the second case, it'll be -1, 2, and 1. So once I execute this, let me execute the function initially. Yeah, there you go. So if I execute p1, it will basically give me a object location of the polynomial function for p1, which is represented by this basically. So now what I'm going to do is I'm going to iterate through values between -2 and 2, not including 2, at steps of 1. So I'm going to iterate for -2, -1, 0, and 1. And I'm going to say, initially print me the values of x that I'm going to pass in this column, this first column. And then I'm going to say, okay, what are the results for the first polynomial object where the coefficients are 2, 3, and -1. And then in this column, give me the values of the polynomial with these coefficients, -1, 2, and 1. So when I execute this, as you can see, these are my results. Now, what if I wanted to do the same thing for arbitrary coefficients, as in a polynomial of nth degree? I'm not specifying the exact degree. So this I can do with this slightly more complicated program, which is actually very simple. So if you see this function, I've defined a polynomial creator function again, but in this case, I have passed variable number of arguments. So this asterisk basically means I can have any number of arguments here, and this will be an iterable with any n number of objects that can be iterated upon. So, and that will be called coefficients. So within that, again, I've defined polynomial x. Now what I've done is I've initialized some variable called res, which will basically be my result variable. And what I'm going to do is I'm going to for loop through this coefficients iterable. And what this basically does is, in a backward way, this is basically going to iterate through the array or the list or whatever we have of coefficients in a backward way. So if I pass 6, 7, 8, 9, it's going to give me 9, 8, 7, 6 in that order. And what this enumerate function will do is it will assign an index to each of the values and coefficients. So for example, I can just show you over here what this means. So if I created a array called say coefficients with some random values over here, right? Now if I'm going to perform this line, right? Now let's see what happens when we do a for loop. Let's see what values we get for index and when we do this, execute this line. So if you see here, once I execute this, as you can see, what I have done is coefficients. Oh, I made a spelling mistake. This is taking from a different variable. So let's fix this. So as you can see, I've entered 4 objects, 4 integers, 1, 23, 4, and 45. And when I do this for loop, I basically want to assign some index value 0, 1, 2, and 3 to each value in this list, but in a backwards manner. So this will be the 0th item, this will be the first, this will be the second, this will be the third. So that's what we are doing in this function as well out here. We are basically going to use this enumerate function to, now if you see this result is basically going to add each component of this polynomial. So if you see closely, what this is going to do is it's going to first, in the first step, is going to find out, well, what is the value of this, the constant term. And then in the next step, is going to find out what is the value of this. And it's going to keep summing it up. It's going to sum this part up until the end. And then we will get our final result in this variable res, and we're going to return that over here. So if you see here, I've done the same thing. I've created 4 function objects, and they're called p1, p2, p3, p4. And now I'm going to iterate through again -2, -1, 0, and 1 as my different x values, and I'm going to see what are the different values for each of these polynomials. So if you see here, my first polynomial is basically, it has only one coefficient, so it's a polynomial of the 0th degree. So basically whatever I pass for x, that itself should be my result. So actually this is a polynomial of 0th degree. So this is basically the only result we will get. So the constant is 4. We will get 4 in every result. So if you see here, what I'm printing is the x values first and what are their respective polynomial values for each of these objects that we've created. So this is a constant. So P1 will only have the result 4. This is P2. So this is a polynomial of degree 1. So it's like saying 2x plus 4, and where x takes values minus 2, minus 1, 0 and 1. And in this case, you can see this is a polynomial of 4th degree. So it's like saying x to the power 4 plus 8x cubed minus x squared plus 3x plus 2. So when we replace x with minus 2, minus 1, 0 and 1, we get the respective values in the P3 column over here. And for P4, it's basically a square polynomial. So yeah, this is an example of how we can create we can do a polynomial creator and get our results accordingly. Now, interestingly enough, what we've done here is basically like, for example, let's look at P3, right? P3 is basically this polynomial. Now, this polynomial function inside our decorator, polynomial creator. So all these examples that I've been showing you where functions are within functions. If you think of it, it's like I'm giving some basic function extra, like I'm doing something extra within them, right? So we can use decorators for this. And in our example over here, what I can do with this function is I can implement the same operation more efficiently by using a decorator within our main function. So we can factorize it in a way that it does not need any exponentiation. So we can, if you think of it, this polynomial can be represented like this, right? If you think of it, it's basically this times x plus some constant, and then that whole thing is again times x plus some constant. Since this is to the power 4, this is all we need. But if you think of it, if we keep going further, all you have to do is again enclose it in another bracket and then do times x. So we can basically use a decorator to do this function. So if you look at this function over here, what I've done is I've created the same polynomial creator with variable number of arguments. But inside this function, like what I've done in the form of a decorator is that I'm going to implement this polynomial by calculating the result in this manner, where it's going to be very much more efficient, and you don't have to keep exponentiating like how I did in this example. So that's what I'm doing over here. And if you see, that is basically implemented over here through this. So when I do the same, when I execute the same thing, and if I go through the for loop again, it should give me the same results, but it's much more efficient. Now let's look at another example of a simple decorator. So I've defined a function called our decorator func. Now this will basically be, this is a reference to another function itself, if you see within this. But inside my decorator, I have a function wrapper where I'm going to print this statement before actually like calling the function x, before calling the function. And I'm going to perform a print statement again after that. And I'm going to return the function wrapper at the end of like executing the decorator. So let's look at what happens when we define this function foo x. So this is basically a simple print statement where I'm saying hi, foo has been called with whatever this is argument. So now let's execute what happens when I say foo hi. So as you can see, let's execute the whole thing. So yeah, as you can see here, I have executed this. It says this is the print statement that I've basically written over here, and this is what gets printed when I call this function here. Now when I move on to the next statement, what I'm declaring is I'm going to now decorate foo with f. Now what this means is I've now created this this decorator object basically. So let's look at what happens when I execute this, and then I'll try to explain to you. So when I execute the whole thing, you can see something else is happening now. So we call foo after decoration. Then we have this before calling foo. And this is basically this print function. This is the print function that gets executed here. Now we have this. This is the function call. This is basically the function call, which is basically this foo function. And this line is being printed from this. So if you see here, I'm getting some results from this, like from this decorator itself, but I'm also calling upon the function that is being referred to by this decorator. So I'm doing two things. I'm doing the main thing, which is being executed here, which is the result is here, but I'm also decorating it with these two lines, which comes from this decorator called our decorator. So let's look at the explanation. So if you look at the output of this previous program, we can see what's going on, and that is that the decoration foo, this when we did this line, which was over here, it's a reference to the function wrapper, which is this. Now in this function wrapper, this function itself, right, like this function that we defined here, that will be called as well, but we will also have a bunch of extra like print statements in the form of these two lines, which you can see over here before calling and after calling, that we've also done along with this. So this is a simple example of how we've used a decorator to modify our basic function. Now this usual syntax for decorators in Python is with the at symbol. So we can write the same thing like what we did before through this. So we write at our decorator, and this will basically apply the decorator to this function foox. So when we do at our decorator and then we define this function and we call it, it will basically do the same thing as doing this, for example. So if I execute this, you can see the same thing has happened here. Now I'm going to give you another example of a decorator. Remember the factorial function that we did earlier, where we did a check within the factorial function. Well, let's see how we can use decorators to aid our case in this. So as we know, before we calculate the factorial of something, we want to make sure that whatever we pass is greater than or equal to 0 and it's an integer, right? So let's define a decorator which will basically do this. So in this decorator, what we're going to do is we're going to call create a function called helper, where we're going to perform this check, and this is going to be our decorator basically, right? However, so what this will do is basically this decorator will say, okay, if this check is met, then you can return the value of function of x, which is the function is what we pass in this as an argument to the decorator. So once the check is done, we can perform a factorial. So that's what we're going to do here. So we've defined our decorator. Now we're going to use the decorator here, and we're going to define within it a factorial function. So when we actually perform the factorial, like for some numbers, like we're going to do factorial of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all these 10 digits from 1 to 9, sorry. So if you're going to do that, what it's going to do is at each step, so for the value 1, it's going to first check whether our integer passed is actually the correct form of an integer, whether it's in integer and greater than or equal to 0. So once that is done, then it will move on to the actual factorial function. So when we do for I in range 1 and 10, since every number is valid, we won't get nothing wrong will happen. There won't be any exception raised. But what if we did factorial -1 now? Now the factorial function itself doesn't have a check, but since we have a decorator around this factorial function, it's first going to do this check, and if it finds an error, it will raise an exception. So if I do this, if you see when I execute, it raises my exception. So this is how we have added some functionality to the original factorial function using this decorator. Now Python provides several functions that enable functional approach to programming. And since functional programming is all about expressions, some of these expression-oriented functions of Python are Lambda functions, list comprehensions, map, filter, and reduce. Now we've already covered the topic of Lambda and list comprehensions. Now let's cover the topics of map, filter, and reduce. So to start off, let's look at the map function. The map function takes in two attributes, a function and a sequence. A function is basically some user-defined function or any function. A sequence is basically an iterable object like a list or a tuple, for example, or a bunch of lists and tuples as well. So let's look at an example. So one of the most common operations that we do with something like a list is doing an operation on each of the elements in the list and then outputting a new list with the values as whatever we have modified to the original items of the list. So what if we did the square of all of these items in this list, and we want to create a list based on that? So we can basically iterate through it, and we can do a square function and then append those values to a new list called squared. And when we do this, for example, over here, you can see when we print squared, we should get the list of whatever square values we have for the original list. But this is slightly a bit tedious. And what if we had a method what if we had a technique wherein we could basically pass a function that we have that we want to do and a sequence on which we want to apply this, and we pass it to a function, and this function basically takes care of applying whatever operations we want to do on each element of a sequence. So this is where the map function comes in use. So let's look at how we use the map function over here. So if you look at this, I've defined a square function. So the square function basically returns, takes an argument x and returns the square of it. And I have a map function which takes the square function as one of the arguments, and the list or an iterable as the second argument. So this map function creates a map object, if you see here. So let's just do it one by one. So I'm creating my list, and I'm going to create my function called square, and I'm going to send this to the map function. So I'm sending this the first argument as the function that I want to do, and the second argument as the list that I want to apply it on. Now let's list out all the items that are in this map object. So if you see, it creates me a list with basically the squared items, and this is exactly what we needed. And another way of doing the same thing would be just going through a for loop in each of the map objects and printing each, which would give me the same results. So if you see here, I found a very neat way of passing a function and an iterable, and using the map function to apply each operation that is part of the function, or applying the function on each item in the iterable. So as you've seen, we basically passed in a user-defined function, and we applied it to each item in the list. Then the map calls the square function on each list item and collects all the return values into a new list. And because map expects a function to be passed in, it also happens to be one of the places where lambda functions are appearing a lot. So let's look at an example where we do the same operation using a lambda function. So if you see here, I have a lambda function where I'm passing it as the function argument, and what this lambda function takes is some variable x or some argument x, it does its square and it returns that x. And this x is basically going to come from each element that is present in this list called items. And when we list down these, you will see it basically does the same thing for us. It creates a list with squared items. Now we can also pass, instead of passing an iterable itself, we can actually pass a sequence of functions and use the lambda function to perform a sequence of functions on particular items. So let's look at a new example, a slightly different one. So we're going to use a NumPy module for this. Don't worry, we're just using it to use the square root function that is present in the NumPy module. We will be learning about NumPy in a later section. So we're going to import this first. And now I'm going to define three functions called square, cube, and square root. So once I've defined these, basically they're returning the square, the cube root, the cube, and the square root of some integer x. And now I'm going to create a list of these functions that you've just seen. And we're going to use a for loop, and we're going to iterate through a range from 0 to 4. So, and we're going to pass this, and we're going to say that we want to apply some function. We want to apply some function x, and we want to return that using this lambda function. Now what values this x will take is based on whatever functions we've stored in this variable called funcs or funcs. And in funcs, we have a bunch of functions called square, cube, and square root that we have defined earlier. So what we're going to do is we're going to apply each of these functions to R, and R will take the values 0 to 4. And now let's see when we print this, what values we get. So if you see here, we get a list of squares, cubes, and square roots for integers 0, 1, 2, 3, and 4. So this is another way of using the map function and lambda functions together to apply multiple different operations to a bunch of iterables. Now for our next example, what we're going to do is we're going to create a function that basically what it does is it creates the uppercase of some string that we pass to it, right? So that's what we've done here in this function called toUppercase. So let's first define this function. Now we have a print function basically which is going to print each object in a particular, which is going to print each element of a particular object, and is going to at the end of it, and the end of printing, we're going to give a small space for printing a new line basically. So let's create this also, this print iterator object. Now what we're going to do is we're going to pass a string with the letters A, B, and C to this function, and we're going to map, we're going to apply the uppercase function to this string. Now if you remember, string is also an iterable where it's a sequence of one character strings. So this whole string is basically a sequence of one character string A, one character string B, and C. So we're going to, we can pass a string as an iterable to the map function because it will apply the operations on each of these characters. So let's see what happens when we do the uppercase function. We apply the uppercase function using the using mapping to the string A, B, and C. So if you see, it's created me a list with capital A, capital B, and capital C as we had expected because we have applied the list function to the map object. Now, in the next step, what we're going to do is we're going to do a very similar thing. We're just going to, instead of simply mapping and creating a list out of it, we're going to store the map object in a variable called map iterator. We're going to print what type of object it is, and then we're going to print out each of the elements using the print iterator function that we defined here. So let's do this. Now, if you see, the class, the type of object is of class map, and the objects elements inside the object are A, B, and C. Moving on. Let's look at now an example where we're going to pass multiple arguments. So instead of one iterable, we're going to pass multiple iterables now, and we're going to apply some sort of an operation. So if you see here, what we have done is we've created two sequences. One is a list of some numbers, and another is a tuple of some numbers. So just to show you, let me first copy this here. Yeah. So if you see here, I have a list and a tuple. And I'm passing both of these, if you see, to this map function. And before that, I have defined a lambda function as the operation that I'm going to apply. And what this does is it takes two arguments, x and y, and it returns the product of both of these. Where does it get x and y from? So the x it gets from this sequence, which is a list, and it takes y from this sequence, which is a tuple. So what it's going to do is going to take x as 1 and then y as 5 in the first step, and it's going to return the product as 5. And then the next step is going to take 2 as x and then y as 6, and is going to return the product of that, and we're going to get 12, and so on. We're going to get 21 and then 32. These values are going to be stored in the map iterator, which is a map type object. And when we use the print iterator function, it's basically going to print out whatever results we got through this mapping. So let's execute this, and as you can see, this is the result we got: 5, 12, 21, and 32, which is what we wanted. So the next part, the next function that we're going to discuss is the filter function now. Now a filter function is basically, again, it takes two arguments, a function and a sequence, and a function basically tests if each element of a sequence is true or not. Now so this filter function will basically take two arguments. So one is the function, and this function is basically going to test if each element of a sequence is true or not, and it's going to take another argument called sequence. And this argument sequence is the list or the tuple or basically any sequence or iterable that needs to be filtered. And it can be, as I mentioned, it can be sets, lists, tuples, or containers of more iterators. And what this function will return is an iterator that is already filtered. So let's look at an example now. So we have this list R, which we've generated, which is basically numbers from -5 to 4. So if I create this list here, you can see it will create a list of -5 to 4. Now, if I wanted to extract only the values that are lesser than 0, well, I can use a for loop and use a if condition to check this, right? So if I did this over here, you can see it returns me some list called result, which contains only the values lesser than 0, which is basically checked through this condition. What if there was a neat or a more convenient or a more organized approach to doing the same thing? Instead of creating a loop ourselves, what if we defined a function where we are going to do the test, or we're going to create the condition, and we're going to pass this to a particular function and then apply that particular operation on every object of some sequence? Well, just like mapping, we have a filter function to do this. And in this example, what we're going to use is the lambda function, which takes an argument x, and it checks for some condition x lesser than 0. And where it's going to get the x from is some sequence R, which in our case is the numbers from -5 to 4. And the filter will basically create a filter object type, which contains only the objects from R that meet this condition, that is x is lesser than 0. And when we use the list operation on top of it, you will see it results in a list with the values that have met my condition. So for our second example, what we're going to do is we're going to create a list which contains a bunch of letters, and we're going to only extract the vowels from these bunch of letters. So let's look at what we have here. We have some letters D, A, T, J, K, O, P, L, and we only want the vowels from this. So we want to filter only the vowels. So we can use that using the filter function by first of all defining a function that returns true if a check is met that one of the letter matches one of these letters in this list called letters. And if it doesn't, it returns false. So this is our condition that we've created. Once we create this condition, this function that checks this, we can pass this function and the sequence into the filter function, and then we can list out whatever we get. So you can see our filtered list contains only A and O, which is basically the only vowels that are present in our original list. Finally, we have the reduce function. This reduce function is basically a functools. It's in the functools module of Python 3.0. And what the reduce function does is it applies a function of 2 arguments cumulatively to the elements of an iterable, and it optionally starts with an initial argument, and it returns a single result. So let's first import this function. And once we've imported it, let's use it in this example that we have here. So in this example, what we're going to do is we have some list called numbers, right? What if we wanted to get the sum of each element in this list? Well, we can iterate over it and store it in some variable called total in each step, right? This is what we would typically do. And in this step, what you can see is the loop basically iterates over every variable in numbers and accumulates them in total. The final result is the sum of all the values, which is the value of 10 over here. In this example, the variable total is what we call an accumulator, and we can apply the reduce function to do the same task. So how do we do it? Let's first of all create a function called myAdd, where we're going to take 2 variables, 2 arguments, and we're going to return the sum of it. Okay, so let's define this function, and now we have a list called numbers, right, which contains 1, 2, 3, and 4. Now let's do reduce myAdd to numbers. Now when I use this function, what it will do is it will apply the function of myAdd. It will take basically each and every element in a sequence. So it will take 1 and 2, then add them together, and then it will create, basically what it will do is it will take 1 and 2, add them together, then we'll have 3. So it will take 3 and then the next element, which is 3 again. So it will create the sum, which is 6, and then it will take 6, and then it will take the value 4, and it will give us the result 10. So this is how the reduce function would work. So this is how it will give us the result of 10. As you can see here, I've passed this function where I've defined that I want 2 arguments to be passed to a function, and then the return should be basically the sum. And then I've passed a whole list of like 4 numbers, and I've used the reduce function to basically do this process for 4 numbers in a step-by-step manner by taking 2 at a time subsequently. And my result, as you can see, is correct, as you can see here. So let's use the lambda function now to do the same task. So what I'm doing now is I'm going to define a lambda function, and that's the function I'm going to pass to this reduce. So when I pass this lambda function, which basically takes 2 arguments, x and y, and it's going to return the sum of that as x plus y. Now where it's going to get x and y from is in a very neat manner. So it will take first the first 2 elements, 1 and 2. It will then do the sum, and we get 3. Then it will take that same 3 and then take the next object, which is 3 again, and then give us 6. Then it will take 6 and then the next element, which is 4, and then give us 10. And then the reduce function will output the single result, which is 10 to us, as you can see here. So yeah, this was our video, a discussion on map, filter, and reduce functions in Python. Now a lambda function in Python is an anonymous function without a name. We usually use lambda functions whenever we want to create a function type object for a short period of time. A lambda function is defined using the lambda keyword. Like a normal function is defined using the def keyword, we define a lambda function using the lambda keyword. Also, the lambda function can take any number of arguments, but it can only accept one expression as a part of it. So think of a lambda function like a sort of a temporary function object that you create whenever you want to perform a particular task or object, but you don't want to give it a name, or you don't want to define a full-blown function and give it a name like that. So over here, I'm going to give you an example of a lambda function. Let's say that this lambda function takes in, let's call it x, and so you define the function, let's call it x, let's call it a lambda function using this keyword. Now we want, say, 2 parameters, right? We're saying, say, a and b, or 2 arguments, a and b. So we're going to pass 2 arguments, a and b, whenever we use this function, and we're going to perform some sort of an expression. Now let's write down a simple arithmetic expression for this. Once you've defined your arguments, just use a colon. Now over here we have our expression. So let's call it a plus b. So now we've created a lambda function called x, where we will pass 2 arguments, and the result will be the expression a plus b. A and B being the arguments we pass. So now let's print the result of, let's say we pass 1 and 3. So now we should get the result 4, right? Because A plus B is equal to 4. So we've passed A as 1, B as 3. Now let's execute this. As you can see, the result is 4. Similarly, you can pass any number of arguments. So we want to call some function x, let's say lambda function. Maybe say A, B and C this time. And we want to do the product of these 3 arguments. So now when we do, when we check the result, let's say we're doing the product of 2, 4 and 6. So this should be 48. And when you execute this, you get 48 as you can see here. So these are 2 simple examples of a lambda function. Now I could have done this in a different way, where I could have defined some function x, and over here I defined that it takes in 3 parameters, and then you can define some, say, return. The function basically returns you A, product B, product C. But many a times you don't need to define a full function called x. You don't want to assign some function with this name. You just want to create a temporary or a short time anonymous function with some name just to perform a simple expression. And in that case, we can use lambda functions. That's an example, by the way. You can use lambda functions in multiple places. So let's move on now. Now, for the sake of this video, what I'm going to do is I'm going to show you how the sorted function works, and we're going to learn how the lambda function uses this sorted function, how they work together. So this will give you a clearer understanding of how we use the lambda function in our code. So to start off, sorted function returns a sorted list from the items in an interval. So you can have a bunch of, for example, numbers, and the sorted function by default will give you, will return you the list of numbers in an ascending order. Of course, you can also, using a parameter called reverse, you can return a list of numbers in the descending order. You can also do this for strings, characters. So if you give it a bunch of characters, say A, E, F, G in the alphabet, it will give you, if you use a sorted function, it will give you the characters. It will return it in an ascending or descending order depending on the parameter you give. So basically this the sorted function, the syntax is you use the keyword sorted, then you pass the iterable, which is basically some list or some tuple. Then you give it a key. So this key sometimes we don't need to give by default. If the iterable does not contain multiple items per object, for like if it's not a tuple of multiple objects, if it's not a list of tuples, for example, you don't need to give it a key. If it's a simple list of numbers, you don't necessarily need to give a key if you want to sort it. But yeah, a key is basically the parameter which we use to tell the sorted function that we want to sort based on something, which is going to be the key in this case. Finally, the third parameter is reverse, which basically just tells us that if we want to sort in the default ascending order, or if we say reverse true, then we will sort in the descending order. Now let's look at some examples. So I have this list over here, and I'm going to print this list. So this list is obviously a bunch of vowels, E, A, U, O, I, and this is not in the ascending order of the alphabet, right? Like we know it as A, E, I, O, U. If I print the sorted form of this list, it should give me A, E, I, O, U, a list with A, E, I, O in the ascending order. Sorry, yeah. So now as you can see, it's given me this list as you can see here. Similarly, if I give it a string as you know is an iterable. It's a collection of characters. So if I use a sorted function on this, interestingly, it will give me a list of these individual characters like P, Y, T, H, O, and N, but in the order that we want it to be in, which is the ascending order, of course. So if I print this, you can see it returns me the list with each character in the order that we wanted it to be in. Now you might notice, why does P come before H? That's because this is in uppercase. So what this does is, first it sorts all the uppercase characters. Since there's only one, so it just places it in the first object of this list, and then it sorts all the lowercase characters that you see here. So yeah, moving on now. Now what if we wanted to say sort this in descending order? So we have this list, and now we want to sort this in a descending order. So in that case, we have to give the parameter reverse, and we have to assign the value true. So once we do this, now when we execute this, you can see we have the return as the same list but in the opposite order. So that's how the reverse parameter works. Now let's try to understand how we use the key function or the key parameter in the sorted function. Now, of course, if we want to sort something based on some key that we want to define, we use the key parameter. So let's take an example now. So in this example, what we have done is I've defined this function called take second. So what this does is it takes the second element of a list of tuples. So what is this list of tuples? Well, this is random. You can see this random. This is a list of tuples. So this is one tuple. This is the next tuple. And what I'm going to do is, in this example, I'm going to create a key out of every second element in each tuple. So I'm going to create a key out of 20, 40, 10, and 13. And based on these, in an ascending order, I will sort this whole list. So what my result should be is that since the smallest of the every second object in these tuples is 10, so this will be my first object in my sorted list. Then it should be the one with 13 because this is the next highest number. So then this will be the next object. Similarly, this will be the next object, then this will be the whole next object. So you see I'm using every second element of the tuple as my key. And for that, to create a key basically, I'm creating this function which will basically return every, it'll iterate through all of these and it will return each of these second elements. So let's actually do this now. So what I have here is I am going to create a sorted list which is going to use a sorted function on this iterable, which is a bunch, which is a list of tuples. It's called random. Now my key is going to be take second. So this sorted function is actually very dynamic in the sense I don't exactly have to create a list directly each of these objects present in the tuples. I just have to define I can even pass a function in the parameter for key, and it will apply this function on the iterable that we pass over here, which is random namely, and it will use this function to generate keys, generate a key out of each second element, and based on that it will do the sorted, it will perform the sorted function. So now if I check what's my sorted list, you will see that as I had mentioned, now it's using the second objects or the second each second object of the tuple as the key. So since 10 is the smallest, this whole object is the first object. Then 13, so we have this object here, and then so on and so forth. So this is how we've used a key to do the sorting function, a key that we've defined on our own. Now similarly, we can use multiple keys as well. So just to quickly go over through this, we have this some list where a bunch of names, a bunch of tuples you can see, right? Tuples with 3 objects each within it. Each first one is always a string denoting someone's name, some student's name. The second is the marks out of 100, and the third is their age. So what we have here is, what we want to do is we want to sort these tuples in the order of first marks, and in case the marks are clashing or they are the same basically, we will sort by the age. So what we want to do is we want to first sort by these marks, as you can see here, but in case they clash, for example, like say this 75 and 75, they're the same marks. In that case, we want to sort it by the age, which is 12 and 20, which is different. So in this case, we're going to use 2 keys. One for the first key will be given the highest priority, and then if there is a clash, then we use the second key. So how do we do this? Now let's define some function, like how we defined this take second function here. This will be our function that we will pass to the key. This function basically what it does is it gives us who has the highest marks. Now since we are creating since the key works in an ascending order, so the smallest object in a key is the first object that gets returned, right? So what we're going to do is we're going to return the error, which is basically the difference between 100, which is the total marks, and the marks the student gets. So this is how we obtain a ascending order in our list, which is what which basically is what we want, because we want the highest marks to be first. So we do 100 minus item 1. Item 1 is basically the first object of whatever iterable we pass. In this case, it would be the first objects of each tuple, which is the marks. Secondly, we want age. Age is the item 2, which is each second object of each tuple. Now, what we return in this function is like this is going to be our key now. A list of errors and the list of age. Error being the marks error, the difference between 100 and the marks you obtain. So now what it's going to do is it's going to take the marks as the first key and the age as the second key when we pass this to a sorting function. So if you skip this, you don't have to look at this, but if you look at this now, we have the sorted list, which is going to be the result of the sorted function on top of what we pass, which is the participant list. Now we're going to use the key. We're going to use the key as the sorter function. So we're going to use the sorter function as a key. And when we print, if you see, we get, let me just execute all of this. So if you see here in this section, what you can see is we have the highest marks first, then the second, then the third. But if you see here, there's a clash. This guy and this guy have the same mark, 75. So now what we want to do is the guy who has the younger age should be in the first in the object. So that is how this has happened, because we've passed two keys, error and the age. So when the clash in error key happened, we went to the age key and then we did ascending order on that. And then finally the rest of the objects that you can see here. So now that we've seen how the sorted function works, now let's look at how the lambda function works using this sorted function, which was the main goal of this video, right? So let's see. So now some of you might have figured out where this lambda function will be used, right? So whenever we were using the key in the sorted function, we had to define a function and then we would pass that function as the key. So as some of you may have figured this out, what we're going to do using the lambda function is we're going to skip that process of defining a function with a new name and all that, and we're going to pass a lambda function, or we're going to use a lambda function as the key. So let's see how we do it. So initially what we've done is we've created this list. This list is a list of dictionaries that you can see. So this first object is a dictionary, second object is a dictionary. Each dictionary contains two keys, the name and the age. And the values are something like Nandini, the values for age is like 20, 20 and 19. So we have three dictionaries in a list. So what we're going to do is we want to print, what we want to do with this, we want to print these objects or these dictionaries in an ascending order of age. So obviously we want this to be first, and then this and this, because 19 is smaller than 20. So let's see how we do this. So if you go here, what we're going to do is we're going to print the sorted function, or the result of the sorted function being applied on this list. So this is our iterable. Now if you see here in the key parameter, we don't predefine a function and pass it over here. Instead we use the lambda, and this lambda function is defined in such a way. So we say lambda, it will take one argument I, and then it will return basically the age index for some I, and this I is, we're going to presume an I to be some sort of an iterable which has an index called age, and which is the case in our case, right? We have a bunch of dictionaries where there is a key in each of these dictionaries called age. So we're going to use that. And now you're going to ask, like, what is I? Well, when we use the lambda function in the sorted function, this I will basically be each object that we get when we iterate upon this list. So we're going to iterate first on this. So it's going to take this dictionary and it's going to search for the age. Then it's going to take this, it's going to search for the age. Then it's going to take this and it's going to search for the age. And each of the time it will pull out what is the value for each of these age keywords or these age indexes or age keys. And out of these objects, so 20, 20 and 19, or these values, we're going to create a key with which we're going to sort each object in this whole list. Okay, so this is how the lambda function will work here. So let's do it. So as you can see, our sorted list now contains this object first, because 19 is the smallest age, and then this and this. Now you might see that there are two 20s. So how do we control which one comes first? Well, by default, it will just give us the result in the way we passed it in the original list. So since Nandini came before Manjeet, in the result also Nandini will come before Manjeet. But what if we wanted to sort it even more? What if we want to sort it in such a way that first we go by age, and the second key will tell us that if there is a clash in ages, we have to go alphabetically by the name. So in this case, we will create a second key. And how we do that? Well, if you go to this step, over here what we're doing is we're doing the same sorted function, but now the lambda will again take one parameter, which is I, which is going to be each object in this iterable list, and we're going to take two keys. So the first key will be the age key and the second key will be the name. So it will first sort on age and then on name. So now if you see, the result should be that Manjeet will come before Nandini, even though the ages are 20, because M comes before N in the alphabet. As you can see, this is the result. Now if we wanted to do the same thing, but in a descending order, all we have to do is after this key parameter, we have to give another parameter called reverse. And we have to give it true. So if we did this, now you see this, or if we do it on this one, to be more clear. Now if I execute this, basically this whole, whatever result we get will be backwards now. Oh wait, I did not enter it in the sorted function. So this should come within the sorted function over here. So now if we execute this, you will see Nandini comes first, Manjeet comes second, and then Nikhil comes third. Because we've done the reverse, we use the reverse keyword as true, reverse parameter as true. So this was a brief lesson on lambda functions.
So let's start with what is NumPy. NumPy is the core library for scientific and numerical computing in Python. It provides high-performance, multi-dimensional array object and tools for working with arrays. And I'll go a step further and say there are so many other modules in Python built on NumPy. So the fundamentals of NumPy are so important to latch onto for the Python, so that you can understand the other modules and what they're doing. NumPy's main object is a multi-dimensional array. It is a table of elements, usually numbers, all of the same type, indexed by a tuple of position integers. In NumPy, dimensions are called axes. Take a one-dimensional array, or we have, and remember dimensions are also called axes, you can say this is the first axis, 0, 1, 2, 3, 4, 5. And you can see down here it has a shape of 6. Why? Because there's 6 different elements in it in the one-dimension array. And they usually denote that as 6 comma with an empty node on there. And then we have a two-dimensional array where you can see 0, 1, 2, 3, 4, 5, 6, 7. And in here we have two axes or two dimensions, and the shape is 2, 4. So if you were looking at this as a matrix or in other mathematical functions, you can see there's all kinds of importance on shape. We're not going to cover shape today, but we will cover that in part 2. Did you know that NumPy's array class is called NDArray for NumPy Data Array? Now we're going to take a detour here because we're working in Python, and two of my favorite tools in Python is the Jupyter Notebook, and then I like to use that sitting on top of Anaconda. And if you flip over to jupyter.org, that's jupyter.org, you can go in here. You can install it off of here if you don't want to use the Anaconda notebook. But this is the Jupyter setup, the documentation on the Jupyter. Jupyter opens up in your web browser. That's what makes it so nice, is it's portable. The files are saved on your computer. They do run in IPython or IronPython. And you can create all kinds of different environments in there, which I'll show you in just a minute. I myself like to use Anaconda. That's www.anaconda.com. If you install Anaconda, it will install the Jupyter Notebook with the Anaconda separate. And you can install Jupyter Notebook and it'll run completely separate from Anaconda's Jupyter Notebook. And you can see here I've now opened up my Anaconda Navigator. What I like about the Navigator, and this is a fresh install on a new computer, which is always nice, I can launch my Jupyter Notebook from in here. I can bring other tools, so the Anaconda does a lot more. And under environments, I only have the one environment, and I can open up the terminal specific to this environment. This one happens to have Python 3.7 in it, the most current version as of this tutorial. And then you open a terminal if you're going to do your pip installs and stuff like that for different modules. You can also create different environments in here. So maybe you need a Python 3.6, Python 3.5. You can see we're having a nice framework like Anaconda really helps. So you don't have to track that on your own in the Jupyter Notebook and your different Jupyter Notebook setups. We'll go ahead and launch this Jupyter Notebook. And then I've set my browser window for a default of Chrome. So it's going to open up in Chrome. And you can see here, this opens up a folder on my computer. We have a couple different options on here. Remember, I set the environment up as Python 3.7. you would install any additional modules that aren't already installed in your Python on this. And it keeps them separate, so you do have to, for each environment, install the separate modules so they match the environment on there. And in here we have a couple things where you can look up what's running. You have your different clusters. Again, I just installed this on a new machine, so I just have a couple things in here that were run on here recently. And where we go on here is we then have on the upper right, New, and from the pull-down menu you'll see Python 3. And this will open up a new window. And now we're in Jupyter Python. So this is a Python window, and we'll just do a print. And this, of course, is let's go hello world. And we'll run that, and it prints out hello world in the command line. There's a couple special things you have to know what we're not going to do today, which is on graphics. If you've never seen this, one of the things you can do is you can also do A equals hello world. And if you just put the A in there, now if you do a bunch of these where you have A equals hello world, B equals goodbye world, and you put A, B, A, then return B, it'll only run the last one. But you can see here, if you put the variable down here, it will show you what's in that variable. And that has to do with the Jupyter Notebook inline coding. So that's not basic Python, that's just Jupyter Notebook shorthand, which you'll see in a little bit. So back to our NumPy array versus Python list. Python list being the basic list in your Python. Why should we use NumPy array when we have Python list? Well, first, it's fast. The NumPy array has been optimized over years and years by multiple programmers, and it's usually very quick compared to the basic Python list setup. It's convenient, so it has a lot of functionality in there that's not in the basic Python list. And it also uses less memory, so it's optimized both for speed and memory use. And let's go ahead and jump into our Jupyter Notebook. Since we're coding, best way to learn coding is to code. Just like the best way to learn how to write is write, and the best way to learn how to cook is cook. So let's do some coding here today. And just like any modules, we have to import NumPy. We almost always import it as NP. That is such a standard. So you'll see that very commonly. We can just run that. And now we have access to our NumPy module inside our Python. And then the most common thing, of course, is to go ahead and create a NumPy array. And in here, we can send it a regular list. And so we'll go ahead and send this a regular array. Let's go 1, 2, 3 to make it simple. And then I'm just going to type in A, and we'll run this. And so you can see down here, the output is an array of 1, 2, 3. And we could also do print, just a reminder that this is an inline command, so that wouldn't work if you're using a different editor. You can see that it's an array 1, 2, 3. But we'll go ahead and leave it as A. Kind of a nice feature so you can see what you're doing really quick in the Jupyter Notebook. And just like all your other standard arrays, I can go A of 0, which is going to be a value of 1. Of course, we do A of 1. You go all the way through this. A of 1 has a value of 2 in it. So whether you're using the NumPy array or the basic Python list, that's going to be the same. That should all look pretty familiar and be pretty straightforward. Remember, the first value is always 0 and when we set on there. So let's take a look why we're using NumPy, because we went over the slide a little bit, but let's just take a look and see what that actually looks like. And what we want to look at is the fact that it's fast, convenient, and uses less memory. So let's take a glance at that in code and see what that actually looks like when we're writing it in Python and what the differences are. And to do this, I'm going to go ahead and import a couple other modules. We're going to import the time module so we can time it. And we're going to import the system module so that we can take a look at how much memory it uses. And we'll go ahead and just run those so those are imported. And so we'll do B equals range of 1. Yeah, 1,000 is fine. And so that's going to create a list of 1,000, 0 to 999. Remember, it starts at 0 and it stops right at the 1,000 without actually going to the 1,000. And let's go ahead and print. And we want system.getSize of. And we'll pick any integer because we have, 0 to 1,000. We'll just throw one in there, 5. It doesn't matter because it's going to whatever integer we put in there is going to generate the same value because we're looking at the size of how much memory it stores an integer in. And then we want to have the length of the B. That's how many integers are in there. And if we go ahead and execute this and run this at a line, we'll see, oops, I did that wrong, comma. If we multiply them together, we'll see it generates 28,000. So that's the size we're looking at is 28,000. I believe that's bytes. That sounds about right. So let's go ahead and create this in NumPy, and we'll go C equals NP. and this is a range. So that's the numpy command to do the same thing that we were just doing in a list. And we'll also use the same value on there, the 1000. And then once we've created the value of C for np.arange, let's go ahead and print. And we can do that by doing c.size times c.item size. And that's very similar to what we did before. We did get the size of, so the C size is the size of the array, and each item size, just reversed. So it's the size of an integer 5, item size is going to be the integers, and C size. And let's just take a look and see what that generates. And wow, okay, we got 4,000 versus 28,000. That's a significant difference in memory, how much memory we're using with the array. And then let's go ahead and take a look at speed. Let's do size. We tried this with lower values, and it would happen so fast that the NP array kept coming up with 0 because it just rounded it off. So size, and let's create an L1 equals range of size, and we'll do an L2. We'll just set up to the same thing. It's also range of size on there. There we go. And then we can do on A1 equals np dot arange size. And then let's do on A2 equals np dot arange. We'll keep it the same size. And what we're going to do is we're going to take these two different arrays and we're going to perform some basic functions on them. But let's go ahead, actually let's just load these up now. We'll go ahead and run this so those are all set in memory. Except for the typo here. Quickly fix that. There we go. So these are now all loaded in here. And let's do a start equals time.time. So it's just going to look at my clock time and see what time it is. And then we'll do result equals, and let's do, let's say we got an array, and we're going to say, let's do some addition here. X plus Y for X comma Y, and we'll zip it up here. Two different arrays. So here's our two different arrays. We're going to multiply each of the individual things on here. L1, L2. There we go. So that should add up each value. So L1 plus L2, each value in each array. And then we want to go ahead and print. And let's say Python list took. And then we'll do time dot time. We'll just subtract the start out of there. So time, whoops, I messed up on some of the quotation marks on there. Okay, there we go. Time minus the start. And we'll convert that to seconds. So we'll go, because that's in milliseconds, so times 1000. And let's hit the run on there. This is kind of fun because you also get a view while we're doing this of some ways to manipulate the script. And as you can see also my bad typing. There we go. Okay, so we'll go ahead and run this. And we can see here that the Python list took 34. Actually, I have to go back and look at the conversion on there. But you can see it takes roughly 0.34 of a second. And we can go ahead and print the result in here too. Let's do that. We'll run that just so you can see what kind of data we're looking at. And we have the 0, 2, 4, 6, 8. So it's just adding them together. It looks pretty straightforward on there. And if we scroll down to the bottom of the answer, again we see Python list took 46. A little different time on there depending on what core, because this is on an 8-core computer, so it just depends on what core it's running on, what else is pulling on the computer at the time. And let's go back up here and do our start time. Paste that into here. And this time we're going to do a result equals, and this is really cool. Notice how elegant this is. It's so straightforward. This is a lot of reason people started using NumPy is because I can add the two arrays together by simply going A1 plus A2. It makes a lot of sense, both looking at it, and it's just very convenient. Remember that slide we're looking at? Fast, convenient, and less memory. So look how convenient that is. Real easy to read, real easy to see. And I don't know if we don't need to print the result again, so let's just go ahead and print the time on here, and we'll borrow this from the top part because I really am a lazy typer. And this isn't the Python list, this is the NumPy list, or NumPy array. And let's go ahead and see how that comes out. And we get 2.99. So let's take a look at these two numbers, 46 versus 2.99. So we'll just round this up to 3. That's a huge difference. That's like more than 10 times faster. That's like 15 times roughly at a quick glance. I'd have to go do the math to look at it. And it's going to vary a little bit depending on what's running in the background on the computer, obviously. So we've looked at this, and if we go back here, we found out it's much faster. Yes, there's going to be different speeds depending on what you're doing with the array. Very convenient, easy to read, and it uses less memory. So that's the core of the NumPy. That's why a lot of people base so many other modules on NumPy and why it's so widely used. So we did glance at a couple operations while we were looking at speed and size. Let's dive into a little bit more into the basic operations. And these are always nice to see. I mean, certainly you want to go get a cheat sheet if you're using it for the first time. Look things up. Google is your friend. We did this for the most basic numpy.array or np.array. And we'll go ahead and create an array. Let's do pairs, 1, 2. And then let's do 3, 4. And if we're going to do that, let's do 5, 6. There we go. And if we go ahead and take this and run this, I can go ahead and do our A down here so it's in line, and it'll print that out. You can see it makes a nice array for us. So we have A, and if you look at that, we have 3 different objects, each with 2 values in them. And hopefully you're starting to think, well, how many dimensions or indexes is that? And you'll see 3 by 2. So let's go ahead and take a look, and let's go, how about A.nDimensions? Speaking of which, we'll run that, and we have 2 dimensions for each object. And then we can do the item size, so A dot. We saw this earlier, where we looked up how many items. It was up here, where we wanted to multiply item size times the actual size of the object. So the memory is being used versus the item size. And we should see 4 there. Memory is compressed down. That's always a good thing. And then the shape. The shape is so important when you're working with data science and you're moving it from one format to another. So we have our shape. We just talked about that. We have 3 by 2. 3 rows by 2 objects in each one. Generally, I don't look too much at the size, but the dimensions I'm always looking up. And this is nice, you can automate it. So you might be converting something, you might need to know how many dimensions are going into the next machine learning package so that you can automatically just have it send that information over. So we looked at A shape. Let's go ahead and create a slightly different array, np.array. Let's go ahead and just do as our original setup here. And one of the features we can do, which is really important, is we can do dtype equals, in this case, let's do np float 64. And so what we've done is we're converting all of these into a float, and we type in A. And now instead of having 1, 2, 3, 4, 5, 6, you see they're all float values. 1.0, there's no actual 0 in there, just there's a 1 dot, or the 1 period, 2, 3 period, 4 period, 5 period, 6 period. And this, again, data science, I don't know how many times I've had to convert something from an integer to a float so that's going to work correctly in the model I'm using. So very common features to be aware of and to be able to get around and use. And we'll also do, let's just curiosity, item size. We'll go ahead and run that. And we see that it doubled in size. So it's not a huge increase. Well, doubling is always a big increase in computers. But it's not a huge increase compared to what it would be if you're running this in the Python list format. And then we did the shape earlier without having it set to the float 64. Let's go ahead and do A shape with it set to 64. And it should be the same 3, 2. So it all matches. So we've gone through, and remember, if this is all brand new to you, according to the Cambridge study at the Cambridge University, if you're learning a brand new word in a foreign language, the average person has to repeat it 163 times before it's memorized. So a lot of this, you build off of it, so hopefully you don't have to repeat it 163 times. But we did manage to repeat it at least twice here, if not a little bit more. And let's go ahead and take this. We're going to go look at one more setup on here. And let me just take this last statement here on the converting our properties of our data. And instead of float 64, let's do complex. Let's just see what that looks like. And let's go ahead and print that out and run it. And so we now have a complex data set up, and you'll see it's denoted by the 1 dot plus 0 dot j. And if we flip over here and do a basic search for NumPy data types, better to go to the original web page, but pull up a bunch of these. You can see there's a whole list of different NumPy data types. Shorthand, complex, we have complex, complex 64, complex 128. Complex number represented by two 64-bit floats, real and imaginary components. One option on there, float 16, float 32. Float, shorthand for float 64, most commonly used. And of course all the different ones that you can possibly put into your NumPy array. So we covered a basic addition up there when we were comparing how fast it runs. But some very basic components, how to set up a NumPy array, how many dimensions it has, item size, data type, item, again we went to item size, and there's also the shape. Probably one of the more used. I use a shape all the time, very commonly used. And then down here you can see where we actually created a NumPy complex data type. So let's look at some other features in NumPy. One of them is you could do NumPy dot zeros, and we're going to do 3, 4. There we go. And we'll go ahead and run this, and you can see if I do np.zeros, I create a NumPy array of zeros. This is really important. I was building my own neural network, and I needed to create an array where I initialized the weights, and I wanted them all to be the same weight. In this case, I wanted them to start off as 0 for the particular project I was working on. And there's other options, like you can do NumPy1s, and we'll do the same thing, 3, 4. We'll run that. And you can see I've created an array of NumPy1s. In this case, it comes out as a float array. And then this is an interesting to note, because we have, let's go back to our Python and do L range 5. And we'll print the L. So that's our list. And if I run that, it doesn't create the range until after the fact, until you actually execute it. That's an upgrade in Python. Python 2.7 actually created the array 0, 1, 2, 3, 4. This one actually creates the script, and then once it's used, it then actually generates the array. And if we do that in NumPy A range, remember that from before, and if we do NumPy A range 5, and let's do L equals, or we can just leave it as NumPy, that's fine. There we go, just run that. You can see there we actually get an array, 0, 1, 2, 3, 4 for the value of the NumPy A range 5. It generates the actual array. And for part 1, we're going to do just one more section on basic setup. And we're going to concatenation, do a concatenation example. There we go. We're going to do strings. Let's take a look at strings and what's going on with there. And let's do, let's see, print. Let's do an np character, something new here. And we're going to add, and then here's our brackets for what we're going to add. And let's say, let's do hello, comma, hi. And in the brackets on there, let's create another one. And this one's going to be ABC, and we'll do XYZ. So we're just creating some, randomly making some up on here. And then we'll go ahead and just print this. If we run that, you can come down here, and of course make sure all your brackets are open and closed correctly. And then you can see in here when we concatenate the example in NumPy, it takes the two different arrays that we set up in there, and it combines the hello with the ABC and the hi with XYZ. And if we can also do something like print, let's do np character dot multiply. So there's a lot of different functions in here. Again, you can look these up. It's probably good to look them all up and see what they are, but it's good to also just see them in action. And let's do hello space, comma, 3, and we'll run this one and run that without the error. And you'll see it does hello, hello, hello. So we multiplied it by 3. And we can also, and let's just take this whole thing here instead of retyping it. And we can do character center. So instead of multiply, let's do center. And over here, keep our hello going. Take the space out of there. And let's do center at 20. And fill character equals, we'll fill it with dashes. So if we run this, you can see it prints out the hello with dashes on each side. And we keep going with that. We can also, in addition to doing the fill function, we can play with capitalize, we can title, we can do lowercase, we can do uppercase, we can split, split line, strip, join. These are all the most common ones. And let's go ahead and just look at those and see what those look like, each one of them. Here we're going to do the hello world, all-time favorite of mine. I always like to say hello universe. And you can see here we did a capital H with the world, but so we want to capitalize. So capitalize is the first one in the array. So we get hello world on there. And we can also take this, and instead of capitalizing, another feature in here is title. And let's just change this to how are we doing? How are you doing? Instead of we, we'll do you. And let's run that. And you can see here, because we created it as a title, it capitalizes the first letter in each word. And in this one, we're going to do character lower. Two different examples here. We have an array. We have hello world all capitalized, and we have just hello. And you can see that one is an array and one is just a string. If we run that, you get an array with hello world lowercase and hello lowercase. And if we're going to do it that way, we can also do it the opposite way. There's also upper. And let's paste those in there. And you can see here we have character.upper, opposite there, python.data, and we'll do Python is easy. Hopefully you're starting to get the picture that most of the Python and the scripting is very simple. It's when you put the bigger picture together and starts building these puzzles and somebody asks you, hey, I need the first letter capitalized, unless it's the title, and then you start realizing that this can get really complicated. So NumPy just makes it simple, and we like that. And so in this case, we did Python data. It's all uppercase. Python is easy, like shouting in your messenger. Python is easy. And then if you're ever processing text and tokenizing it, a lot of times the first thing you do is we just split the text, and we're just going to run this np.character.split. Are you coming to the party? If we do that, it returns an array of each of the individual words. Are you coming to the party, splitting it by the spaces? And then if you're going to split it by spaces, we also need to know how to split it by lines. And just like we have the basic split command, we also have split lines. Hello, and you'll see here the scoop in for our new line. And when we run that, if you're following the split part with the words, you should see hello, how are you doing? The two different lines are now split apart. And let's just review 3 more before we wrap this up. Commonly used string variable manipulations. We have strip, and in this case we have Nina, admin, Anita, and we're going to strip A off of there. And let's see what that looks like. And then you end up with nin, demin, nate. It basically takes up all leading and trailing letters. In this case we're looking for A. More common would be a space in there, but it might also be punctuation or anything like that that you need to remove from your letters and words. And if we're going to strip and clean data, we also need to be able to reformat it or join it together. So you see here we have a character join. We'll go ahead and run this. And it has on the first one, it splits each of the letters up by the colon and the second one by the dash. And you can see how this is really useful if you're processing, in this case, a date. We have day, month, year, year, month, date. Very common things to have to always switch around and manipulate depending on what they're going into and what you're working with. And finally, let's look at one last character string. We're going to do replace. If you're doing misinformation, this is good, pulling news articles and replacing is and what. In this case, we're just doing he is a good dancer. We're going to replace is with was. And you can see here, he was a good dancer. Hopefully that's not because he had a bad fall. He just was from 1920s and has gotten old. So there we go. We've covered a lot of the basics in NumPy as far as creating an array. Very important stuff here when you're feeding it in. How do we know the shape of it, the size of it? What happens when we convert it from a regular integer into a float value as far as how much space it takes. We saw that that doubled it. Item size, you have your in dimensions, and probably the most used is shape. And we'll cover more on shape in part 2. So make sure you join us on part 2 because there's a lot of important things on shape in there and setting them up. We also saw that you can create a zeros based array. You can create one with ones. If we do a range, you can see how it is a lot easier to use to create its own range, or a range as it is in NumPy. You saw how easy it was to add two arrays. We saw that earlier, just plus sign. Then we got into doing strings and working with strings and how to concatenate. So if you have two different arrays of strings, you can bring them together. We also saw how you can fill, so you can add a nice headline, dash, dash, dash. We saw about capitalize the first letter. We saw about turning it into a title, so all the first letters are capitalized. Doing lowercase on all the letters, upper for all the letters, just lower and upper, nice abbreviation. We also covered how to split the character set, how to strip it. So if you want to strip all the A's out from leading A's and ending A's or spaces, you can do that very easily. Also how to join the data sets. So here's a character join option for your strings. And finally we did the character replace. And here in our Jupyter notebook we can go under new and create a new folder, Python 3. I think I forgot to do this last time, but we could just do the Control++, which in any browser enlarges the page, makes it a lot easier to see. Always a nice feature. Another beautiful benefit of using Jupyter Notebook. And let me go ahead and show you a neat thing we can do in Jupyter. This is nice if you're working with people and you're doing this as a demo on a large screen. I'm going to do the hashtag or pound symbol array manipulation, kind of a title of what we're working on. And then I'm going to call this cell type markdown as opposed to code. And you'll see it highlights it here, and then if I run it, it just turns it into array manipulation. And then we're specifically going to be working on array manipulation, changing shape to start with. And we'll go ahead and mark this cell also a markdown, so it has a nice little look there. And then it comes up, and you can see it, just like I said, it just highlights it and makes it in bold print, just making it easier to read. Not a Python thing, but a Jupyter thing that's good to know about, especially if you're working with the shareholders, since they're investing money in you. Of course, the first thing we want to do is import. We're going to import NumPy as in P, and that should be standard by now. By now, you start a Python program, you're doing some data science. NumPy is just something you bring in there. And let's go ahead and create our array. And we're going to do that as the np.arange. Remember, that's 0, well, we're going to do 0 to 9. And then we'll go print, put a little title on the original array. We'll just print that array A. Remember from the first lesson, so we have our array which is 0, 1, 2, 3, 4, 5, 6, 7, 8. And let's add a print space in between. Let's create a second array, B, but we want this to reshape array A. And what does that mean? And the command is simply reshape. And then we have 9 items in here, and this is so important right now. So be very aware, if I did some weird numbers in here, it's not going to work. And we want multiples of 9. We know that 3 times 3 is 9. So we're going to reshape our A array by 3 by 3. And then we're going to print, well, let's give it a title. Oops, I had too many brackets in there. Modified array. And then let's go ahead and print our B. And let's see what that looks like. And as we come down here, you can see we've taken this and it's gone from 0, 1, 2, 3, 4, 5, 6, 7, 8 to an array of arrays. And we have 0, 1, 2, 3, 4, 5, 6, 7, 8. And so we split this into 3 by 3. And you can guess that if I tried to reshape this, let's just do a 5 by 3, which is 15, that's going to give me an error. So it's not going to work. You're not going to be able to reshape something unless the shape, all the data in there matches correctly. So we can take this flat 9, and they call it a flat because it's just a single array. And we can reshape it into a 3 by 3 array. And first you might think matrices, which this is used for that, definitely. I use it a lot in graphing because they'll come in that I have an array that's xy, comma xy1, y1, comma x2, y2. And so the shape of it might be 2 by the length of the number of points. And I need to separate that into x flat array and a y flat array. And you can see this can be very easy to reshape the array doing that. And we can of course go back. We can do b, do a print, and we'll do b dot flatten. Remember I said it's called a flatten array. And if we run that, you'll see it just goes back to the original one. It takes this 0, 1, 2, 3, 4, 5, 6, 7, 8 and flattens it back to a single array. And then one other feature to be aware of is if we flatten it, one of the commands we can put in there is order. Let me just go ahead and do that. Order equals F. Strangely enough, F stands for Fortran. The whole Fortran days. I remember actually studying Fortran programming language. In this case, you'll see that it uses the first, like 0, 3, 6 is the order. So instead of flattening it like we had before, 0, 1, 2, 3, 4, 5, 6, 7, 8, it now does 0, 3, 6, 1, 4, 7, 2, 5, 8. And if you go to the NumPy array page, you can see here that they have the flatten. I just open up the NumPy ND array flatten setup to look it up. And they have three different options. They have C, F, and A. And it's whether to flatten in C, which was based on how the C code works for flattening, or originally worked, which is row major. Fortran, which is column major, or preserve the column Fortran ordering from A. So whatever it was in, the default is the C version. So the default that you saw, you could put order equals C and it'd have the same effect as we saw there before. You could even do order equals A. That would also have the same effect because that's the default. So really the only other thing you usually change on here is to change it to C if you need it. And you can see right here, or F, I mean not C. The only thing you really want to change it to is to your F for the Fortran order, which then does it by column versus by row. And let's look at, here we go, reshape. So let's create a range of 12, and let's reshape it. And we'll do 4, 3 for this one. And remember this is NumPy. I forgot the NP there. np.arrange. And we can type in just A for print, or you can do full print A. And of course in Jupyter Notebook you even have a little extra print at the beginning. If we run this, we'll see we create a nice array of 0, 1, 2. It's reshaped it. So we have 4 rows and 3 columns, or you could call that 3 columns and 4 rows. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But this one is so important. We'll do np transpose A. Let's go ahead and run that. And it helps if I get all the S's in there and don't leave an S out. And you'll see here we've taken our array. If you remember correctly, we had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we've swapped it. So we've gone from a 3 by 4 or a 4 by 3 to a 3 by 4. And this really helps if you're looking at like a huge number of rows and the data all comes in. Like let's say this is your features in row 1, your features in row 2, and this is X, Y, Z. Well, when you go to plot it, you send it all of X in one array, all of Y in one array, and all of Z in another array. And so it's really important that we can transpose this rather quickly. This is kind of a fun thing. I can highlight it and do brackets around it, and if you remember correctly, because we're in Jupyter, it doesn't matter where we do the print or not. It'll automatically print it for us. And you see if I hit the run button, it comes up with the same exact thing. And let's play with the reshape, and you know what, let's zoom this up a little bit here. Make that even bigger so you can really see what's going on. And let's play with the reshape just a little bit more. We'll do B equals np.arange. Let's do 8. And reshape, we'll do 2, 4. Let's go ahead and print B and then run that. And you'll see we have now the 2 rows. This is a bit more like, so we have 4, maybe 2 rows of 4 things. So this might be all of our X components and our Y components. So we can switch it back and forth real easy. Important to note here, whether we do 2, 4, or in the case of 4, 3, this has 12 elements. And so however you split it up, it's got to equal 12. So 4 times 3 equals 12. That's pretty straightforward. Same thing down here. 2 times 4 equals 8. If I change this, and let's say I do 2, 3, let's just run that in, and you'll find we get an error because you can't split 8 up into 2 rows by 3. You have to pick something that it can split up and arrange it in. So let's go ahead and run that. And just for fun, let's go reshape our B again, if I can type. Reshape our B again. And what else goes into 8? Well, we could do 2 by 2 by 2. So we can take this out to 3 different dimensions. And then if we, because this is going to come out, as a variable, we can just go ahead and run it, and it'll print it. We could also do a print statement on there, just like we did before. And you'll see we have two different groups of two variables of two different dimensions. So 2 by 2 by 2. And let's go ahead and assign this to a variable. C equals B reshape. And let's do something a little different. Let's roll the axes. Roll axes. And we'll take our C and do 2, 1. And if we go ahead and run this, it's going to print that out. Whoops. Hit a wrong button there. Let's do that one again. And you roll the axis, and you can see that we now have, instead of 0, 1, 2, 3, 4, 5, 6, 7, we now have the 0, 2, 1, 3, 4, 6, 5, 7. So what's going on here? We're taking and we're rolling the numbers around, and let's just simplify this. We'll just do it with C, 1 and run that. And so if we roll a single axis, you got 0, 1, and then it rolled the 4, 5 up, and then we have 2, 3, 6, 7. And if we do 2, let me see what happens there. And this is one of those things you really have to play with and start feeling what it's doing. We've now taken 0, 2, 4, 6, 1, 3, 5, 7. So you can see we've now rolled by 2 digits instead of rolling the 1 setup. We now rolled 2 digits up there. And so if we go back and we do the 1, so we've rolled it up, 0, 1, 4, 5. And then we're going to take the 2 in there. And we've rolled the 0, 1, 2, 3, 4, 5, and 6, 7. So we start rolling these things around on here. There's a lot of different things you can do on this. But it's another way to manipulate the numbers on your NumPy. And finally, let's go ahead and swap axes. We'll do C. And let's just go ahead and run that. It's going to give me an error on there. That's because it requires multiple arguments. Left out the arguments. So now we can swap them. We get the 0, 2, 1, 3, 4, 6, 5, 7. So you can see everything's been swapped around. So next thing we want to go over is we want to go over NumPy arithmetic operations. How can we take these and use these? Let me just go ahead and put this cell as a markdown. There we go. We'll run that so it has a nice thing. All right, nice title on there. That's always helpful. And let's start by creating two arrays. We'll do A is an NP range, A range 9. And let's reshape this 3 by 3. So by now you should be seeing this reshape stuff, and this should all look pretty familiar. We have our 0, 1, 2, 3, 4, 5, 6, 7, 8 on there. And let's create a second one, B. And this time, instead of doing A range, let's do NP array. We'll just create a straight up array. And we'll do an array of 3 objects. So it's going to be 3 by 1. And if we go ahead and print B out, let me run that. This is actually pretty common to have something like this, where you have a 3 by whatever it is and a 3 by 3 array. When you're doing your math, you kind of have that kind of setup on there. And what we can do is we can go np.add AB. Don't forget, we can always put a print statement on there. So if we add it, you'll see that it just comes in there and it goes, okay, we're adding 10 to everything. And we could actually do something more, make it more interesting. 11, 10, 11, 12. So let's change B's now, 10, 11, 12, and let's run that. And you can see that we have 10, and then you had 1 plus 11 is 12, 2 plus 12 is 14, 13, so 10 plus 3 is 13, 11 plus 4 is 15, and 12 plus 5 is 17, and so on. We'll put this back, since that's how the original setup was. Let's do 10 by 10 by 10, and run that, and get the original answer. And if you're going to add them together, we need to go ahead and subtract AB, and we run that. We get minus 10, minus 9, minus 8, just like you would expect. So we have our subtraction. 0 minus 10 is minus 10, and so on. And if you're going to add and subtract, you can guess what the next one is. We're going to multiply. And we'll multiply AB. And this should be pretty straightforward. You should expect this. If we multiply 10 times 0, we got 0. 10 times 10 is 10, and so on. And finally, if you're going to multiply, what's the last one we got is divide. What happens when we do divide A by B? And we run this, and we're going to get 0. And this is 0 divided by 10 is 0, 1 divided by 10 is 0.1, 2 divided by 10 is 0.2, and so on and so on. So the math is pretty straightforward. It just makes it very easy to do the whole setup. And again, if we went this, and let's say, let's change this up here. Instead of 10, we do 100. And make this 1,000. There we go. And if we run that, and then we do the add, you can see we got 10 plus 100 plus 1,000. Same thing with the subtract. Same thing with the multiply. And then you can also see the same thing here with the divide. So a lot of control there with your array and your math. Again, let's set this back to 10. Oops, it's right up here, wrong section. There we go, 10. And we'll just go ahead and run these and get back to where we were. And this brings us to our next section, which is slicing. And let's put in our, we'll just make this a cell type markdown. And then we run that. Of course, it gives us a nice looking slicing there. And slicing means we're just going to take sections of the array. So let's create an array np a range. Let's just do 20. And if you remember, if we do a, we have a 0 to 19. And then we can do a, and remember we can always print these. This can always be put in a print, but because I'm in Jupyter, if you're doing a demo in Jupyter, it's just so great that you have all these controls on here. So we can slice 4 on, and this should look familiar because this is the same as a Python and a lot of other different scripting languages. If we do 4, it goes 0, 1, 2, 3, that's the first 4 in the thing, and it skips some and starts with this one. The first 4 are skipped, and then from there on. You can also do the opposite and go till the 4th one. If we run that, we get 0, 1, 2, 3. Quite the opposite on there. We can do a single item, so we can pick object number 5 on the list, run that, and 5 happens to be 5 because that's the order they're in. And then this one's interesting because I can do s equals slice, and let's create a slice here, and let's do 2, 9, let's leave it 2 on there. So we'll create an s slice on here. And then if we take our array and we do array of s, we're taking our slice in there, and let's go ahead and run that. And let's take a look and see what it generated here. First off, we started with 2, so we have 2 at the beginning. We're going to end at 9, which happens to be 8, so it stops before the 9. Remember when we're doing arrays in Python. And then we step 2, so 2, 4, 6, 8. We could do this as 3. Let me run that, and you can see how that changes, 2, 5, 8. And we could do this as, let's leave this at 3, and if we change this to 10, oops, let's make it 12. There we go. And we run that, we have 2, 5, 8, 11. So that's pretty straightforward. It's a very nice feature to have on here where you can slice it and take different parts of the series right out of the middle. So now that we've accessed the different pieces of our array, let's get into iteration. And this is interesting because my sister, who runs a college data science division, the first question she asks is, how do you go through data? And she's asking, do you know how to iterate through data? Do you know how to do a basic for loop? Do you know how to go through each piece of the data? And in NumPy, they have some cool controls for that. So put this in as a markdown. There we go, and run it. And it's called the ND-iter. I'm not sure what the ND stands for, but ND-iter for iterator. So before we do that, though, let's create an array or something we can actually iterate through. We'll call it a equals np a range. Let's do something a little funny here, or funky. And we'll do 0, 45, 5. I'm not sure why the guys in the back picked this particular one, but it's kind of a fun one. And if I run that, we do this, you can see we get 0, 5, 10, 15, 20, 25, 30, 35, 40. That's what this array looks like. And that's just from our slice. This is just a slice. That's all that is we created a slice of 0 to 45, step 5. And so we can do with this, we can also do a equals reshape. Let's go ahead and take and reshape this. And since there's 9 variables in there, we'll do a reshape it 3 by 3. So if we run that, whoops, missed something there. That is the A. That really helps. So if we do the A reshape, and we'll go ahead and print that out, we get 0, 5, 10, 15, 20, 25, 30, 35, 40. And then we simply do 4xn, our numpy ND-iter of A, colon, and we'll just go ahead and print x. And let's see what happens here when we run through this and we print each one of those. It goes all the way through the whole array, so it's the same thing we just saw before. We got 0, 5, 10, 15, 20, 25, 30, 35, 40. So it prints out each object in the array, so you can go through and view each one of these. And certainly if you remember, you could also flatten the array and just do for A and that also and get the same result. There's a lot of ways to do this, but this is the proper way with the ND iterator because it'll minimize the amount of resources needed to go through each of the different objects in the NumPy array. And hopefully you asked this question when I just did that. And the question is, how can I change this instead of doing each object? So first of all, let's go ahead and take my cell type and we're going to mark that down and run it. And so we're going to work on iteration order C style and F style. Remember C because it came from the C programming and F because it came from the old Fortran programming. So let's give us a reminder. We'll do a print A, and we'll do for x in np iterate A. But we also want to do this in a specific order. And you know what? I'm a really lazy typer, so let's go back up here. This is the ND iterator. I knew I was missing the ND part of A. And let's do order equals C. We'll print X on there. And let's do that again. And this time order equals F. There we go. Order equals F. And let's go ahead and run this and see what happens here. And the first thing you're going to notice, our original array, 0, 5, 10, 15, 20, 25, 30, 35, 40. When we do order C, that's the default, 0, 5, 10, 15, 20, and so on. And then when you come down here, you'll see F, order F, is 0, 15, 30. So it takes the first digit of each of the subarrays, or the second dimension, and then it goes into the second one, 5, 20, 35, 10, 25, 40. So slightly different order for iterating through it if you need to do that. So we've covered reshaping, we've covered math, we've covered iteration, we've covered a number of things. The next section we want to go ahead and go over is going to be joining arrays. So we need to bring them together. Let me go ahead and take the cell and make it a markdown. Cell type markdown. There we go. And run that. So let's work on joining arrays so we can bring them together and what different options we have. And let's do, we'll do an NP array 1, 2, 3, 4. We'll go ahead and print. Let's do, oops, first. Well, these arrays aren't that big, so let's just go ahead and keep it all on one line, A. So if we run this, first array 1, 2, 3, 4. Whoops, I forgot that it automatically wraps it when you do it this way. So we'll go ahead and keep it separate and print A. There we go. And let's go ahead and do a B. And we'll do 5, 6, 7, 8. And notice I'm keeping the same shape on these two arrays. Depending on what you're doing, those shapes have to match. And let's go ahead and print second array. Do a print B. We'll go ahead and run that. Oops. Missed something up there. Let me fix that real quick. When I was reformatting it to go on separate lines, I messed that up. There we go, run. All right, so we have first array 1, 2, 3, 4, second array 5, 6, 7, 8. And we'll put a carried return on there. And the key word we use is concatenate. And if you're familiar with Linux, that usually means you're adding it to the end on there. And we're going to do what they call along axis 0. So we have concatenate AB along axis 0. Let's go ahead and run that and see what that looks like. And so we have 1, 2, 3, 4, 5, 6, 7, 8. So now we have an array that is 4 by 2. Has a nice shape of 4 by 2 on here. And if we're going to do it along the axis 0, you should guess what the next one is. We're going to do it along the 1 axis. And let's see how those differ from each other. Let's just go ahead and run that. And again, all we're doing is adding in the axis equals 1. So we have our concatenate, we have AB, and then axis 1. Remember a couple things. One, these are the same shape. So we have a 2 by 2, same dimensions going in there. You're going to get an error if you're concatenating and they're not. If you have something that instead of 1, 2 is 1, 2, 3, 4, 5, 6 with a 5, 6, 7, 8. They'll give you an error on there. In fact, let's take a look and see what happens when we do that. Let me just take this. 1, 2, 3, 3, 4, 5. And let's run that. And if we come down here, oh, we got there. It says, all the input array dimensions except for the concatenation axes M must match exactly. So it'll let you know if you mess up. That's always a good thing. Let's go ahead and take this back here, and let's go ahead and run that. And so we have our 0 axes, which is 1, 2, 3, 4, 5, 6, 7, 8. We bring them together. And you'll see a very different setup here when we do it along the axis 1. We end up with, instead of 4 by 2, we end up with a 2 by 4. 1, 2, 5, 6, 3, 4, 7, 8. And that's just changing which axes we're going to go ahead and concatenate on. What I find is when you're talking about the concatenate or the joining arrays, you really got to play with these for a while to make sure you understand what you mean by the axes. It looks very intuitive when you're looking at it. Axis 0, 1, 2, 3, 4, 5, 6, 7, 8. Axis 1 is then splitting it a different way, 1, 2, 5, 6, 3, 4, 7, 8. When you're actually using real data, you start to really get a feel for what this means and what this does. So if we're going to do that, let's go ahead and look at splitting the array. And do that under Markdown and run it. There we go. So you have a nice little title there. And we'll go ahead and create an array of 9. Let's do NP split. We'll do A, and we're going to split it by 3. Let's just see what that looks like. So if we split it, we get an array 0, 1, 2, 3, 4, 5. We get 3 separate arrays on here. Now remember, we're looking at, let me just print A up here. So we're looking at 0, 1, 2, 3, 4, 5, 6, 7, 8, and then we can split it into 3 separate arrays. And let's take this, we're going to do this right down here. I'm just going to move the A split down here. Instead of the 3, let's do 4, 5, and put that in brackets. And so when we do it this way, we have 0, 1, 2, 3, 4, 5, 6, 7, 8. And that's kind of interesting. I wasn't sure what to expect on that, but we get, when you split an A by 4, 5, you get a totally different setup on here as far as the way it split the array. And to understand how this works, I'm going to change the 5 to a 7. And this will visually make this a little bit more clear. So we had 4 and 5, it went 0, 1, 2, 3, 4, 5, 6, 7, 8. And you see the markers 4 and 5. When we do 4 and 7, I get 0, 1, 2, 3, 4, 5, 6, 7, 8. And so what you're looking at here is the first markers, this is going to go to 4. So there's our first split at the 4, the marker at 4, and then the second split is going to be at position 7. And this is the same thing here. 4, position 5. That's why we're splitting it in those 2 sections. We could also do it 7. Let's just see what that looks like. Run. And you can see I now have 0, 1, 2, 3, 4, 5, 6, 7, 8. So we can split it in all kinds of different ways and create a different set of multiple arrays on here and split it all kinds of different ways. And before we get into the graphs and other miscellaneous stuff, let's go ahead and look at resizing the array. We'll go ahead and take this cell and set the cell as a markdown and run it. Give us a nice title there. And we'll do an array, an NP array of 1, 2, 3, and 4, 5, 6 here. And let's go ahead and just print. Let's go print a dot shape. And we'll go ahead and run that. Whoops, hit a wrong button there. Hit the comma instead of the dot. So we have a shape of 2, 3 here. And this is important to note because when we start resizing it, it's going to mess with different aspects of the shape. And so we'll go ahead and do a print. Scoop in for a blank line. There we go. And let's do b equals np.resize. We're going to resize A, and let's resize it with 3 by 2. And then we'll just go ahead and print B and print B period shape, not a comma. We'll run that. Oops, forgot the quotation marks around the end. We'll go ahead and run that. And let's just see what that looks like. So we have 1, 2, 3, 4, 5, 6, our original array, with a shape of 2, 3. And then we want to go ahead and resize it by 3, 2. And we end up with 1, 2, 3, 4, 5, 6, and we end up with the shape of 3, 2. That shouldn't be too much of a surprise. You know, we got 6 elements in there. We can resize it by 2, 3 was the original one, and then we're actually just reshaping it is how that kind of comes out as when you resize it like that. But what happens if we do something a little different? And let's go ahead and just take this whole thing and copy it down here so we can see what that looks like. And instead of doing 3, 2, remember last time I did the, to reshape it, I messed with the numbers and it gave me an error. Well, when you resize it, you don't have to match the numbers. They don't have to be the same dimensions. So we can, instead of going from a 2, 3 to a 3, 2, we can resize it to a 3, 3. So let's take a look and see how it handles that. And when we come down here to 3, 3, we end up with 1, 2, 3, 4, 5, 6, and it repeats 1, 2, 3. So it actually takes the data and just adds a whole other block in there based on the original data and repeating it. All right, now at this point, we've been looking at tons of numbers and moving stuff around. What we want to go ahead and do is get a little visual here, because that certainly you can picture all the different numbers on there, but let's look at histogram. Let's put this into a histogram. Let me go ahead and run that. And to do that, we're going to use the matplot library. So from matplot library, we're going to import pyplot as PLT. And that's usually the notation you see for pyplot. So if you ever see PLT in a code, it's probably pyplot in the matplot library. And then the guys in the back did a nice job, and gals too, guys and gals back there. Our team over at Simplilearn put together a nice array for me, 20, 87, 4, 40, 53, with a bunch of numbers. That way we had something to play with. And what we want to do is we want to do plot the histogram. Now remember, a histogram says how many times different numbers come in. And then we're going to put them in bins. And we have bins 0 to 20 to 40 to 60 to 80 to 100. You might, in here with the matplot library, they call them bins. You might hear the term buckets, or they put them in buckets. That's a really common term. And then we want to give it a title. So the way it works is you do your plt.hist for histogram, your plt title, and your plt show. And we're doing just a single array in here in the numpy array of A. And let's go ahead and run this piece of code. Take it a moment to come out there. It says figure size, so it's generating the graph. And you can see we have, and let's just take a look at this. Let me go down a size. There we go. Okay, so now we can see what we're taking a look at here. So between 0 and 20, we have 3 values. So we have a 20 here, we have a 4, and a 11, and a 15. 0, 1, 2, 3. It's actually 4 values, but they start at 0. So remember, we always count from 0 up. And from 20 to 40, we got 20. So it's 1, 42, 3, 4, 5, 6. And so you can see in the histogram, it shows that the most common numbers coming up is going to be between the 40 and 60 range, least common between the 80 and 100. This looks like an age demographics is what this looks like to me. And you can see where they would have put it in the buckets of different age groups, which would be a nice way of looking at this. Histograms are so important and so powerful when you're doing demos and explaining your data. So being able to quickly put a histogram up that shows what's common and how it's trending is really important. And using that with a numpy is really easy. And you know what, let's take the same data, and I want to show you why we do bins, or why we have buckets of data. I'm used to calling it buckets. Why we have bins. Let's do it instead of by 20, let's do it by tens and see what happens. And what happens when you do it by tens is you miss out on you can see a nice curve here on the first one, and on the second one it looks like a ladder going up and a plummet, a ladder going up and a plummet, and a ladder going down. So the first would be more indicative of an age group, and the second one would be what you would get if you divided incorrectly. You wouldn't see the natural trend of, I don't know what this would be, maybe how much food they eat. Hopefully not, because I'm in 50, so I'm right in the middle there, which means I eat a ton of food compared to everybody else. But it's some kind of demographic. Maybe it's mental. Maybe it's knowledge, because we hit a certain point and then we start losing, our marbles start leaking out or something. So you start off knowing something, and then as you get older, you grow more. But you can see here where you lose that. You lose that continuity in the thing if you split the histogram into too many bins or too many buckets. And if you actually plotted this by the individual numbers, it would just be a bunch of dots on the graph and wouldn't mean a whole lot. And we've looked at graphs. There turns out are a ton of useful functions in NumPy. I'm sure there's even new ones that aren't going to be in here. But let's just cover some important ones you really need to know about if you're using the NumPy framework. One of them is line space function. This is generating data. So you have a line space, we have 1, 3, 10, and when we do that, we end up with 10 numbers. So if you count them, there's 10 numbers. They're between 1 and 3, and they're evenly spaced. We get 1, 1.222. But these are all, there's a total of 10 here, and it's right between the 1 and 3 range. That can be, there's a lot of uses for that, but they're probably more obscure than a lot of the other common NumPy arrays set up. Then a real common one is to do summation. So we'll do summation where you do, in this case, we create a NumPy array of two different arrays, 1, 2, 3, or two different dimensions, 1, 2, 3, 3, 4, 5. And we're going to sum them up under axes 0, which is your columns. And if you remember correctly, columns is the 1 plus 3, 2 plus 4, 3 plus 5, so we have 3 columns. And if we change this, we'll just flip this to 1. We get 2 numbers. So we get 1, 2, 3 all added together, which equals 6, and 3 plus 4 plus 5, which equals 12. We'll set this back to 0. There we go, since we're looking at axis 0. And these probably could have been, some of these could be underneath our math section. Square root and standard deviation, 2 very important tools we use throughout the machine learning process and data science. And simply we take the NP array, we have again the 1, 2, 3, 4, 5, 6, 3, 4, 5. I don't know why I need to keep recreating it, I probably could have just kept it. But we can take the square root of A. So it goes through and it takes the square root of all the different terms in A. And we can also take the standard deviation, how much they deviate in value on there. And there's a rabble function. We can run that. And NP array is x, we're going to do x equals, hey, we changed it from A to x. X equals rabble. And this sets it up as columns. So we have 1, 2, 3, 4, 5. This is all columns on here. Very similar to the flatten function. So they kind of look almost identical, but we also have the option of doing a rabble by column. And then another one is log, so you can do mathematical log on your array. In this case we have 1, 2, 3, and we'll find the log base 10 for each of those 3 numbers. And there's a couple of them, you can't just do any number here after log, but there is also log base 2. Log base 10 is pretty commonly used on here. We'll go and run that, there we go. Before we go, let's have a little fun. Let's do a little practice session here on some more challenging questions. So you start to think how this stuff fits together. Right now we just looked at all the basics and all the basic tools you have. So let's do some NumPy practice examples. And let's start by figuring out how do you plot, say, a sine wave in NumPy. What would that look like? And so in this project we wouldn't have to do this because I've already run these, but we'd want to go ahead and import our NumPy as NP and import our matplot library pyplot as PLT. So we get our tools going here. And then we'll break it into 2 sections because we need our XY coordinates in here. So first off, let's create our X coordinates. And our X coordinates we're going to set to an A range. And we want this A range, since we're doing sine and cosine, it's going to be between 0 and 0.1. And then we use our NP, and we actually can look up NumPy stores pi. So you have the option of just pulling pi in there directly from NumPy. It has a few other variables that it stores in there that you can pull from there. But we have NumPy pi, and we generate a nice range here. And let's go ahead and run this. And just out of curiosity, let's see what X looks like. I always like to do that. So we have 0.1, 0.2, 0.3, 0.4. So we're going 0 to, in this case, 9.4, 3 times NumPy pi. Remember, pi is like 3 point something, something, something. So that makes sense. It should be about 9. And we're doing intervals of 0.1. So we create a nice range of data. And then we need to create our y variable. And so y is going to simply equal np or numpy.sign of x. And then once we have our x and y, and if we print, let's go ahead and just print y. See how that, we'll do this. Let's do this so it looks print x, print y. So we basically have two arrays of data. So we have like our x-axis and our y-axis going on there. And this is simply a plt.plot because we're going to plot the points, and we'll do x comma y, and then we want to actually see the graph, so we'll do plot.show. And we'll go ahead and run that. And you see we get a nice sine wave. And here's our numbers 0 through 9. And here's our sine value, which oscillates between -1 and 1 like we'd expect it to. Then for the next challenge, let's create a 6x6 two-dimensional array and let 1 and 0 be placed alternatively across the diagonals. Oh, that's a little confusing. So let's think about that. We're going to create a 6x6 two-dimensional, so the shape is 6x6, two-dimensional array, and let 1 and 0 be placed alternatively across the diagonals. Now, if you remember from lesson 1, we can fill a whole numpy array with zeros or ones or whatever. So we're going to do np, create a numpy zeros, and we're going to do a 6x6, and we'll go ahead and make sure it knows it's an integer, even though it's usually the default. And just real quick, let's take a look and see what that looks like. So if I run this, you can see I get 6x6 grid, so 6x6, 0, 0, 0, 0, 0. Now, if I understand this correctly, when they say 1s and 0 placed alternatively across the diagonals, they want the center diagonal, maybe that's going to stay 0 all the way down, and then the next diagonal will be 1s all the way across diagonally, and then the next one zeros, the next one ones, and the next one zeros, and so on. Hopefully you can see my mouse lit up there and highlighting it. So let's take a little piece of code here, and we'll do z1 : 2, comma : 2 equals 1. And wow, that's a mouthful right there. So let's go ahead and run this and see what that's doing. And so what we're doing is we're saying, hey, let's look at, in this case, row 1. There's 1. And then we're going to go every other row 2, so we're going to skip a row. So skip here, skip here, skip here. So we're going down this way, and we're going every other row going this way. It's hard to highlight columns. So you can see right here where we're not touching each row, like this row right here is not being touched. Okay, so we're going to start with row 1, and then we're going to skip a row and another one, and so we're going every 2 rows. And then in every 2 rows, we're looking at every 2, starting with the beginning. That's what this thing blank means. So we're going to start with the beginning, and we're going to look at all of them, but we're going to skip every 2. So starting with row 1, we look at all the rows, but we do it by 2 steps. So we go 1, skip 1, 1, skip 1, 1, skip 1, 1. If you left this out, it'd do every 1. This would just be 1s. In fact, let's see what this looks like. If I go like this and run it, you can see that I just get 1s. So this notation allows us to go down each row, row by row, and we're going to do every other row set up on there. And so if we're going to start with row 1, we also, Control Z, try that. There we go. We'll start with row 0. Again, we're going to go each row, step 2. So we'll start with row 0. And we'll go every other row. And this time we'll start with 1, column 1. And again, we go every other one going down. That's what that step 2 is. That's skipping every other one. We're going to set that equal to 1. So let's see what that looks like. And you can see here we get our answer. We get 0, 1, 0, 0. But it has the 1s going in diagonals on every other diagonal and 0 on every other one. A little bit of a brain teaser, that one, trying to get that one to work out. So you can see how you can arrange your rows, and here's your step and your different axis on there. And then the next one is find the total number and locations of missing values in the array. The first challenge is to create some missing numbers. So let's create our array Z. We're going to do numpy.random.rand 10, 10. And before we do the second part, let me just take this second part out. And let's just see what that looks like. So let's run that. And there we go. So we have a 10 by 10 random array. It randomly is picking out numbers. And next, we want to go ahead and take our random integer size equals 5. And then we're going to do a random 10 size equals 5. So in the Z, we're going to select a number of random spaces here and set them equal to null value. And let's go ahead and run that so you can see what that looks like. And if we look at the array, we've created 1, 2, 3, 4. There should be a fifth one in here. My eyes may be failing me. So we've created a series of, because 0 to 5, 0, 1, 2, 3, 4. So we got 5, there are different null values on here. And this is kind of a neat notation to notice that we can generate random integers, size equals 5. So this generates 5 by 5 miniature grid inside of this to tell it where to put the nans at. So that's kind of a cool little thing you can do. And then we want to look up and see how many null values are in there. And this is simply just NP is nan of Z. Simple. So if it is nan, then we want to sum it up. So we're going to sum up all of the different null values on there. And let's do one more feature in here, which is really cool. Let's go ahead and print the indexes. So NP argware NP is nan of Z. So we're going to create our own another NP array. And let's run this, and we'll see here that it comes up with the 4 indexes. So we did count 4 of them up there. It tells you where they are, 1, 9, 2, 0, 4, 6, 5, 4. And then let's go ahead and run this again. Run, there we go. This time I got 5. That's what we get for random numbers. Another fun one that I always like to do is very similar because we have np is nanz.sum. So we're summing the number of nans. And we can get the indexes and you can reshape the indexes. But you can also just do, we'll do an INDS where np is nan of Z. And let's just print that. Print INDS. Let's see what that looks like. And it's very similar to what we have. We have 0, 1, 3, 0, 6, 3, 8, 6, 9, 3. But I've split it into 2 different arrays. So we have our X and our Y kind of coordinates going there. And what I can now do is I can now do Z INDS equals. And at this point, you can also, instead of getting the sum, you can get the means or all the numbers and that kind of thing, or the average as it is. So that'd be one thing you could do, and you can pick out the average. That's very common in data science to get the average and just use that for a value. But we'll go ahead and just set it to 0, and then let's go ahead and print our Z and run that. And you can see when we come down here, we have wherever there was a null value, it is now 0. And you can set this to whatever you want. This is another way to replace data or help clean data up, depending on what it is you're doing. So, wow, we covered a lot of stuff. So quick rehash going over everything. We went into there, we looked at array manipulation, changing the shape, how to switch that around. We even had the flatten down there, which remember we have another command lower that's similar. We could change the order by F. Remember F stands for Fortran, very strange connotation, but there's C and F. C is the standard, and F switches it to a different order. To be honest, I usually have to look it up because I almost never use F, but when you need it, you're like, oh my gosh, what was the other order? Just do a quick Google. So we talked about reshape, making sure that the dimensions are the same. You don't want to have like something that has 12 objects in it and reshape it to 11 and 5 because it doesn't work. It doesn't divide into 12. We can transpose, so we can switch them. So we can go from a 4 by 3 to a 3 by 4. Oops, I did that the other way around. 3 by 4 to 4 by 3. We covered reshaping the array. We did the roll the axes. You can do some weird things with swapping and rolling axes and transposing the numbers. We dug a little bit into the arithmetic. So we talked about adding, we talked about subtracting, multiplying, dividing. And at this point it's so important we just look up the NumPy mathematics. And you can see here they have just about everything. Your trigonometry, your hyperbolic functions, rounding, sums, products, differences. There are all your different miscellaneous mathematical connotations. So Google it, go to the main NumPy page and look at the different setups you can do on there. So we covered that, and we did slicing, how to break it apart. We did iterating over the array. We covered joining arrays and how to concatenate. Remember, concatenate just means add on to it. So in this case, how are you adding B onto A is how you'd read that. From Linux, you should catch the concatenate because that's used regularly there. Splitting the array, we talked about how to split the array in different ways. So you can split it in array of arrays, all kinds of different ways to split the array up. How to resize it. And remember, resize does not have to have the same shape, but if you resize it, it will take the data and begin at the beginning and add new rows on if the size is bigger. If it's smaller, it truncates it. It just cuts the end off. We looked at how to do a histogram and how to plot that. We mentioned buckets or bins, as they call them in PyPlot. And then we covered a lot of other useful functions in NumPy. We talked about the line space setup for doing numbers in a series. How to sum the axes up. Again, that's part of the mathematical formulas there that we looked at. There's a sum, there's also means and median. All of those you can compute in NumPy. And you can also do the square root and standard deviation. The ravel function, very similar to the flatten. To be honest, I almost always just use the flatten, but the ravel has its own kind of functionality that it does. And then we went into some NumPy practice examples. We challenged you to create a sine wave in NumPy and how to do that. We're kind of looking for that A range. Remember how we do the A range, and you can have your beginning value, your end value, which they did as 3 times pi, NumPy pi, and we're going to do intervals of 0.1, and then y just equals the NumPy sine of x. There's our math from the math page we were just looking at. Remember that? It's right at the top. And finally, we went down here. We had this kind of a little brain teaser, how to do diagonal zeros and ones, playing with the different connotations of the NumPy array. And then we did a random size, and we played a little bit with with the null values, playing with null values. If you're doing any data science, null values are like a headache. What do you do with them? Big sets of data, you get rid of them. Small sets of data, you have to factor something in there, like figure out the average or the median there, and then replace it with that. So let's start with what is Matplotlib. Matplotlib is an open source drawing library which supports rich drawing types. It is used to draw 2D and 3D graphics. And there are so many packages in the Matplotlib, we're going to cover the basics. And there are so many packages that sit on top of the Matplotlib that we can't even cover them all today. But we'll hit the main ones so that you have a good understanding of what the Matplotlib is and what the basics can do. You can understand your data easily by visualizing it with the help of Matplotlib. You can generate plots, histograms, bar charts, and many other charts with just a few lines of code. And here we have some basic types of plots that you can see here that we'll go into. We have the bar chart, the histogram. Boy, I use a lot of histograms in my stuff. A scatter plot, line chart, pie chart, and area graph. Let's start plotting them. And to do this, I'm going to be using Jupyter Notebook. You can use any of your Python interfaces for programming or scripting and running it. Of course, we here really like the Jupyter Notebook for doing a lot of basic stuff because it's so visual. And in our Jupyter Notebook, which opens up in this case, I'm using Google Chrome, you can go up here to New, and we'll create a new Python 3 and set that up. If you're not familiar with Jupyter Notebook, we do have a tutorial that covers some of the basics of that. And you'll look at any of our tutorials. I usually cover a number of them showing how to set up Jupyter and Anaconda. I myself use Jupyter through Anaconda. In fact, let's go ahead and open that up and just take a look at this, see what that looks like. You can see your Anaconda Navigator. If you install it, it will automatically install the Jupyter Notebook. And that also installs a lot of other things. I know some people like the Qt console for doing Python or Spider. I've never used them. I actually use Notepad++ as one of my editors. And then I use the Jupyter Notebook a lot because it's so easy to have a visual while I'm programming. And even simple script in Python, I'll take it from the Jupyter Notebook and then do a save as. You can always go under File, and you can download as a Python program. So that will download it as an actual Python versus the IPython that this saves it as. So let's go ahead and dive in and see what we got going here. And let's go ahead and put Matplotlib tutorial. And I'm going to turn this cell into a markdown so it doesn't actually run it. You can see it has a nice little title there. That's all Jupyter Notebook. And then from matplotlib, let's import pylab. Back one. And then let's go ahead and just print. We'll go pylab and the version. Let's go ahead and run this. So we're going to import our pylab module from the matplotlib. And we find out that we're in version 1.15.1. Always important to note the version you're in. Probably, I was reading an article that said the number one thing that Python programmers struggle with is remembering what version they're working in and making sure that they're going from one platform to the other with the same version. And if we're going to graph things, I think we need some data to graph. So we're going to import NumPy as NP. Now, if you're not familiar with NumPy, definitely go back and check out our NumPy tutorial. There's so many different things you can do with it, dealing with reshaping the data and creating the data. We're just going to use it to create some data for us. And there is a lot of ways to create data, but we're going to use the np.linespace. So we're going to create a NumPy array, and the way you read this is we're going to create numbers between 0 and 10, and we're going to create 25 of these numbers. So we're just going to divide that equally up between 0 and 10. And if we have x coordinates, we should probably have some y coordinates. And we'll do something simple like x times x plus 2. And let's just take a look. We're going to print x and print y. Let me go ahead and run this. And let's see what we got going on here. So we have our x coordinates, which is 0, 0.4, 0.83, etc. And you can look at this as an xy plot. So where we have 0, we have 2. Where we have 0.416, we have 2.17. And just as a quick reminder, we're going to do print np array x comma y dot reshape 25 comma 2. And the reason I want to do this is I want to show you something here. A lot of times a program returns x comma y, and it's an array of x comma y, x comma y, x comma y. And so when you're working with the pyplot, you have to separate it out and reshape it. So if I start off with pairs like this, I can reshape them. If I know there's 25 pairs in there, I can switch the 2 and the 25. And this is kind of goofy, but we'll do it anyways. Reshape. So I'm going to reshape my 25 by 2 back to 2 by 25. And if I run that, you'll see I end up with the same output as the XY, the two different arrays in here. And this is important that we want X and Y separate. Again, that's all NumPy stuff, but it's important to understand that this is a format that matplotlib works with. It works with an array of X's, and they should match your array of Y's. So each one has 25 different entities in it. And then for our basic plotting of this data, it only takes one command to draw a graph of this data. And so we use our, from up here where we imported pylab, we take our pylab, and the key under there is plot for plotting a line. And then we want our x coordinates and our y coordinates. And we'll throw in R. And the R simply means red. So we're going to draw the line in red. Let me go ahead and run that. You can actually switch this around if you wanted to do different. There's B for blue. We have a lot of fun. Yellow. Hard to see yellow. There we go. But we'll go ahead and stick with red. Run. And when you're doing presentations with these, try to be consistent. You know, if the business and the shareholders send you a spreadsheet and they have losses in red, use red for losses in your graph. Try to be consistent. Use green for profit, for money. You don't have to necessarily use green, but it's whatever they're using, whatever the company's using. Try to mirror that. That way, people aren't going to be confused if you switch your data around and every time one graph has red for loss and one graph has blue for loss, it gets really confusing. So make sure you're consistent in your graphs and your coloring. And something to know, because we're going to cover this in a minute, this is your canvas size. So we have a canvas here, and what we're going to do next is we're going to look at subgraphs. Okay? So let's take our pylab and create a subplot. And one of the things also to know when we're working with the matplotlib, I'm not setting, when I do this, this is my drawing canvas, the pylab. So once I've imported the pylab, I'm drawing my images on there. Very important to know. And with the subplot, we're going to give it some different values. And we're going to represent by rows, columns, and indexes. And let's do 1, 2, 1. So it's going to be the first row, second column, and the index is like you can stack your graphs and things like that. We don't worry too much about indexes, but rows and columns. We want to go ahead and use row 1 and column 2. And if we're going to have one object, we should probably have two. But before we do that, we have to plot data onto the subplot. So the order is very important. And we'll go ahead and stick with our x comma y. And let's do this. We're going to add in a third parameter here. Remember we did red? We're going to add shorthand dash dash for dashed lines. So this plots the data into row 1, column 2. And if we're going to do that, let's do another one, pylab.subplot. And if we're going to do row 1, let's do column 2 and index 2. And this time we're going to add G for green, and this denotes a style. And if we're going to set up our pylab subplot, there we go, pylab, we got to go ahead and plot that, pylab plot. And instead of xy, we want y comma x. Whoops, I messed up. This is in the wrong spot. There we go. We'll move that down here real quick because that goes in the plot part. So the subplot tells it the row, column, and index, and the pyplot tells it what data. In this case, we switch them, and the color, and then the style shorthand. Now let's go ahead and run that. And you'll see it takes this canvas, splits it in two, and now we have two different graphs. And we have the red one with dashed lines, and we have the green one, which has the little stars going up. And if we take this, and let's just for fun, let's change this and run that with an index of 1. It puts them both on the same index. It also gives me a warning because it's a strange way of doing two subplots. It's depreciated. There's another way to do it. But most people just ignore that warning because it's not going to go away anytime soon. Now that's using the same setup. What happens if we do, instead of this, let's change the column on here and find out what happens. And if we do the column, it didn't really like that on the setup, it just disappears. So let's keep our column as 2, and let's change the row on the second one to 2, and run that. And you'll see again it kind of squishes everything together. It can cause some issues. So let's take the index. So they each need a unique index. And you can see here where I've made some changes. I said row 2, and look what happens when I change to column 2. So I now have row 2, column 2, index 2. It squished it up here, so you could put another graph underneath is what that does. And there's all kinds of different things. You really have to just play with these numbers till you get a handle on them, because you have to repeat it 164 times according to Cambridge University if it's completely new to you. And you can see right here where, there we go, 3, run. There we go. But you can see it takes a little bit sometimes to play with these and get the numbers right. Oops, I hit the wrong one, that's why. Let's go 3 there, run. There we go. Now it's overlapping, so I have this doubled over here on the right. For now, we'll just go ahead and leave this with the where we have column and row 2 and the two different indexes so they appear nice and neatly side by side. And then, as we just saw, as we were flashing through them, we can put them on top of each other. And let me just highlight that and copy it down here. Paste it down there. And here we have 1, 2, 1. And then we'll do 1, 2, 1 also for this one, and that puts the two subplots directly on top of each other. It gives us that warning, and you can see we now have two different sets of data graphed on top of each other. And you can also see how it did the indexes. Since one of them is from 0 to 10, that's the green one on the x-axis, and the other one is from 0 to 10 on the y-axis. So it took the greatest value of either one and then used those as a shared value. So let's next look at operator description. And we'll go ahead and turn this cell into a markdown and run that so it looks nice. So Fig, and you remember I talked about the canvas earlier. I briefly mentioned it. We're going to look a little bit more at the canvas later on. But that's what the figure is. Fig, we're going to add axes. So we're going to initialize a subplot, add the subplot, in rows, in columns, and all kinds of different things with this that you can do. Let's look at that code and see exactly what's going on. And I want you to notice that there's Fig, which is the actual canvas in the matplot library. And AX is commonly used to refer to the subplots. So when we're creating subplots, you'll see AX equals PLT subplot. Earlier, we did the pylab. So let's go ahead and import pyplot from matplot library. And we're going to do it as PLT. You'll see that a lot. That's really the standard in the industry, is to call it PLT, just like pandas is PD and NumPyArray is NP. Certainly you can import it as whatever you want, but I would stick to the standards. And we're going to do the same graph as we did above with the pylab, but with the PLT. So if it looks familiar, there's a reason we're doing this, because we want to show you how the figure part works and working with the canvas goes. But we're going to do the same plot as we did before, and we'll call it fig, and we're going to set that equal to plot figure. So there's our figure or our canvas on there. And let's create a variable called axes, and we're going to set that equal to fig.addAxes. And in this, we're going to control the left, right, the width, the height of the canvas from 0 to 1. And so we can go ahead and I'm just going to put some stuff in there. I got 0.5, 0.1, 0.8, 0.8. So when you're looking at this is a 0 to 1, or you could say 50%, 10%, 80%. But it's a control. It's going to control your left and your right, along with the width and the height. So the width and the height, we're going to use 80%, and we're going to have like a little indent on the left and the right. And this should look familiar from above. Axes.plot. X comma Y, and then let's give it a color. How about red? Since we're recreating the same graph, let's keep it uniform. Oops, and it helps if I use AXIS instead of AXES. I don't know where that came from. But this looks identical to the one we had up above. So here's our axes plot, X comma Y of red. Same graph, same setup, but this time we've added a variable equal to the figure.addAxes. So our plot figure is our canvas, our axes is what we're working in, and then our axes.plot X comma Y. And again, we can draw subgraphs. We put that down here. Just like we did before. And a little different notation here. We're going to have fig comma axes equal plt.subplots, and in here it's going to be the number of rows. We're going to do 1 row, and columns equals 2. So if you remember before, that's what we did. We had 1 row with 2 different graphs on it. We're going to do the same thing, but note how we did this. Here's our figure, or our canvas, and our axes. We're going to create actually 2 different axes. We're going to create row 1, column 2. And so axes is an array of information. So we can simply do let's do ax in axes. And this will now look familiar. Ax.plot. We're going to do X comma Y. We'll go ahead and make it red. Keep everything looking the same. Remember, nice uniform graphs. Everything looks the same. And if we go ahead and run this, you'll see we get 2 nice side-by-side graphs. So just as we had before, the same look, the same setup. And just for fun, let's change in columns to 3. We'll run that, and now you'll see we'll have 3 on there. And let's see if we make it a little bit more interesting. We'll do in rows equals to 2. And you can see down here we're going to get an attribute error because it's trying to scrunch everything together. So it does have a limit how much stuff it can put in one small space. That's important to know. You can fix that by changing the canvas size, which we'll look at in just a minute. And there's other ways to change it on here. But here we go. We can do in rows 2 and columns equals 1. You can see 2 nice images right above each other. We'll go back to the original. 1 row, 2 columns, side by side, left to right. And we can also draw a picture or graph inside another graph. And that's kind of a fun thing to do. It's important to note that we can layer our stuff on top of each other, which makes for a really nice presentation. So let's start by fig. We'll create another figure. So we're going to start over again with our canvas. We set that equal to plt.figure. So there's our new canvas. And let's do axes. We'll call it axes 1 and 2. Axes 1 equals fig.addAxes. Remember this from earlier? And this here, similar numbers we used before, saying how big this axis is, this figure in the axes is. So this is going to be the big axes. And let's do axes 2 equals another figure add axes, and then 0.2, 0.5, 0.4, 0.3. And if we're going to do this, they need data on them. So let's go ahead and plot some data on our axes. So axes1.plot. And we'll make this simply x comma y comma, make it red. And then let's go axes2.plot. And let's reverse them. Y comma x comma green. There we go. Doing what I told you not to do. You shouldn't be swapping axes around and plotting your data in 5 different directions because it's confusing. But let's go ahead and run this and see what this looks like. And then let's talk a little bit about this. We talked about the 0.2, 0.5, 0.4, 0.3. And let me just grab the annotation for that. That's left, right, width, and height. So we have in here that this is going to be left, right. So here's our left is 0.1 in. 0.5, and you know what, let's just play with this a little bit. What happens when I change this to 0.1? Moves it way over to the left. So there's our 0.1. So we can make this 0.4. Run that. There we go. So you can see how you can move it around the branches on here. 0.2, 0.5 is the left, so that's our right. So let's see what happens when we do let's make this 0.1. And that actually is, they had it down as left, right. I thought this was wrong. It's actually how far from the bottom. Let me switch that on here. Bottom. There we go. So we had here on this. We can go ahead and put that back to 0.5 and run that. And this is 0.3. Let's make this 0.3 also. And that is the width. And then, of course, there's the height. We can make that really tiny. Actually, let's do 0.2. And let's run that. And you can see it changes the height on there. We can make it even smaller, 0.2 by 0.2, and as you can see, you can get stuck playing with this to make it look just right. It can sometimes take a little bit. Certainly, once you have the settings, if you're doing a presentation, you try to keep it uniform, unless it doesn't make sense for the graph you're working on. Try to keep the same colors, the same position, and the same look and feel. And I mentioned earlier we can adjust the canvas size. So this is from earlier, I just copied it down below. We're going to replot the same data we've been looking at. And what we can do is we can change the figure size to 16 by 9. And let me run that and show you what that looks like. So it fills the whole screen. And then if you are, normally when you're working on the screen, you don't worry too much about this. But we can set the DPI to 300. Run that. There it goes. This is your dots per inch. And if you are doing an output of this and you're printing a hard copy, you want the higher quality. I would suggest nothing under 300 if it's a professional print. You might get a little less than that, but whenever I'm doing professional graphics and printing them out on something, 300 dots per inch is kind of the minimal on there. You can go a lot higher too, but keep in mind the higher you get, the more memory it takes and the more lag time and the more resources you use. So usually 300 is a good solid number to use in your dots per inch. And you can see it draws a nice large canvas here, which is 16 by 9, and then the DPI is 300 on here, so it's a little higher quality. And just out of curiosity, I wonder how long it takes to draw something double that size, 600. And you can see here where at 600 DPI, it's going to take a while. There it goes, just because it's utilizing a lot more graphics on there. And let me just go back to the 300. Now we'll actually let's do a 100. You're not going to see a difference on this because it is web-based graphics are pretty low. And up here you saw I did this with the plot figure. This works the same if I do figure axes subplot, figure size, and then we'll go ahead and do axes plot x comma y comma, we'll stick to red. Let's go ahead and run this. And you should get almost the same thing here. Here's our axes on the subplot on here with the fixed size and the DPI. Let me take this all out. Let me just remove all that real quick. Run it again. There we go. Now we're back to our original figure. And let's look at some of the other things you can do with this. One of the things we can do is we can set a title for the axes. So axes set title. You'll see right here, since I put this on the axes, it's the main title for the whole graph. And if you're going to have a title, you should also label. So we can label our X label, and we can set our Y label. In this case, we're just going to call it X and Y. Keep it nice and uniform, and if we run this, you'll see that we've added a nice X label and Y label. Whoops, where'd they go? And it turns out in this environment that you have to put it before the title. So let me go ahead and put it before the title. And there's our X, Y, and let me run that. And of course, we can also do up our size a little bit so you can see what's going on a little better. So here we have X label X. If you come down here, you'll see our X label and our Y label. We can, of course, change this to X label. We can change this to Y. It can be whatever you want on here, of course. And our title graph. There we go. Run. So here we have our title graph, our Y label, and our X label all set up on our nice little plot. And then before we move on to the next section, let's do one more thing on here. We have a thing called the legend. And we're going to set our AX legend, label 1, label 2 up here. That's the format for it, but let's go down here and actually use it. I'm going to do two different plots. We're going to have axes plot x by x times x squared and x cubed. And if I run this, you'll see it puts two nice graphs on the setup on there. But it's nice to have a legend telling you what's going on. So for the legend, we can actually do axes, since we have the two plots, legend. And on here, we've created an array, and we have y equals x squared, y equals x cubed. You can actually put this as whatever you want. Those are just strings. And then location 2. And let's go ahead and run this and see what that looks like. And you can see it puts a nice legend on the upper left-hand corner. Location 2. We can do location 3. And run it, and it drops it down to the bottom. location 1. I can't remember where that's at. There we go, upper right. So each one of these is a number that refers to the different locations on the screen. 0. Kind of have to play with them or look them up to remember where they're at, but they do work. It just kind of moves around depending on where you want your legend at on there. So on this section we cover the title of the graph, the Y labels, and legends. We're getting into starting to look really fancy here. So we now have something we can actually put out. You'll see the title of the graph looks a little fuzzy. So I might, in a web setup, put the DPI up a couple notches. Maybe put it at 200. 100 might work fine. Just so, that's something to notice on here when you're playing with these different things. We had our subplots, DPI equals, let's do 200 and just see what that looks like. So you can see it now is a lot clearer. It's also larger, so it's a nice little feature you can throw in there with your DPI dots per inch. So the next section is, let's look at some graph features. We're going to look at line color, transparency, size, and a few more things on here. And, oops, I forgot the main title. So we have our figure and our axes equals our plot and subplots. And I'm going to go ahead and do a DPI equals 150 so the graph comes out nice and large and easy for you to see. And let's go ahead and do 3 plots on here. We'll do x by x plus 1, so it's just going to be a straight line. Plot x plus 2, and axes dot plot x plus 3. This looks like we're doing nearest neighbor setup or showing how it located data and putting your lines on there between the nearest neighbors. There we go. So it draws a nice little graph with 3 lines on it. One of the things we can do is we can control the alpha on this. Oops, and you can actually see when they did these lines, it automatically pulls in different colors for your setup. So there's some automatic things going on in there. And a lot of times we do that comma R, where we're going to do color equals red, another notation on here. Let's go ahead and run this. Now we have a bright red line down there. And with the Matplot library, you're not limited to red. You can also use one of many different color references, as you see here, with the #, 1155DD, which is just blue. And we can do the same thing with another color on here, which turns out to be green. And I can just as easily do this. Green, blue, oops, there we go, blue, and run that. And you'll see here we have red, blue, and green. And what I want to do is I want to make this, we're going to set what's called the alpha on this. And we're going to set this equal to 0.5. So this is halfway see-through when I run this. And it's almost going to look pink because you can see through it. And let's change this just a little bit, just to make this kind of fun. Let's square it. There we go, run it. So now we have this nice square that comes up. And you can see when it crosses it, because I plotted these 2 lines after it and they have no alpha, the red is behind those lines, or in this case pink because we did the alpha halfway through. So let's go ahead and do this. Alpha equals 0.5. And, you know what? Instead of squaring it, let's take it to the 0.5 power. That'll be kind of interesting to see what that does. We'll just go to keep it squared. There we go. And run that. And let's go back and look at this where it crosses over. And the first thing you'll see right here is on the blue, it's kind of light blue now. You can see how the 2 colors add together. You get almost a purple on there. So I can clearly see where the red crosses the blue line. And then the green just blanks it over because I didn't do any opaqueness, no alpha on there. So this is great if you have lots of data that crosses over and you need to be able to track those lines better. And we'll go ahead and do this 0.5 and we'll run that. Oops, I did equals 0.5. Let me go ahead and run that. And so you can see right here, now you can easily see the red line, how it crosses the green and the blue down here. And if we want to, we can do this as the default is 1, is solid. So we can change this all to 0.8. Let me just do that. Oops, 58, 8. There we go. Run. Oops, I must have hit a wrong button there. Let me try that again. I accidentally got rid of a bracket. And let's go ahead and run that. And we come down here and look at this. You can still see where it passes behind them, but the green dominates and the blue dominates because we're now at 80% instead of 50%. And you can do less. That's kind of fun, although at some point the lanes kind of fade. So 0.5 is usually the best setting on there. We have a nice pastel here at 0.3, and you can easily see where they cross over. And just like you can play with the colors, we can play with line width. And let's try DPI 100 and see what that looks like on my screen. Equals 100. And we'll go ahead and just take our AX plot. Let's do 4 of these lines just so you can see how they look next to each other. Real quick here. There we go. And if I run this, they should all appear the same. It automatically does different colors on there. So let's do color equals blue. Forgot my quotation marks. There we go. And we'll go ahead and just make these all blue, just for purposes of being nice and uniform. And then what I want to do is I want to do the line width. Line width equals 0.25. And let's just copy and paste that down here. Let's do equals 1. About 1.5. And let's do just make this equal to 2. Let's see what that looks like. And when we do that, you can see it goes from a very thin line, a 0.5, a 1, or 1.5, and 2, which is twice the width of the 1. And if we're going to do different sizes, we had different colors, we had our alpha scheme. Let's take this whole thing here. Let's paste it down here and do another one. But instead of line width, let's look at styles. And something to note here, you can actually abbreviate this with LW. So line width can also be let's just do everything 0.2. And let's set up a line style. We'll do the first one dashes, and let me just paste that down here so I'm not doing a lot of extra typing. There we go. Take this out. So we have our dashed. We can do a dash dot. Oops, let's do the dash dot here. And a colon here. There we go. And there's a lot of different options. We'll look at a few more as we go down for different ways of highlighting data. But when you look at this, we have everything as a line width of 2, and now we have a straight line, we have a dash line, or a dot dash, and a dot 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 line. And then another thing we can add on here is we're going to do, here's our x plot, and we did x, let's do x plus 4, so it goes right on the top. I'm going to do color black, line width 1.5, so it's a smaller line. And we're going to take the line and we're going to set dashes. So look how I've changed some of the notation here for my line and my ax plot. So I can set my line comma equal to ax plot, and then I can change the line settings this way. And when I run this, run that on here, you'll see the 5, 10, 15, 10 creates a series of dashes that are varied in length. In this case, they alternate between a short dash and a long dash. And we can play with these numbers. Curiosity always has me what happens when you play with the numbers, just to see what they look like. Let's do this. Let's paste this down here. I'll do 2 of these just because they're kind of fun to play with. And let's change this from 10 to 3. And we're going to change this one from 15 to 4. And let's run that. And you can see the differences in the lines. Oops, a little bit confusing on there, because I forgot to change the lines are all on top of each other. So let me change that really quick here. And let's run that. And now you can see here's our original dash line alternating. When I change these numbers on the second one, the very end value to 3, you can see now we have dashes of 5. Let's see, I'm going to guess this is a dashes of 5, skip 10, dashes of 15, skip 3, and then it goes back to the beginning. Dashes, 5 dashes, skip 10, 15 dashes, skip 3. And of course the last one we just switched up a little bit. It looks a lot more uniform because I'm using 2 sets of 10. Or if I did something like this and changed it to 30, it really becomes pronounced as far as the distances between them. And instead of 4, let's put 30 here also. 30 by 30, there we go. Really pronounced on that one. And let's look at one more important group for plotting our data. And in this, here's our plot we started with the x plus 1, x plus 2, x plus 3, and did it in blue on this one, 3 or 4 different blue lines. And this property, we want to add the actual plots, so you can see where the plots are on the graph. And for that, we might have marker equals O. And if we run this, you'll see it puts a dot for each of these, and there's 25 dots because we have 25 x values. So we actually have 0, and each of the different values of x, y are then plotted here with the dots. And we don't want to just limit ourselves to dots. We can also do plus sign, that's another option. Dots is most common. I actually like the dots the best. If we do the plus sign, you can see it puts a nice crosshairs or plus sign on there. And we can do a marker. There's a number of different markers you can use. And I think this one was it. S is another one, which is a nice square. And that's actually a good one, S for square. O for period. Okay, that's just kind of weird. So you can see that probably on these markers, another one is number 1. So if we run that, you'll see we now have these little hatch marks. And let's just go with the O on this one. By the way, this works with square really nicely. Some of the stuff we're going to do here on just a second. Let's do marker size equals 2. And change that to 5 and run that. And you can see here it puts a nice little tiny dot versus this size dot here. And this is interesting because it said 2. I thought it would be bigger. But if you do 0.5, it gets even smaller. And let's just do 10 to see what that looks like. Run. That looks huge. So marker size, a lot of these are dependent on the DPI and the setups. There's things that switch around as far as the way the size shows up. You got to be a little careful when you change one setting, it can change all the other markers. And then let's take our square on here, and we had marker size, so we also have marker face. We'll set that equal to red. Of course, we gotta change so it's up 1 notch. We'll run that. Whoops, must have mistyped something on here. And I did, it's marker face color equals red. And so when I run that, you can now see I have the squares on there with the marker face color. Of course, we can mix and match these. Come down here and we'll make this, instead of, let's make this +7. And we'll make this size 15. Marker face color equals, and we'll do what, green, just because. There we go, run. Very hard to actually see what's going on there. Still 25 dots, they kind of overlap. As you can see, they print them over each other. And of course, if we really wanted to make it look horrible, we could just make that really huge. Generally though, you want something a little bit smaller and cuter. We'll just try doing it this way. There we go. That's too small to even see the face. So 4, you can start to see the face on there around 4, and maybe on 8. 8 might be a good number for this. There we go, 8. Again, that all just depends on what you're trying to show and display. So we've covered a lot of stuff here as far as our lines. We've covered opaque with our alpha setting on there. Give us some nice pastels. You can see how they overlap and how they cross over. We covered the line width, different size on there, different formats for the line itself, and these are all, you can combine all these. So you can have our line width equals 2, line style equals dash. You can bring this down here also to the markers. And then we added markers in, just standard circle, a plus sign, the square, a little tick, which uses a 1. Then we add a marker size and a marker color face, and we combine those. You see we get a nice different series of representations. We also briefly mentioned color, where you didn't have to use, like in here we used color black. Someplace up here, I'd have to find it, we use the actual number for the color, as opposed to, I changed them to red and blue. So you can get very precise on the color if you have a very specific color set that you need to match your website or whatever you're working on. All of those are tools in the Matplot library. So we have one more piece to formatting the graph, so we want to show you, and then we have 2 big sections. We're going to go over the different graphs that they have along with a challenge problem. So let's go to the last section we're going to look at is limits. We're going to limit our data. So this first part I'm just going to paste in there. We're going to create our subplots 1, 2. So 1 row, 2 columns. We're going to do a figure size of 10, 5. This should all look familiar now since we've done a number of them. And we're going to go ahead and plot, and this is an interesting notation you should notice here. Our axes 0, so 1 we've used, instead of, you can just iterate through them, but they're just an array, so it's an array of 0 is still the axes of the first axes out of 2. And we're going to plot x squared, x cubed, line width 2. So we're going to go ahead and just plot 2 graphs right on top of each other without doing multiple plots on here. And we'll set the grid equal to true on here. Let's go ahead and run that. And you can see here are 2 plots with the x value going across. And I'm going to do something similar. And by the way, you can just, if you look at it, you can see the grid on there. That's all that is. Easier to spot the data going across. We're going to take the same data for axis 1. So we have our plot of x squared, x and x cubed, line width 2. And this time we're going to take our axis 1 and do y limit. It's actually set underscore y limit. This is the y-axis, so it's going to be an array of two values. And we'll do 0, 60. I'm just making these numbers up. The guys in the back actually made them up. I'm just using their numbers. And we're going to set the x limit, and we'll set the x limit as, don't forget our brackets there, 2, 5. So it's the same data going in, but we're setting a limit on it. And let's go ahead and run that. And let's see what it comes out of. And here we have the y limit 0 to 60. So we're looking at just the lower part of this curve here up to here. And we have the x limit 2 to 5. So that starts right here at 2, and you can see very different graphs. This is kind of nice because you could actually put one of these on top of the other if you wanted to draw focus to one part of a graph. Remember how we did that earlier, one inside the other? But just a quick note, you can easily limit your graph and kind of reshape the way it looks quite easily. And we can also add that grid down there if you want a grid. We'll run that and add the grid in there. Whoops, I guess you have to do the grid beforehand. Switch that. There we go. Sometimes the order on this is really important, so you may double check your order when you're printing these things out. It also helps if I change it to 1. So in this case, it might not be the order. I wonder if we'll go back here as 1. There we go. So it doesn't matter the order on grid. But you can set the grid for easy viewing here. Nice setup on there. But you can see how we can limit the data. So let's start looking at some other 2D graphs and make this cell a markdown. So when we run it, it has a nice pretty title to it. And let's go ahead and create some data with an NP array. We'll do 0 to 5 on here. There we go. And let's look at 4 common graphs. We'll put them side by side. So we'll do a figure. Our axes equals plot, subplots, 1, 4 columns, and then figure size. Hopefully it'll fit nicely on here. It seems to do pretty good on here. And I'll go ahead and just run that since we're in there. Run. You'll see I have 4 blank plots on here. And we'll start with axes of 0. Let's set title. And we want this to be a scatter plot. A scatter plot just means it has a bunch of dots on it. So here's our axes of 0 dot scatter. Easy to remember. Scatter a bunch of plots on there. We'll do our n, or we can do x or n. There we go. And let's go ahead and do axes set title scatter. Oh, already did that. We're just going to do scatter. That's how you do it on there. That is how you create a scatter plot, simply with the scatter control. And we'll do, let's do the variable x plus, and let's throw some randomness in here. Usually scatter plots have a lot of random numbers connected to them. That's why they do them on there. And so the bigger the x gets, the bigger the randomness, so 0.25 times the randomness. And what we should end up down here is with the scatter plot. And you can see as you go up, it just kind of has some random numbers and moves up and down the line. But plots just the points. So if you remember from back up here where we did marker, this is plotting basically just the marker. So it's a scatter plot. Probably less used is a step plot. So for x is 1, we'll go ahead and do a step plot so you can see what that looks like. And this time I'll use our n value instead of x. We generated that n value up here. And so for this we have n times 2, or n squared, n times 2, n squared. Line width equals 2, and if we run that, it creates a nice step up. Let's see, so we've got a scatter plot, we've got a step plot. Let's do a bar plot. And we'll use the same formula, n squared, alignment centered, because you can have them to the left or right, width 0.5, and alpha, if you remember correctly, that's how opaque it is. Let's see what that looks like on there. So we have some nice, you can see here a nice bar plot. It should look very similar to the step plot, but colored in. And we can change the width. Let's see what happens if we do 0.9, run. And if we take width out completely, run that, you can see it starts coming together on there. And we can change the alpha. We can take the alpha out too and run that. So now you have the solid colors. And if we take out the center and run that, everything, you really can't see the shift on here because that's actually the default on this. But these are common settings for the bar graph. Let me just put them back in there. There we go. Alignment, center, and alpha. Now, I can't say I've used the step graph very much. There's certain, I guess, domains of expertise that require a step graph. But the scatter plot and the bar graph, very common, especially the bar graph. And we'll look at histograms here in just a minute. So I use histograms a lot, especially in data science. But this is nice if you have very concrete objects. How many people are wearing yellow hats? That kind of thing. But if we're going to do that, let's go ahead and do the last one, which I see a lot more in the sciences. I'm certainly using the data science, but more like for mapping. I saw a publication on solar flares, and they were discussing the energy. And so filling in the graph gives it a very different look. So we're going to do the fill between. And it's just like you think it'd be. It's fill between, but with a underscore between them. And we'll do x and x squared and x cubed. And we'll do color green and alpha again, in case you had other data you wanted to plot on there. You can see it forms a nice squared coming up here. And also, if you look at the bottom one is your squared value, the upper line is your cubed value, and then it fills in everything in between. If you remember from calculus, this would be if you had like a motor and efficiency, they would talk about the efficiency going up and the loss, and you're looking for the space or the area between the two lines. So it gives you a nice visual of that. And let's look at a few more basic two-dimensionals. So we're going to have our figure size on here. We're going to do a radar chart. To be honest, I've never used a radar chart in business or in data science. I have to find a reason to use one now. So the first line for doing a radar chart, we have to add axes into the figure. And with this actually creates our, let's run it so you can see what it creates. It creates a nice, looks like you're on a submarine and you're tracking the hunt for red October or something like that. And it needs all of these. The polar is the fact that we're doing polar coordinates. 0.6.6 has to do with the size. If you take out any of these things and run them, you get just a box. If you take out the other half, you pretty much get nothing in there. And if you change these numbers, change them a little bit, you can see it gets bigger. They had 0.6 on here. I'll go ahead and leave it as 1 because that's just kind of fun. But that's all about the size on here, the height and the width. And then let's create some data. T equals NP line space. And this is 0 to 2 times NP times pi. So if you remember, that is the distance across, and we're going to generate 100 points. So this is just a thing of data we're putting together. Then we can simply do an ax.plot. And in this case, let's do t comma t, which would be a diagonal line on a regular chart. And we'll give it a nice color equals blue. And line width equals 3. Let's see what that looks like. And we can see here a spiral coming out. And remember, this would be just a diagonal line on a regular chart. What happens if we take this and instead of t times 0.5, there we go. And you can see it slightly alters the way it spirals out. We could do t times 2. Spirals out a little quicker. So it's kind of just a fun. Like I said, I've never used a radar chart. It's a column. But you can always think of radar in a submarine. Kind of looks like one of those, or in an airplane. And none of this would be complete if we didn't discuss histograms. Oh my gosh, do I use a histogram so much. And we'll use our numpy that we have set as np to generate. Oh, it looks like we have 100,000 variables we're going to set equal to n. And of course, we create our figure and our axes. Subplots 1, 2, figure size 12, 14. So we're going to look at 2 different variations of the histogram. And we'll set a title, default histogram, set our title there. And then this is simply hist for histogram, and we'll just go ahead and put in our n in there. And let me run this and see what that looks like. And let's talk about what is going on here. So we generated an array here of data, 1,000 random arrays. It looks like they're mostly between -4 and 4. And then it adds up each one. It says 0, you have 35,000 that are 0. So that's what's most common on here. And we have 20,000 that are somewhere in this range right here between the -2 and, well, it looks like 1 and -2. And somewhere between 0 and 1, there's 30,000 numbers. So all this is saying is this is how common these variables are. And this will point you in so many directions when you're looking at data science to go ahead and run your histogram. So you should always have your histogram, and you can always put limits and all the other different things on your array, just like you did on the other graphs on there. And then we're going to do a cumulative detailed histogram. And all it is a histogram. Let me just do that. And we set cumulative equal to true and bins equal 50. And I really want to highlight the cumulative equals true is important. But we can now choose how many bins we have. In the first one, it kind of selected them for us. In this case, let me go ahead and run this. And you'll see it prints the data out for us. And here's our, whoops, must have missed, oh, there we go. It doesn't help that I put it over the old one. There we go, okay. So now you have your default histogram, and now we have a cumulative histogram. And we should have 50 steps in there. And let's just find out if that's true, not so much by counting them. I'm not going to count them. If you want to, you can count them. Let's just change it to 10 and see what happens. And we see here we have now 10 counts of that. And we could set that for 5. And run that. And then we have our 5 on there. And we go ahead and take the cumulative equals true out, just so you can see what that looks like. And let me run that on here too. That looks just like it did before. I think there's 1, 2, 3, 4, 5, 6, 7, 8. They have 8 different bins on here, is what the default came out of. Put that back in there, run. And so now it should look almost identical, and it does. And then we can put the cumulative back in, see what that looks like with the cumulative. And run that. And we can see how that shifts everything over and has a slightly different look. Wait, it shifts it all to the right? No, it doesn't actually shift it to the right. It's cumulative, so it's the total of the different occurrences. And so what that means is, like, if you consider this like for the year of rainfall, we have like day 1, you had a little bit of rain. Day 2, we have more rain. And so if you look at the number, this is 100,000, 35,000. So it's a cumulative detailed histogram of the occurrence as it grows. And rainfall is a good one, because that would be a cumulative histogram of how much rain occurred throughout the year. And we're going to look at 2 more graphs. We've already looked at a bunch of them. We looked at our radar graph. We've looked at scatter, step, bar, fill in, basic plots. We've looked at different ways of showing the data. We can increase the size of the line, the look, the color, the alpha setting. So let's look at contour maps. Just put that in there. There we go. Draw a contour map. And before we draw a contour map, we need to go ahead and create data for it. And if you have contours, your data is all going to have 3 different values. So let's go ahead and create the data here. We have our, you'd import your matplot library, your numpy, so we have our numbers array. And we'll import matplot.cm, and that's your color maps. So you have all these different color maps you can look at. There's like hundreds of color maps. So if you don't want to do your own color, you can even do your own color map. They're pretty diverse. And of course our PLT, our pie plot. And to generate our different data, we're going to create a delta 0.025. And we'll start with x, and we're going to create an array between -3 and 3 in delta increments of 0.025. And we'll have our y, we'll do something similar, and then we'll create our xy into a mesh grid. Again, these are all numpy commands, so if you're not familiar with these, you'll want to go back and review our numpy tutorial. And we'll do an exponential on here, -x² minus y² for our z1. We'll do a z2, so we have 2 different areas, and z equals z1 minus z2 times 2. So we've created a number of values here. And let me go ahead and run this, and let's plug that in so you can see where those values are going. So once we've set these, we're going to create our figure and our x from our PLT subplots. We're going to create the variable cs, and this is going to be our contour. So right here, cs is our contour surface, and we're feeding it x, y, and z. And if you remember, x, y we created as our x and y components using our mesh grid. And you know what? Let's do this just because it's kind of good to see this. Let's go ahead and print x, and let's print y. And I always like to do this when I'm working with something that's either is really complicated, in this case is what we're looking at, or you don't understand yet. So we've created a mesh grid. We have x, y, and when we're done with this, we end up with, here's our x, and this set of values, and our y. So these are x and y coordinates. And then we've also created z based on our x and y. So we have x, capital Y, and capital Z as our 3 components. X and y being the coordinates, while z is going to be our actual height, since we're doing a contour map. So we created our contour map from our x, y, and z coordinates. We want to go ahead and put in a C label. Maybe we want to go ahead and do a title on here. We'll put that in our set title, and this is a contour. There we go, contour map. And let's go ahead and run this and see what that looks like. And you'll see we generated a nice little contour map. There's different settings you can play with on this, but you can picture this being you're on a mountain climb, and here we have a line that's represent 0, maybe that's sea level. And then moving on up, you have your contours of 0.5 and then -1 and different setups, little hills. I guess if it's minus, that's like a pit. So I guess you're going down into a pit at -5 and -1. And on the other side, you can see you're going up in levels. So here's a mountaintop, and here's like a basin of some kind. And in data science, this could represent a lot of things. This could also be representing 2 different values and maybe profits and loss. I don't know if I'd ever really do that as a contour map, but I'm sure you can be creative and find something fun to do with a contour map. And then we're going to look at one last map, which is the 3D map. And those can be really important as a final product because they can show so much additional information that you can't fit on 2-dimensional graphs. There we go. Draw a 3D image. And so we're going to import from our MPL toolkits the mplot 3D and the axes 3D. We're going to import axes 3D. This is what's going to let us work with the 3D image. And this should look familiar. We're going to create another figure just like we did before. Figure size 14 by 6. That's a good fit on the screen. We'll go ahead and run that. So we have our figure, and let's go ahead and take our x, and we're going to set that equal to fig.add_subplot. That should also be familiar from earlier. And we're going to work with, this sets the settings for the projection. And we're going to use 1, 2, 1 projection 3D. And we'll see what that looks like in just a minute. And we just created some three-dimensional data here before, where we had X, Y, and Z, capital X, Y, and Z. So we're going to reuse that data. We're just going to use that since this is also a three-dimensional image. So let's use that for a three-dimensional graph. And we simply do AX plot underscore surface, and our capital X, capital Y, capital Z. So there's our data coming in. And we're going to add some settings in here. We're going to do R stride 4, C stride 4, and line width 0. And I'll show you what that is here in just a minute. Let's go ahead and run that so we can see our graph. And of course it helps if I don't add an extra comma in there. And you can see it generates this really beautiful three-dimensional graph. So let's take a little bit time to explore some of these numbers we have going in here. We have the R stride 4, the C stride 4, and the projection 3D. Projection 3D is the important one because that's telling us that this is a 3D graph here. So what are these first numbers? 1, 2, 1. Let's just change one of these. I'm going to change this to 5, and it's going to give me an error. Let's change it to 1. And oops, that didn't work. Let's change this middle one to 3 instead. And you're going to see how it starts reshaping the size and how it fits on the screen. And we'll change the first one to 2. We'll run that one. And again, it's changed the dimensions and the size and how it fits on here. Play with these numbers till you get a nice look and feel for it. Part of it is the tilt and the angle. We'll do 7 on this one. There we go. You can see it really shifted it there. But again, that changes the size and how it fits on the canvas. But we'll leave it at the 1, 2. And just so you get a good look at what we're talking about here, this is column width and index from before. If we do 1, 1, 1, you can see that it now spreads it out all the way across. It uses the whole setup on there. So this has to do with the size and how big you want it to be. Now, there's one term that we didn't cover in this yet, but we've used it throughout the whole setup. And I'm just going to type that down here, even though we're not going to go into detail. And that's the term heat map. You might see that is kind of starting to lose ground as far as a common reference, but there sure are a lot of people who still talk about heat maps. What is a heat map? Well, it is simply a color map. That's all it is. So if you ever see the term heat map, that refers to the fact this is in different colors representing different heights. That one isn't a heat map, but you can see up here we switched into, let me go back up here, here we go. This one has different colors for the different values. A lot of times you'll use, like instead of X and Y, you might do a heat map where you have a fourth value, and the fourth value represents the color. And so you'll see this 3D image in a nice colors represented by a heat map. That's all it is. So if you see the term heat map, that only means we're plotting some of the data in color to make it stand out or to give it a fourth dimension in this case. So we've covered a lot of things on Matplot, and that brings us, covered all the basics, so that brings us to practice example. And this is going to be the challenge for you. And let me go ahead and change our cell type markdown and run that so it looks pretty. Practice example, write a Python program to create a pie chart of the popularity of programming languages. Okay, excellent. And if you're going to have a challenge, we need some data. And I'll just throw in import our Matplot library at the beginning. You should do that automatically. And so for our data to plot, we're going to have our languages. We're going to have Python, we're going to have Java, PHP, JavaScript, C#, C++. So those are 6 categories. And then we have our popularity. Oops, misspelling there. Popularity. We'll give the first one 22.2%, Java 17.6%. And I don't know if these are real numbers they pulled. My guess is that they might have just been made up because I don't know if Python's really that much more popular than the other ones. Maybe specific to data science, because Python's very popular in data science right now because it has so many options. The only other program that's highly used and exclusively for data science is R. So Python's big, and Python also does a lot more. It's a full programming language, where R is primarily for data science. They didn't even put R in here. So we have Python, we have Java, we have our PHP, and you can see the different values they've given it, or different percentages. And I did add these up. It does not add up to 100%. It adds up to 71% or something like that. And then we're going to give colors. And we've chosen, these guys in the back brought in these colors. I'm not sure what these colors are. We'll find out in a minute, so it'll be exciting. But you can see they're using the actual color values you can pull off of a color wheel or something like that. You could have just as easily done blue, red, green if you're too lazy to pick the exact colors. And then let's go ahead and solve this and see what we got here. We're going to do something a little fancy just because we can. The first thing we're going to do is we're going to use a variable called explode. And you'll notice that there's 6 variables in here, so that matches our 6 different categories. And the first one we've done is 0.1 and then 0, 0, 0, 0, 0. 0.1, when we put this in here under the explode in the plot, it will actually push that square out. So it's a really cool feature to highlight certain information on a pie chart. And this is simply plt.pie. And we're plotting popularity. There we go. And before we add in all the really cool settings for this, let's go ahead and run it. And you'll see we generate a nice flat pie. Not too exciting there. And then we'll go ahead and put in all the extras. I talked about explode, where we can explode one of the values out. So here's our explode equals explode. Labels is languages, because we want to know what the different colors mean. Here's our colors equals colors, our auto picture. And this is standard print format. So that's a Python setup on there. And that's just going to put the value on the pie slice. And then we're going to add shadow, because it just looks cooler with a shadow, gives it a little 3D look. And we'll do a start angle of 140. Let's go ahead and run this and take a look and see what comes out of that. And look how that changes the whole setup. So here's our labels. There's our value we put on there. There's our slice that's pushed out. There's our shadow, a 3D effect. And then we started at 140. We could also rotate this. Let's just do this angle 90. And if we run it, you'll see the blue pie slice has moved up a little bit. We could actually let's just take the whole starting triangle out and run. It'll default to 0. This is what it looks like if it defaulted to 0. So depending on where you want the highlighted slice to appear, usually you want that to appear on the left because people read left to right. And so it draws a focus onto, in this case, Python and how great Python is. I'm a little biased. We're teaching a Python tutorial, so it should be understandable that we're looking at Python. And one last reference before we close. You can go over to the matplotlibary.pyplot setup, and if you go underneath the different functions on there, you can look this up on their website. You'll see a full list, and this is why it's so important to go through a tutorial like this, because this list is just so massive. I'm trying to figure out, like, here's our bar plot. There's a bar H. You can add barbs. There's a box plot we didn't cover. C labels, a totally different kind of, for your contour plot you can set up in there. If you go down here, we have our figures we used on there. We showed you the basics of how to do the figure. You'll see some closer references on those. There's a histogram down here, HIST. There's also the hist2d, makes a 2D histogram plot. H-lines, all of this, these are all the different commands that are underneath of here. And you can see it's pretty extensive. We've covered all the basic ones so that you now have a solid ground to look at these different options. So when you come to these functions, some of them are going to look a little off, or not off, will look unfamiliar, but you'll still have the availability to probably understand most of this and have a basic understanding of your matplot library. So what is the scikit-learn? It's a simple and efficient tool for data mining and data analysis. It's built on NumPy, SciPy, and Matplotlib, so it interfaces very well with these other modules. And it's an open source, commercially usable BSD license. BSD originally stood for Berkeley Software Distribution License, but it means it's open source with very few restrictions as far as what you can do with it. Another reason to really like the scikit-learn setup, so you don't have to pay for it as a commercial license versus many other copyrighted platforms out there. What we can achieve using the scikit-learn, we use the two main things are classification and regression models. Classification, identifying which category an object belongs to. For one application very commonly used is spam detection. So is it a spam or is it not a spam? Yes, no. In banking, it might be, is this a good loan, bad loan? Today we'll be looking at wine. Is it going to be a good wine or a bad wine? And regression is predicting an attribute associated with an object. One example is stock prices prediction. What is going to be the next value? If the stock today sold for $23.05 a share, what do you think it's going to sell for tomorrow and the next day and the next day? So that'd be a regression model. Same thing with weather forecasting. Any of these are regression models where we're looking at one specific prediction on one attribute. Today we will be doing classification. Like I said, we're going to be looking at whether a wine's good or bad. But certainly the regression model, which is in many cases more useful because you're looking for an actual value, is also a little harder to follow sometimes. So classification is a really good place to start. We can also do clustering and model selection. Clustering is taking an automatic grouping of similar objects into sets. Customer segmentation is an example. So we have these customers like this, they'll probably also like this. Or if you like this particular kind of features on your objects, maybe you like these other objects. So it's a referral is a good one, especially on Amazon.com or any of your shopping networks. Model selection, comparing, validating, and choosing parameters and models. Now, this is actually a little bit deeper as far as a Scikit-learn. We're looking at different models for predicting the right course or the best course or what's the best solution. Today, like I said, we're looking at wines. So it's going to be, well, how do you get the best wine out of this? So we can compare different models, and we'll look a little bit at that, and improve the model's accuracy via different parameters and fine-tuning. Now, this is only part one, so we're not going to do too much tuning on the models we're looking at, but I'll point them out as we go. Two other features, dimensionality reduction and pre-processing. Dimensionality reduction is we're reducing the number of random variables to consider. This increases the model efficiency. We won't touch that in today's tutorial, but be aware if you have, thousands of columns of data coming in, thousands of features, some of those are going to be duplicated, or some of them you can combine to form a new column, and by reducing all those different features into a smaller amount, you can increase the efficiency of your model. It can process faster, and in some cases you'll be less biased, because if you're weighing it on the same feature over and over again, it's going to be biased to that feature. And pre-processing. These are both pre-processing, but pre-processing is feature extraction and normalization. So we're going to be transforming input data such as text for use with machine learning algorithms. We'll be doing a simple scaling in this one for our pre-processing, and I'll point that out when we get to that. And we can discuss pre-processing at that point. With that, let's go ahead and roll up our sleeves and dive in and see what we got here. Now, I like to use the Jupyter Notebook, and I use it out of the Anaconda Navigator. So if you install the Anaconda Navigator, by default, it will come with the Jupyter Notebook, or you can install the Jupyter Notebook by itself. This code will work in any of your Python setups. I believe I'm running an environment of 3.7 setup on there. I'd have to go in here into environments and look it up for the Python setup. But it's one of the 3X's. And we go ahead and launch this, and this will open it up in a web browser. So it's kind of nice. It keeps everything separate. And in this Anaconda, you can actually have different environments, different versions of Python, different modules installed in each environment. So it's a very powerful tool if you're doing a lot of development. And the Jupyter Notebook is just a wonderful visual display. Certainly you can use, I know Spider is another one which is installed with the Anaconda. I actually use a simple Notepad++ when I'm doing some of my Python script. Any of your IDEs will work fine. Jupyter Notebook is Iron Python because it's designed for the interface, but it's good to be aware of these different tools. And when I launch the Jupyter Notebook, it'll open up, like I said, a web page in here. And we'll go over here to New and create a new Python setup. And like I said, I believe this is Python 3.7, but any of the three, the Scikit-learn works with any of the 3X's. There's even 2.7 versions. So it's been around a long time. So it's very big on the development side. And then the guys in the back, guys and gals, they went ahead and put this together for me. And let's go ahead and import our different packages. Now, if you've been reading some of our other tutorials, you'll recognize pandas as PD. Pandas library is pretty widely used. It's a data frame setup, so it's just like columns and rows in a spreadsheet with a lot of different features for looking stuff up. Seaborn sits on top of Matplot libraries. This is for our graphing. And we'll see that how quick it is to throw a graph out there to view in the Jupyter Notebook for demos and showing people what's going on. And then we're going to use the random forest list the SVC or support vector classifier and also the neural network. So we're going to look at this. We're actually going to go through and look at 3 different classifiers that are most common, some of the most common classifiers, and let's show how those work in the scikit-learn setup and how they're different. And then if you're going to do your setup on here, you'll want to go ahead and import some metrics. So the sklearn.metrics on here, and we're going to use the confusion metrics and the classification report out of that. And then we're going to use from the sklearn pre-processing the standard scalar and label encoder. Standard scalar is probably the most commonly used pre-processing. There's a lot of different pre-processing packages in the sklearn. And then model selection for splitting our data up. It's one of the many ways we can split data into different sections. And the last line here is our percentage matplot library inline. Some of the Seaborn and matplot library will go ahead and display perfectly inline without this, and some won't. It's good to always include this when you're in the Jupyter Notebook. This is Jupyter Notebook, so if you're in IDE, when you run this, it will actually open up a new window and display the graphics that way. So you only need this if you're running it in a editor like this one, with specifically Jupyter Notebook. I'm not even familiar with other editors that are like this, but I'm sure they're out there. I'm sure there's a Firefox version or something. Jupyter Notebook just happens to be the most widely used out there. And we can go ahead and hit the run button, and this now has saved all this underneath the packages. So my packages are now all loaded. I've run them, whether you run it on top or you run it to the left, and all the packages are up there, so we now have them all available to us for our project we're working on. And I'm just going to make a little side note on that. When you're playing with these and you delete something out and add something in, even if I went back and deleted this cell and just hit the scissors up here, these are still loaded in this kernel. So until I go under kernel and restart and clear or restart and run all, I'll still have access to pandas. Important to know, because I've done that before. I've loaded up, maybe not a module here, but I've loaded up my own code and then changed my mind and wondering, why does it keep putting out the wrong output? And then I realized it's still loaded in the kernel and you have to restart the kernel. Just a quick side note for working with a Jupyter Notebook and one of the troubleshooting things that comes up. And we're going to go ahead and load up our data set. We're using the pandas, so if you haven't yet, go look at our pandas tutorial. A simple read the CSV with the separation on here. And so let me go ahead and run that. And that's now loaded into the variable wine. And let's take a quick look at the actual file. I always like to look at the actual data I'm working with. In this case, we have wine quality-red. I'll just open that up. I have it in my open office setup. I'm separated by semicolons. That's important to notice. And when we open that up, you'll see we have, go all the way down here. It looks like 1,600 lines of data minus the first one, so 1,599 lines. And we have a number of features going across. The last one is quality. And right off the bat, we see the quality is has different numbers in it, 5, 6, 7. It's not really, I'm not sure how high of a level it goes, but I don't see anything over a 7. So it's kind of 5 through 7 is what I see here. 5, 6, and 7. 4, 5, 6, and 7, looking to see if there's any other values in there. Looking through the demo to begin with, I didn't realize the setup on this. So you can see there's the different quality values in there: alcohol, sulfates, pH, density, total sulfur dioxide, and so on. Those are all the features we're going to be looking at. And since this is a pandas, we'll just do wine head, and that prints the first 5 rows of data. That's of course a pandas command. And we can see that looks very similar to what we were looking at before. We have everything across here. It's automatically assigned an index on the left. That's what pandas does if you don't give it an index. And for the column names, it has assigned the first row. So we have our first row of data pulled off our comma separated variable file, in this case semicolon separated. And it shows the different features going across. And we have, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 features. 12 including quality, but that's the one we want to work on and understand. And then because we're in pandas data frame, we can also do wine.info. And let's go ahead and run that. This tells us a lot about our variables we're working with. You'll see here that there is 1,599. That's what I said from the spreadsheet, so that looks correct. Non-null float 64. This is very important information, especially the non-null. So there's no null values in here. That can really trip us up in pre-processing. And there's a number of ways to process non-null values. One is just to delete that data out of there. So if you have enough data in there, you might just delete your non-null values. Another one is to fill that information in with like the average or the most common values or other such means. But we're not going to have to worry about that. But we'll look at another way, because we can also do wine is null and sum it up. And this will give us a similar, it won't tell us that these are float values, but it will give us a summation. Oops, there we go, let me run that. It'll give us a summation on here, how many null values in each one. So if you wanted to, from here you would be able to say, okay, this is a null value, but it doesn't tell you how many are null values. This one would clearly tell you that you have maybe 5 null values here, 2 null values here. And you might just, if you had only 7 null values and all that different data, you'd probably just delete them out. Where if 90% of the data was null values, you might rethink either a different data collection setup or find a different way to deal with the null values. And we'll talk about that just a little bit in the models too, because the models themselves have some built-in features, especially the forest model, which we're going to look at. At this point, we need to make a choice. And to keep it simple, we're going to do a little pre-processing of the data, and we're going to create some bins. And bins we're going to do is 2, 6.5, 8. What this means is that we're going to take those values. If you remember up here, let me just scroll back up here. We had our quality. The quality comes out between 2 and 8 basically, or 1 and 8. But we have 5, 5, 5, 6. You can see just in the first 5 lines of variation in quality. We're going to separate that into just 2 bins of quality. And so we've decided to create 2 bins. We have bad and good. It's going to be the labels on those 2 bins. We have a spread of 6.5 and an exact index of 8. The exact index is because we're doing 0 to 8 on there. The 6.5 we can change. We could actually make this smaller or greater, but we're only looking for the really good wine. We're not looking for the 0, 1, 2, 3, 4, 5, 6. We're looking for wines with 7 or 8 on them. So high quality. This is what I want to put on my dinner table at night. I want to taste the good wine, not the semi-good wine or mediocre wine. And then this is a pandas. So PD, remember, stands for pandas. Pandas cut means we're cutting out the wine quality and we're replacing it. And then we have our bins equals bins. That's the command. Bins is the actual command. And then our variable bins, 2, 6.58. So 2 different bins. And our labels, bad and good. And we can also do, let me just do it this way. Wine quality, since that's what we're working on. And let's look at unique. Another pandas command, and we'll run this. And I get this lovely error. Why did I get an error? Well, because I replaced wine quality and I did this cut here, which changes things on here. So I literally altered one of the variables that is saved in the memory. So we'll go up here to the kernel, restart and run all. That starts it from the very beginning. And we can see here that that fixes the error because I'm not cutting something that's already been cut. We have our wine quality unique, and the wine quality unique is a bad or good. So we have 2 qualities objects. Bad is less than good, meaning bad's going to be 0 and good's going to be 1. And to make that happen, we need to actually encode it. So we'll use the label quality equals label encoder. And the label encoder, let me just go back there since this is part of sklearn. That was one of the things we imported, was a label encoder. You can see that right here from the sklearn.processing import standard scalar, which we're going to use in a minute, and label encoder. And that's what tells it to use bad equals 0 and good equals 1. And we'll go ahead and run that, and then we need to apply it to the data. And when we do that, we take our wine quality that we had before, and we're going to set that equal to label quality, which is our encoder. And let's look at this line right here. We have dot fit transform. And you'll see this in the pre-processing. These are the most common used, is fit transform and fit transform. Because they're so often that you're also transforming the data, when you fit it, they just combine them into one command. And we're just going to take the wine quality, feed it back into there, and put that back in our wine quality setup, and run that. And now when we do the wine and the head of the first 5 values, and we go ahead and run this, you can see right here underneath quality 0, 0, 0. Have to go down a little further to look at the better wines. Let's see if we have some that are 1s. Yeah, there we go. There's some 1s down here. So when we look at 10 of them, you can see all the way down to 0 or 1. That's our quality. And again, we're looking at high quality. We're looking at the 7 and the 8s, or 6.5 and up. And let's go ahead and grab our, where was it? Here we go, wine quality. And let's take another look at what else, more information about the wine quality itself. And we can do a simple pandas thing, value counts. Hopefully I typed that in there correctly. And we can see that we only have 217 of our wines which are going to be the higher quality. So 217, and the rest of them fall into the bad bucket, the 0, which is 1,382. So again, we're just looking for the top percentage of these. The top, what is that? It's probably about a little under 20% on there. So we're looking for our top wines, our 7 and 8s. And let's use our, let's plot this on a graph so we can take a look at this. And the SNS, if you remember correctly, that is, let me just go back to the top, that's our seaborn. Seaborn sits on top of Matplot library. It has a lot of added features, plus all the features of the Matplot library, and it also makes it quick and easy to put out a graph. And we'll do a simple bar graph, and they actually call it count plot. And then we want to just do count plot the wine quality. So let's put our wine quality in there. And let's go ahead and run this and see what that looks like. And nice inline. Remember, this is why we did the inline, so make sure it appears in here. And you can see the blue space, or the first space, represents low quality wine, and our second bar is a high quality line. And you can see that we're just looking at the top quality wine here. Most of the wine, we want to just give it away to the neighbors. No, maybe if you don't like your neighbors. Maybe give them the good quality wine, and I don't know what you do with the bad quality wine. I guess use it for cooking. There we go. But you can see here it forms a nice little graph for us with the seaborn on there, and you can see our setup on that. So now we've done some pre-processing. We've described our data a little bit. We have a picture of how much of the wine, what we expect it to be, high quality, low quality. Checked out the fact that there's none, we don't have any null values to contend with or any odd values. Some of the other things you sometimes look at these is if you have like some values that are just way off the chart. So the measurement might be off, or miscalibrated equipment if you're in the scientific field. So the next step we want to go ahead and do is we want to go ahead and separate our data set, or reformat our data set. And we usually use capital X, and that denotes the features we're working with. And we usually use a lowercase y. That denotes what, in this case, quality, what we're looking for. And we can take this and we can go wine. It's going to be our full thing of wine. Dropping, what are we dropping? We're dropping the quality. So these are all the features minus quality. And make sure we have our axes equals 1. If you left it out, it would still come out correctly just because of the way it processes on the defaults. And then our y, if we're going to remove quality for our x, that's just going to be wine, and it is just the quality that we're looking at for y. So we put that in there. And we'll go ahead and run this. So now we've separated the features that we want to use to predict the quality of the wine and the quality itself. The next step is if you're going to create a data set and a model, we got to know how good our model is. So we're going to split the data, train and test splitting data. And this is one of the packages we imported from sklearn. And the actual package was train, test, split. And we're going to do x, y, test size 0.2, random state 42. And this returns 4 variables. And most common you'll see is capital X train, so we're going to train our set with. Capital X test, that's the data we're going to keep on the side to test it with. Y train, Y remember stands for the quality or the answer we're looking for. So when we train it, we're going to use X train and Y train, and then Y test to see how good our X test does. And the train test split, let me just go back up to the top. That was part of the sklearn model selection, import train test split. There is a lot of ways to split data up. This is, when you're first starting, you do your first model, you probably start with the basics on here. You have one test for training, one for test. Our test size is 0.2 or 20%. And random state just means we just start with it's like a random seed number, so it's not too important back there. We're randomly selecting which ones we're going to use. Since this is the most common way, this is what we're going to use today, there is, and it's not even an sklearn package yet, so someone's still putting it in there. One of the new things they do is they split the data into thirds, and then they'll run the model on they combine each of those thirds into 2 thirds for training and 1 for testing. And so you actually go through all the data and you come up with 3 different test results from it, which is pretty cool. That's a pretty cool way of doing it. You could actually do that with this by just splitting this into thirds, and then, or have a test set, one test set third, and then split the training set also into thirds, and also do that and get 3 different data sets. This works fine for most projects, especially when you're starting out. It works great. So we have our X train, our X test, our Y train, and our Y test. And then we need to go ahead and do the scalar. And let's talk about this because this is really important. Some models do not need to have scaling going on. Most models do. And so we create our scalar variable. We'll call it SC, standard scalar. And if you remember correctly, we imported that here, along with the label encoder, the standard scalar setup. So there's our scalar, and this is going to convert the values. Instead of having some values that go from 0, if you remember up here we had some values are 54, 60, 40, 59, 102. So our total sulfur dioxide would have these huge values coming into our model. And some models would look at that and they'd become very biased to sulfur dioxide. It'd have the hugest impact. And then a value that had 0.076, 0.098, or chlorides would have very little impact because it's such a small number. So when we take the scalar, we kind of level the playing field. And depending on our scalar, it sets it up between 0 and 1 a lot of times is what it does. Let's go ahead and take a look at that. And we'll go ahead and start with our X train. And our X train equals SC fit transform. We talked about that earlier. That's an sklearn setup. It's going to both fit and transform our X train into our X train variable. And if we have an X train, we also need to do that to our test. And this is important because you need to note that you don't want to refit the data. We want to use the same fit we used on the training as on the testing. Otherwise, you get different results. And so we'll do just, oops, not fit, transform. We're only going to transform the test side of the data. So here's our X test that we want to transform. And let's go ahead and run that. And just so we have an idea, let's go ahead and take and just print out our X train. Oh, let's do first 10 variables, very similar to the way you do the head on a data frame. You can see here our variables are now much more uniform, and they've scaled them to the same scale, so they're between certain numbers. And with the basic scalar, you can fine-tune it. I just let it do its defaults on this, and that's fine for what we're doing. In most cases, you don't really need to mess with it too much. It does look like it goes between like probably -2 to 2 or something like that. That's just looking at the train variable. We'll go ahead and cut that one out of there. So before we actually build the models and start discussing the sklearn models we're going to use, we covered a lot of ground here. Most of when you're working with these models, you put a lot of work into prepping the data. So we looked at the data, noticed that it's separated, loaded it up. We went in there, we found out there's no null values. That's hard to say, no null values. We have, there's none null value. I can't say it. And of course we sum it up. If you had a lot of null values, this would be really important coming in here. So is there a null summary? We looked at pre-processing the data as far as the quality. And we're looking at the bins. So this would be something you might start playing with. Maybe you don't want super fine wine. You don't want the 7 and 8s. Maybe you want to split this differently. So certainly you can play with the bins and get different values and make the bins smaller or lean more towards the lower quality. So you then have like medium to high quality. And we went ahead and gave it labels. Again, this is all pandas we're doing in here. Setting it up with unique labels and group names. Bad, good. Bad is less than good. That can be so important. You don't know how many times people go through these models and they have them reversed or something. And then they go back and they're like, why is this data not looking correct? So it's important to remember what you're doing up here and double check it. And we used our label encoder. So that was to set that up as quality 0, 1. Good, in this case we have bad, good, 0, 1. And we just double check that to make sure that's what came up in the quality there. And then we threw it into a graph because people like to see graphs. I don't know about you, but you start looking at all these numbers and all this text and you get down here and you say, oh, yes, you know, here, this is how much of the wine we're going to label as subpar, not good. And this is how much we're going to label as good. And then we got down here to finally separating out our data so it's ready to go into the models. And the models take X and a Y. In this case, X is all of our features minus the one we're looking for, and then Y is the features we're looking for. So in this case, we dropped quality, and in the Y case, we added quality. And then because we need to have a training set and a test set so we can see how good our models do, we went ahead and split the models up, X train, X test, Y train, Y test. And that's using the train test split, which is part of the sklearn package. And we did, as far as our testing size, 0.2 or 20%. The default is 25%, so if you leave that out, it'll do default setup. And we did a random state equals 42. If you leave that out, it'll use a random state. I believe it's default 1. I'd have to look that back up. And then finally, we scaled the data. This is so important to scale the data. Going back up to here, if you have something that's coming out as 100, it's going to really outweigh something that's 0.071. That's not in all the models. Different models handle it differently. And as we look at the different models, I'll talk a little bit about that. We're going to only look at 3 models today, 3 of the top models used for this, and see how they compare and how the numbers come out between them. So we're going to look at 3 different setups. Oh, let me change my cell here to Markdown. There we go. And we're going to start with the random forest classifier. So the 3 setups we're looking at is the random forest classifier, support vector classifier, and then a neural network. Now we start with the random forest classifier because it has the least amount of moving parts to fine tune. And let's go ahead and put this in here. So we're going to call it RFC for random forest classifier. And if you remember, we imported that. So let me go back up here to the top real quick. And we did an import of the random forest classifier from sklearn ensemble. And then we also, let me just point this out, here's our SVM where we imported our support vector classifier. So SVM is support vector model, support vector classifier. And then we also have our neural network. And we're going to, from there, the multi-layered perceptron classifier. Kind of a mouthful for the P, perceptron. Don't worry too much about that name. It's a neural network. There's a lot of different options on there in setups, which is where they came up with the perceptron. So we have our 3 different models we're going to go through on here. And then we're going to weigh them. Here's our metrics. So we're going to use a confusion metrics, also from the sklearn package, to see how good our model does with our split. So let's go back down there and take a look at that. And we have our RFS equals random forest classifier, and we have n estimators equals 200. This is the only value you play with a random forest classifier. How many forests do you need? Or how many trees in the forest? So how many models are in here? That makes it pretty good as a startup model because you're only playing with one number and it's pretty clear what it is, and you can lower this number or raise it. Usually start up with a higher number and then bring it down to see if it keeps the same value. So you have less, the smaller the model, the better the fit, and it's easier to send out to somebody else if you're going to distribute it. Now the random forest classifier, everything I read says it's used for kind of a medium-sized data set. So you can run it on big data, you can run it on smaller data obviously, but it tends to work best in the mid-range. And we'll go ahead and take our RFC, and I just copied this from the other side, .fit xtrain, ytrain. So we're sending it our features and then the quality in the Y train, what we want to predict in there. And we just do a simple fit. Now remember, this is sklearn, so everything is fit or transform. Another one is predict, which we'll do in just a second here. In fact, let's do that now. Predict RFC equals, and it's our RFC model, predict. And what are we predicting on? Well, we trained it with our train values, so now we need our test, our X test. So this has done it. This is the 3 lines of code we need to create our random forest variable, fit our training data to it. So we're programming it to fit. In this case, it's got 200 different trees it's going to build. And then we're going to predict on here. And let me go ahead and just run that. And we can actually do something like, let's do predict RFC. Just real quick, we'll look at the first 20 variables of it. Let's go ahead and run that. And in our first 20 variables, we have 3 wines that make the cut, and the other 17 don't. So the other 17 are bad quality, and 3 of them are good quality in our predicted values. And if you can remember correctly, we'll go ahead and take this out of here. This is based on our test. So these are the first 20 values in our test, and this has, as you can see, all the different features listed in there, and they've been scaled. So when you look at these, they're a little bit confusing to look at and hard to read, but there's a -0.01, so this is 0.36, -0.01, so 0.164, -0.09, or no, it's still -1, so -0.9, all between 0 and 1 on here. I think I was confused earlier and I said 0 between 2, -2, but it's between -1 and 1, which is what it should be in the scale. And we'll go ahead and just cut that out of there. Run this. We have our setup on here. So now that we've run the prediction and we have predicted values, well, one, you could publish them, but what do we do with them? Well, what we want to do with them is we want to see how well our model performed. That's the whole reason for splitting it between a training and testing model. And for that, if you remember, we imported the classification report. That was again from the sklearn. There's our confusion matrix and classification report. And the classification report actually sits on the confusion matrix, so it uses that information. And our classification report, we want to know how good our Y test, that's the actual values, versus our predicted RFC. So we'll go ahead and print this report out, and let's take a look. And we can see here we have a precision out of the 0. We had about 0.92 that were labeled as bad that were actually bad. And out of precision for the quality wines, we're running about 78%. So you kind of give us an overall 90%. And you can see our F1 score, our support set up on there, our recall. You could also do the confusion matrix on here, which gives you a little bit more information. But for this is going to be good enough for right now. We're just going to look at how good this model was, because we want to compare the random forest classifier with the other two models. And you know what, let's go ahead and put in the confusion matrix, just so you can see that on there, with y-test and prediction RFC. So in the confusion matrix, we can see here that we had 266 correct and 7 wrong. These are the mislabels for bad wine, and we had a lot of mislabels for good wine. So our quality labels aren't that good. We're good at predicting bad wine, not so good at predicting whether it's a good quality wine. Important to note on there. So that is our basic random forest classifier. And let me go ahead, change cell type to markdown and run that so we have a nice label. Let's look at our SVM classifier, our support vector model. And this should look familiar. We have our CLF we're going to create. We'll call it, just like we call this an RFC. And then we'll have our CLF.fit. And this should be identical to up above. X train, comma, Y train. And just like we did before, let's go ahead and do the prediction. And here is our CLF predict. And it's going to equal the CLF.predict. And we want to go ahead and use X underscore test. And right about now you can realize that you can create these different models and actually just create a loop to go through your different models and put the data in. And that's how they designed it. They designed it to have that ability. Let's go ahead and run this, and then let's go ahead and do our classification report. And I'm just going to copy this right off of here. They say you shouldn't copy and paste your code, and the reason is when you go in here and edit it, you invariably will miss something. We only have 2 lines, so I think I'm safe to do it today. And let's go ahead and run this. And let's take a look how the SVM classifier came out. So up here we had a 90%, and down here we're running about an 86%. So it's not doing as good. Now remember, we randomly split the data, so if I run this a bunch of times, you'll see some changes down here. So these numbers, this size of data, if I ran it 100 times, it would probably be within plus or minus 3 or 4 on here. In fact, if I ran this 100 times, you'd probably see these come out almost the same as far as how well they do in classification. And then on the confusion matrix, let's take a look at this one. This had 22 by 25. This one has 35 by 12. So it's doing not quite as good. That shows up here 71% versus 78%. And then if we're going to do a SVM classifier, we also want to show you one more. And before I do that, kind of tease you a little bit here, before we jump into neural networks, the big save all deep learning, because everything else must be shallow learning, that's a joke. Let's just talk a little bit about the SVM versus the random forest classifier. The SVM tends to work better on smaller numbers. It also works really good on, because a lot of times you convert things into numbers and bins and things like that. The random forest tends to do better with those. At least that's my brief experience with it. Where if you have just a lot of raw data coming in, the SVM is usually the fastest and easiest to apply model on there. So they each have their own benefits. You'll find though again that when you run these like 100 times, the difference between these two on a data set like this is going to just go away. There's randomness involved depending on which data we took and how they classify them. The big one is the neural networks, and this is what makes the neural networks nice is they can look into huge amounts of data. So for a project like this, you probably don't need a neural network on this, but it's important to see how they work differently and how they come up differently. So you can work with huge amounts of data. You can also, in many respects, they work really good with text analysis, especially if it's time sensitive. More and more you have an order of text, and they've just come out with different ways of feeding that data in, where the series and the order of the words is really important. Same thing with starting to predict in the stock market. If you have tons of data coming in from different sources, the neural network can really process that in a powerful way to pull up things that aren't seen before. And when I say lots of data coming in, I'm not talking about just the high lows that you can run an SVM on real easily. I'm talking about the data that comes in where you have maybe you pulled off the Twitter feeds and have word counts going on, and you've pulled off the different news feeds that business are looking at, and the different different releases when they release the different reports. So you have all this different data coming in, and the neural network does really good with that. Pictures. Picture processing now is really moving heavily into the neural network. If you have a Pixel 2 or Pixel 3 phone put out by Google, it has a neural network for doing, it's kind of goofy, but you can put little Star Wars androids dancing around your pictures and things like that. That's all done with the neural network. So it has a lot of different uses, but it's also requires a lot of data and is a little heavy-handed for something like this. And this should now look familiar because we've done it twice before. We have our multi-layered perceptron classifier. We'll call it an MLPC, and it's this is what we imported, MLPC classifier. There's a lot of settings in here. The first one is the hidden layers. You have to have the hidden layers in there. We're going to do 3 layers of 11 each. So that's how many nodes are in each layer as it comes in. And that was based on the fact we have 11 features coming in. Then I went ahead and just did 3 layers. Probably get by with a lot less on this. But I didn't want to sit and play with it all afternoon. Again, this is one of those things you play with a lot because the more hidden layers you have, the more resources you're using. You can also run into problems with overfitting, with too many layers, and you also have to run higher iterations. The max iteration we have is set to 500. The default's 200. Because I use 3 layers of 11 each, which is, by the way, kind of a default I use. I realized that usually you have about 3 layers going down and the number of features going across. You'll see that's pretty common for the first classifier when you're working in neural networks. But it also means you have to do higher iterations. So we up the iterations to 500. So that means it's going through the data 500 times to program those different layers and carefully adjust them. And we do have a full tutorials you can go look up on neural networks and understand the neural network settings a lot more. And of course we have, you're looking over here where we had our previous model where we fit it. Same thing here, MLPC, fit, X train, Y train. And then we're going to create our prediction. So let's do our predict and MLPC, and it's going to equal the MLPC. And we'll just take the same thing here, predict X test. Let's just put that down here, dot predict X test. And if I run that, we've now programmed it. We now have our prediction here, same as before. And we'll go ahead and do the copy print again. Always be careful with the copy paste, because you always run the chance of missing one of these variables. So if you're doing a lot of coding, you might want to skip that copy and paste and just type it in. And let's go ahead and run this and see what that looks like. And we came up with an 88%. We're going to compare that with the 86 from our tree, our SVM classifier, and our 90 from the random forest classifier. And keep in mind, random forest classifiers, they do good on mid-sized data. The SVM on smaller amounts of data, although to be honest, I don't think that's necessarily the split between the two. And these things will actually come together if you ran them a number of times. And we can see down here the amount of good wines mislabeled with setup on there. It's on par with our random forest. So it had 22, 25. Shouldn't be a surprise, it's identical. It just didn't do as good with the bad wines labeling, what's a bad wine and what's not. See, yeah, because they had 266 and 7. We had down here 260 and 13. So it mislabeled a couple of the bad wines as good wines. So we've explored 3 of these basic classifiers. These are probably the 3 most widely used right now. I might even throw in the random tree. If we open up their website and we go under supervised learning, there's a linear model. We didn't do that. Most of the data usually just start with a linear model because it's going to process the quickest and use the least amount of resources. But you can see they have linear quadratic, they have kernel ridge. There's our support vector, stochastic gradient, nearest neighbors. Nearest neighbors is another common one that's used a lot. Very similar to the SVM. Gaussian process, cross decomposition, naive Bayes. This is more of an intellectual one that I don't see used a lot, but it's like the basis of a lot of other things. Decision tree, there's another one that's used a lot. Ensemble methods, not as much. Multi-class and multi-label algorithms, feature selection, neural networks, that's the other one we use down here, and of course the forest. So you can see there's in sklearn there are so many different options, and they've just developed them over the years. We covered 3 of the most commonly used ones in here and went over a little bit over why they're different. Neural network, just because it's fun to work in deep learning and not in shallow learning, as I told you. That doesn't mean that the SVM is actually shallow. It covers a lot of things, and same thing with the decision tree, the random forest classifier. And we notice that there's a number of other different classifier options in there. These are just the 3 most common ones, and I'd probably throw the nearest neighbor in there and the decision tree, which is usually part of the decision forest depending on what the backend you're using. And since as human beings, if I was in the shareholder's office, I wouldn't want to leave them with a confusion matrix. They need that information for making decisions, but we want to give them just one particular score. And so I would go ahead and we have our sklearn metrics. We're going to import the accuracy score. And I'm just going to do this on the random forest since that was our best model. And we have our CM accuracy score, and I forgot to print it. If you remember in Jupyter Notebook, we can just do the last variable we leave out there, it'll print. And so our CM accuracy score we get is 90%. And that matches up here. We should already see that up here in precision. So you can either quote that, but a lot of times people like to see it highlighted at the very end. This is our precision on this model. And then the final stage is we would like to use this for future. So let's go ahead and take our wine. If you remember correctly, we'll do wine head of 10. We'll run that. Remember our original data set? We've gone through so many steps. Now we're going to go back to the original data. And we can see here we have our top 10 on the list. Only 2 of them make it as having high enough quality wine for us to be interested in them. And then let's go ahead and create some data here. We'll call it x new equals, and this is important. This data has to be, we just kind of randomly selected some data. It looks an awful lot like some of the other numbers on here, which is what it should look like. And so we have our x new equals 7.3.58 and so on. And then it is so important. This is where people forget this step. X new equals sc. Remember sc? That was our standard scalar variable we created. If we go right back up here, before we did anything else, we created an sc, we fit it, and we transformed it. And then we need to do what? Transform the data we're going to feed in. So we're going to go back down here and we're going to transform our x new. And then we were going to go ahead and use the, where are we at? Here we go. Our random forest. And if you remember, all it is our RFC predict model right there. Let's go ahead and just grab that down here. And so our y new equals, here's our RFC predict. We're going to do our x new in, and then it's kind of nice to know what it actually puts out. So according to this, it should print out what our prediction is for this wine. And, oh, it's a bad wine. Okay, so we didn't pick out a good wine for our X new. And that should be expected. Most of the wine, if you remember correctly, only a small percentage of the wine met our quality requirements. So we can look at this and say, oh, we'll have to try another wine out, which is fine by me because I like to try out new wines, and I certainly have a collection of old wine bottles, and very few of them match. But you can see here we've gone through the whole process. Just a quick rehash. We had our imports. We touched a lot on the sklearn, our random forest, our SVM, and our MLP classifier. So we had our support vector classifier, we had our random forest, and we have our neural network, 3 of the top used classifiers in the sklearn system. And we also have our confusion matrix and our classification report, which we used, our standard scaler for scaling it, and our label encoder. And of course we needed to go ahead and split our data up in our mplot line train. And we explored the data in here for null values. We set up our quality into bins. We took a look at the data and what we actually have and put a nice little plot to show our quality, what we're looking at. And then we went through our 3 different models. And it's always interesting because you spend so much time getting to these models, and then you kind of go through the models and play with them until you get the best training on there without becoming biased. That's always a challenge, is to not overtrain your data to the point where you're training it to fit the test value. And finally, we went ahead and actually used it and applied it to a new wine, which unfortunately didn't make the cut. It's going to be the one that we drink a glass out of and save the rest for cooking. Of course, that's according to the random forest on there because we used the best model that it came up with.
So let's begin. I'll be coding on PyCharm today, and the first library that we look into is the OS library, which stands for operating system. So to use the OS library, first we need to import it. So say import OS. Now in here, I'll have 2 functions. I'll just demonstrate 2 of the most common functions that you can utilize from the OS library. First one is to extract the current working directory. Create a function, and I'll have a variable CWD, which stands for current working directory. Now this variable will store the return value from a function which retrieves the current working library. So you say os.get CWD, and that is it. 1 line, and you have your present directory stored in a variable CWD. So I'll print this out, and that's our first function. So out here, I'll call the function So now we can run our program. So this is our current directory. You can see the users within the user, my particular username, and PyCharm projects /demo is this particular project under PyCharm. Okay, so that is our first function. Let's have a look at the second one. Now I'll demonstrate how you can retrieve the path of a particular file. So create another function here, and to this function I'll pass a file name. Now in here have another variable, I say path, which holds the value of the path that this file is stored in. And to retrieve that, you say os.path.apps_path, which stands for absolute path. Now you know there are two types of paths. There's the absolute and the relative path name. The absolute path name is, it gives the path name right from your C drive or D drive, whichever drive it belongs to. So the relative path name is the path respective to our current working directory. Now I'll have a variable file name out here, which will hold the name of my file whose path I need to find out. So I say sample.txt, and then I'll pass this file name to my function file path. And that's it. Now let's run our code. Okay, so we have not printed the value out. Let's do that. Print path. Run your code again. The first function that we called is to retrieve our current working directory, and the second function is to retrieve the path of this file sample.txt, and this is the right path. This is exactly where I've stored my file. So all's good. So those are the two most common functions that you use with the library or the module OS. There are quite a lot more which you can definitely check out. So next we look into the time module. So as usual, first import the module. Now before I show you a few functions in the time module, you need to understand what epoch is. So 1st January of the year 1970 is the starting point of a certain timeline, and epoch time is basically the number of seconds that's passed since 1st January of 1970. So to get your epoch time, use the function time.timeoff, and I'll store the value of this function returns the epoch time, and I'll store it in a variable ppc. Print that out. So that's the number of seconds that has passed as of right now since 1st January 1970. Now obviously this has no meaning to us. So what we do is we'll convert this to a format that means something to us. And for that purpose we use the function local time. So I create a variable local time and use the function local time, to which you pass the EPC variable. Now print out local time. So as you see here, now we actually have numbers that make sense to us. We are in the year 2019, the third month, which is March, date is 18, 12 hours, 42 minutes, 47 seconds. So this is something we can actually decipher. Now again, this is a structure. It's not in our traditional formatted way. So if you want to extract certain information from this structure, you can easily do it saying local time, that you use the variable, and then just use these keys in here to extract that particular value. For example, I want to extract the year. So I say tm_year, print that, and you see here the year alone is extracted. Now if I want the entire thing to be displayed in a more formatted way, that's exactly what we have the function ctime for. For that you say print and use the function ctime. Again, to this you need to pass the epoch value, that's EPC, run our program. So now you see we have it in a more formatted way, Monday, March 18th. So we even got the day of the week in here. So those are the basic things you can do with the time module. Let's move on to our next module. So the next module we'll look at is the SMTP module. Now just like HTTP, SMTP is also a protocol. This is a protocol for sending emails. So it stands for Simple Mail Transfer Protocol. So first we'll import SMTP lib. Now in this demo, what we'll be doing is, of course, we'll be sending out an email. So we'll send an email to someone's email ID through Python. Now obviously Python itself cannot send an email out. What you have to do is you'll be accessing a domain. So you'll give the username and password for this domain, and you'll put in commands here such that it automates the process of sending a mail from that particular domain to another email ID. So first we need to set a domain and a port. And for that we use the function smtp_lib.smtp, and this takes 2 arguments. The first argument is our domain name. Now the domain name is basically like if you're using Gmail, it'll be smtp.gmail.com. If you're using Hotmail, it would be smtp.hotmail.com and so on. So I'll be using gmail.gmail.com, and the second argument is the port number, which is generally 587. Now 587 is the standard port number according to the standard encryption standard, which is TLS. Now that you have set the domain and the port number, the next thing you need to do is make the servers communicate with one another. That is basically the sender server telling the receiver server, hi, I'm present here, and the receiver server gives an appropriate response. Now in here we'll be using smtp.ehlo instead of hello. That is basically just an extended version of hello. It adds a few additional features to your SMTP. Now before that, we need a variable into which we'll store the object returned by this function. So I'll have SMTP obj. So that SMTP is the object through which we'll be referencing our domain and port number. So now you say SMTP obj.ehlo. Now the next thing we do is we'll put our SMTP in the TLS mode. So for that we use the function start TLS. So as I mentioned before, guys, this port number is the standard port number for TLS. So now it must be clear why we are using this particular port number. It's because we are using the TLS connection. So you say start. Okay, so now our connection setup account through which we'll be sending out the email. So you say smtp obj.login, and now you pass 2 parameters in here. The first is of course the email ID, and that is followed by your password. So to create our file, first we need to import the OS package, and in particular we need to import path library from the OS package. Now create function, and to this function I'll be passing the path at which I'll create my new file. So now before you create the file, you actually need to check if the file is already present. So you say if not, path.isFile dest. So you're passing the destination here to this function .isFile. And if your file is already present, then this portion of the code will be skipped because our entire program is for building, because the entire purpose of our program is to build a file, which we do not need to do if it already exists. Now in here, you say open dest, w. So guys, this function actually returns true only if this file is present, and this particular path is actually a file. So suppose this destination, whatever passed to dest, is present but it's a folder, not a file, we'll still enter this particular block. And so in here what you do is you open this folder in write mode and say f.write welcome to Python. So let's assume destination was a folder and not a file. You enter this block here. A file is created which is opened in the write mode, and within that file you enter the content welcome to Python scripting. Now you're ready to close the file. Now outside here I'll assign the path to destination. So this is the path, guys. I want to create this file sample.txt under this path. So basically along with the path name where you're creating your file, you also pass the file name, and then you call this function create file passing dest, and once your file is created you can just print out file created, right? Okay, now we need to run our code. Well, we don't need a input from the user, so we say print. So we print file created. Now let's run our code. According to the statement here, there's no error. Our program executed completely and created a file. So now let's check if this actually worked. So I go to my desktop. This is the folder where sample should have been created, and yes, it is. We'll open the file, and as you can see, the content too matches. So we were successfully able to automate the creation of a file. So the first argument is the email ID. So you have the email ID within quotes, put it within single quotes, and then your second is the password for this particular ID, and that's my password. So with these credentials, your SMTP will basically log in to your account and then use the services of this account to send to send an email. Now the next function that will be used, the next function that we'll be using is the one that basically sends your email out. So that's called send mail, and in here you'll put in your to and from email IDs. Okay. Next is the ID that we are sending the email to. Next is the from ID. I'll be sending an email to the ID enj2 Simplilearn, again gmail.com. Now the third argument to this function is the message that we'll be actually sending. So I'll be sending a very short message here. The first thing you enter is the subject, and the subject would be SMTP check. And then to move on to the next line, which is basically the body of your message, put in /n. This is a test email, and that's it. That's the body of my message with the subject preceding it. And the last thing we need to do is we will quit the SMT connection. So once your mail sent out, we'll close the connection. This terminates the program. Let's now run this code. So programs run. Now to check if this actually worked, we need to go open our account at ANJ2 Simplilearn and check if this particular message is present in our inbox. So guys, this is the mailbox that I send the email from, and this is the one that I send the email to. As you can see here, ANJ2 Simplilearn, and here is the message which has been sent. So we checked out 3 libraries in Python: the OS library, the SMTP, and the time library. Next, we'll check out a few programs which determine things at runtime. So now I'm going to write a function, func1, and this function will receive a few arguments. I'll fill in the space later on. Now all this function does is it prints out the various arguments that it receives. So suppose the arguments are stored in I, and what you pass here is also I. So you pass a number to this function, and this function prints out that number. So out here we'll be calling the function and passing a value to it, say 10. Now what if I want to pass varying number of arguments? So say 10, 20, 30 for this particular run, and maybe the next run I want to pass 4 arguments. I want to pass 42. So how do we make this function flexible enough that it accepts any number of arguments and prints these out? That is where we have args come in. So when you put this within the brackets, what happens is that your function will take any number of arguments that you pass to it and store it in the variable args. So now to print out each value that's passed to this function, you take a for loop and you iterate that over args, and then one by one you can print each of these values out. So let's run this program now, and as you see, 10, 20, 30, 40, each of them have been printed out in a separate line. And the beauty with this function is you can change the number of values that you print. In fact, you can even give in different types of argument. So I have all integers here followed by a string, and it all works. So that is where you use the variable args. Now, similarly, we have another variable which is used in this argument space, which is called quargs. So that's KWARGS, and you always precede this with 2 stars, 2 asterisks. So far we looked at how a function can accept variable number of arguments. Now we look into how the function can do this while accepting the arguments as values to labels. So what I mean here is, instead of just passing 10, 20, 30, what if I want to pass A equal to 10, B equal to 20, C equal to 30, and again the number of such pairs could vary. So in that case, we have args for the varying part and quarks for the label part. So what you do here, in the similar manner, you will have a for loop which will iterate through quarks, and we want to extract every item in it. So we say items and print out I. Run this code, and as you can see here, so you get all the pairs printed out. So we saw how Python allows a function to determine the number of arguments it receives at runtime instead of it being fixed beforehand itself. Now let's move on to another program which demonstrates automation, and that is creation of a file. So this is one of the most common and the most basic things that you come across when you're learning scripting, not just in Python but any language. So far we saw how a function works. We have a function name, and within it we have some code to perform a certain function. Now functions in Python can also be nested, and that is what we look at now. So I'll first create a function func1, and in here I'll have a variable, say x, which is equal to 10, and within this function I'll create another function, so that will be the nested function func2, and to func2 I'll pass x, and within func2 I'll just increment x by 1 and return this value. So here's the thing, now within function 1 we need to have a call to function 2, so you say func2 and you pass x to it, and out here we'll call function 1. So result equal to func1, print out the value of result. So what happens here is you're calling the function func1, control goes in here, x is assigned the value 10, and over here there's a definition for func2, but right now it's skipped. It moves on to this return line. Now in the return line you're basically returning func2. So what that does is it'll call function 2 along with the argument x, and function 2 returns x plus 1. So where will this value be returned? Of course it will be returned to the statement from where the call is made. So that is still within function 1, and that means function 1 will return the value that function 2 is returning. So what we have in result would be 10 plus 1, which is 11. Let's now run this code. So as you see here, 10 plus 1, 11 is what's passed. So that is how nested functions work. Now, why are nested functions important? They are important to understand the concept of how functions can also be passed as an object in Python and why we would do so. So I'll delete this entire code, create a function func1 once again, and in here I'll print this is first function. So that's func1. Now within function 1, I'll have my second function, the nested function, and within the nested function, I'll print out this is the nested function, and out here, I'll have a third function, which I'll call the outer function, which will print out this is the outer function. Now what I can do here is instead of directly making a call to outer function, so sometimes what happens is you do not want to make a direct call to a particular function. You want to make a direct call to say function A, and through function A, you want to call a function B or C. So for that, what you do is you make a call to func1, and as an argument to func1, you passed another function name as an object. So I pass outer func. So as you see here, guys, outer func is essentially a function, but I'm passing this function as an object to func1. So func1 will receive this function. I'll store that in a variable called func. Maybe called func will also be passed to our nested function, and within the nested function, we'll make a call to this passed function. And of course, finally, the return statement where we'll be calling our nested function. Let's now run this code. Our outer function was not called, and that's because we did not put these parentheses here, which does not really make it a call statement. Let's run this code now. And as you see, all our three functions were called, but through a call statement for just one. So we just called our outer function func1, passed the other outer function as an argument to this, and that took care of executing all the three functions that we have. This kind of a situation does not come handy very often, but in certain applications where you need to decide which function needs to be executed at runtime, then having the capability of passing a function name as an object comes really helpful. So we saw how you can create functions at runtime. Now Python also allows you to create classes at runtime. So let's check that out. Now the term for creating class at runtime is called factory. So what you do here is you have to basically create the skeleton or just write down the basic description for all your possible classes. So you mention the class that it inherits from and the attributes associated with this classes, but you do not create it. You just give that sort of definition, and then later you'll have certain expressions to evaluate which class is to be created depending on certain situations. So let's begin creating the definition for our classes. So my first class would be a base class, of course. So you say type base class, and this will inherit from the mother of all classes, which is the objects class, and following this you'll have list of all the attributes associated with this class. So I have no attributes associated with my base class. Now the second class I create, C1, will inherit from my base class, which is B, and with this class C1 we'll have an attribute named val associated to it, to which we'll assign the value 5. Now my third class C2 will be about the same thing as C1, just that this time my attribute val will have a different value, 10, just so we can differentiate between the two, and of course our class name would be C2. Now we'll have a function, say def class creator, and to this I'll pass a variable, say bool. Now if the variable is true, you say return C1, and that will essentially create your class C1. Else return C2, which will create class C2. Now outside here, I'll call the class creator function, and I'll call it with both the values true and false so we can see the difference. Now of course this just creates a class, so to extract an attribute value, which is how we'll be able to differentiate between the creation of the both classes, say dot attribute name, which is val in our case, and in a similar manner we'll call class creator again, but this time with false, extract the value. So let's run the code now. So as you can see here guys, first time we passed true to class creator, and if it is true, it's creating class C1, which is this, and that has the value 5 associated with attribute val. Similarly, when we pass false, it creates C2, which has the value 10 associated with the attribute val. So that's how Python allows you to create classes even during runtime. So now that we looked into that, we are back to our nested functions, or program in which we call functions as objects. Now suppose I want to call this outer function alone. Now the question is this the only way of calling the outer function within the func1? What I mean is func1 is basically your wrapper function right now, and every function that's called through func1 comes inside this. So I want to call all the functions in the same manner, in the same serial as before, but is there an easy way to do this? Well, yes, there is. This is where decorators come handy. So just on top of outer func, if I say at func1, that way this allows me to call outer object through func1, but just with this one statement in this format. So I just say outer func, but now that I have added a decorator of func1, although I'm calling outer func, it'll be called through func1 just as before. Let's run this code, and as you see here, your func1 has been called first, and outer func has just been passed as an argument to func1. So that is what decorators basically do. They allow you to change the operation or the functionality of a function. Now this is just one use case for a decorator. Decorators are also used a lot to differentiate between static and class methods. So that will be our next program. Now both class method and static method are bound to the class. The main difference between both of them being that a class method can actually change the state of a class, while a static method is not allowed to do so. But here we are not looking into what static and what class methods are, but how you can specify them. So for that purpose, first I'll create a class demo, and I'll have two methods in here. My first method, add1, which will take the argument x and return x plus 1. And my second method is add2, which again will take x and return x plus 2. Now I want my first method to be a class method and the second to be a static method. Now before we put in the decorators, one thing you need to remember is the class method always has self passed as an argument to it, while a static method will not have this argument self. So we remove that. Now how do you specify which method is class and static? That is where decorators come in. You simply have to say @class method, and that will define the first method as a class method. Similar way, @static method, and it's done. That's how you define both of them. Now to call class and static method, as I mentioned earlier, your class method is bound to the class. So you can just say print of class name is demo. So demo.add1, pass 10 there. That's good enough. Now our second, which is a static method, is also bound to a class, but to be more specific, it's bound to the object of the class. So you can't directly say demo.add2. You need to first create an object of demo, and then through the object you call a static method. So if you're a programmer, you know this is how static methods are always called, especially in Java, where we really take advantage of this feature. So create an object of demo and then use obj, call your static method. method, add to, pass 10 in there, and there you go. That's how you differentiate between class and static methods. Let's run the program. There's an error here, which is I made a small spelling mistake. It's capital O. Run the code now. So the first function, which is a class method, increments x value by 1. So that's 11. And our second method, add to, gives 12. The next thing we'll be looking at is simple GUIs with Python. Now for that, we'll be using a module called tkinter. So let's import that. Import ttk, which is only that particular library we need from this particular package. Sorry, it's tkinter, not ttkinter. Now first we need to create an object of tkinter type. So this is the instantiation of our object. Now first thing, we need to create a frame. So a frame is like this top level object, and all the widgets that you will be adding to the frame will be organized in a block format. That's why we have the frame, and to this you obviously pass your tk object. Those are the first two basic things. Now we are ready to create our widget. So here I'll be creating a very simple GUI which has a click me button and a label. It does not really perform anything. This is just to show you a basic demo on tkinter. You can explore this further. There are a lot of materials online. So first thing, we will be creating a label. So for the label, of course, the label would be a text. So we'll have a variable label text which will be initialized to some value of the type string var. So why we are not simply giving the value here? It's because when we are creating widgets, we often want to change the text that appears, or in some cases the text is given by the user and we need to accept that. So the only thing we can specify there is the type of the value that is given by the user, or the type of the value that will appear on the widget. So this is where we mention the type. So our type would be string var. Now we'll create a label object. So we say label, and it'll be within our frame, and what will appear as this label, the text that will appear here, that's what we need to specify. So we say text variable and label text. Okay, so I forgot to import some libraries. So I'll just import the entire tkinter package here. Okay, so we created our label. Now we can give a value to this label text. To give a value to label text, you say label text dot set, and in here I'll enter my string. This is a label. Now our second widget would be a simple click me button. So button equal to button, and the button will be within our frame, and the text that will appear on the button would be click me, and that's it. So that's all the widgets we are having here. Now every widget is put into a block format, including the frame. So for that we use the pack function. There are other formats too, and various functions to take care of these. For example, if you say label.grid and button.grid, the widgets would be put in a table like format. So now that all our widgets are inserted into our frame, we can call the main loop. So what is the main loop? Now once everything for your application is created and you say let's go, let's execute this application, that's when you call the main loop. This creates an infinite loop. So your program runs and it's running an infinite loop until the user terminates it. So over here we are basically displaying a user interface. Therefore main loop is the essential feature that your GUI should have. You cannot have a GUI without running your main loop. Now let's run this program. So as you see here guys, this pop-up appeared. This is the label, click me. Of course our button is clickable, but it does not do anything. We didn't add any functionality to it. Now see, as I said before, main loop puts your program into an infinite loop until the user interferes with this execution. So your loop is still running. It'll run for as long as you do nothing. You don't touch this. Now to terminate this, the user needs to go ahead and close it like that. So that is GUI with Python. So guys, that's pretty much it. We have covered most of scripting with Python.
You can actually read a little bit about it. Currently, Beautiful Soup 4 is the current version. If you don't remember the full website for it, you can always do what I do, which is go over and do a search for Beautiful Soup official site. And it almost always comes up right at the top, and you click on there and it'll take you to the crummy.com software site for Beautiful Soup. Now, we're going to use our whatever Python interface you want, IDE. I'm going to use Jupyter Lab, which is built on Jupyter Notebook through Anaconda. So when I open up my Anaconda Navigator, you'll see that I have my different tools available. Again, you might be using a different editor, and that's okay. You might be in PyCharm or something like that, where you don't need need to do this. And Jupyter Lab is Jupyter Notebook with added tabs and some added features. It's basically in beta testing, so it's got a few little glitches when you're saving things and moving between projects, but for the most part it's a great upgrade to the Jupyter Notebook, and you can use them together. So you don't have to, it's built on Jupyter Notebook, so anything you do in Jupyter Notebook you can open up in Jupyter Lab. And the first thing we need to do is we need to go ahead, in this case I'm going under my environments since it partitions the environments out, and I'm going to open up a terminal window. We have to install some packages in here to work with. Now there's a lot of choices on this. Because of the simplicity, will be using conda install. Now you can use pip install for the same thing, and we're going to install our Beautiful Soup 4. And you have to type out the whole thing, Beautiful Soup 4, and you can use a pip install if you're using a different environment. And I am using Python version 3.6, although according to Beautiful Soup they also work on 3.7, all the way from 2.7 through all of 3x. Now according to the Beautiful Soup website, the Beautiful Soup 4 works on anything, you can install on anything from Python 2.7 all the way through any of the Python 3 versions. This just happens to be Python 3.6 because there's a lot of other packages that don't work on 3.7 yet. And we'll go ahead and run this install on here and let it go through its environmental setup. And of course with conda, it goes in there and finds all the dependencies. Pip doesn't do as much as far as finding dependencies, but you know exactly what's on there with pip. So if you're doing a huge distribution, you probably want to use your pip install so you can track what's going on there. With the conda, I like to just let it take over since this isn't a major distributed package going out. Another quick note between pip and conda is that if you start on a project in one of these environments and you're using pip in there, stick with pip. If you're using conda, stick with conda. They track the packages and you can run into some issues where they're not tracking the same packages and something gets overwritten. So it's important to stay very consistent with your install on your environments. And we'll also need to go ahead and install our NumPy environment and our pandas on here. So go ahead and do that. If you haven't added those packages in, go ahead and install those into your environment that you're working in. And of course pandas is just simply install pandas. And let's just install a couple more packages. In this case, let's get our install our matplot library, because we're going to plot at the end since we're going to be collecting data. And for this project, that will be all the packages we'll need. So we can go ahead and close out of our installer or whatever setup you have. And we'll go back to home and we'll just launch our Jupyter Lab, and that will open up in our browser window. Now, if you're coming from Jupyter Notebooks and first time in Lab, we can go ahead and just create our first notebook, Python 3. You can also do it under File, Launcher, and you'll see New Notebook. It automatically opens up and we can just click right on there. It'll pop open on the left, and I'll right click this and we'll rename this. We'll rename it just Beautiful. And it is a IPyNB file on there. So that should look familiar because that's the Jupyter Notebook file. This is a new one. Now, I have multiple tabs, and in the past I usually hid this on the other computer, all my notes for the lesson today. But this is my notes going down, and we'll go ahead and just start going through this and see what it looks like to do a data pull from front to end and see how that works as a data scientist pulling that information in from the website. And the first thing I want to do is I want to go ahead and close this side window. That way it get the nice full screen. And we can also up the size a little bit. One of the wonderful things about working in a browser window, just do that Control+ thing. The packages we talked about is pandas. So we imported our pandas if you haven't already. That's our data frame. If you haven't done our pandas tutorial, definitely worthy of the time to go through there and understand pandas because it's such a powerful tool. This basically turns your data into a spreadsheet data frame. Our NumPy is our number array, so it kind of works with pandas very closely as far as manipulating data in arrays. Matplot, we want to go ahead and bring that in, our PLT, so that we can plot the data at the end. And this line right here that says Matplot library inline is for the Jupyter Notebook specifically. It tells it to print that on this page. A lot of the newer versions don't actually require to have that line. They'll still print it on the page. But you should still include that if you're in the Jupyter Lab setup. And then we have our URL library.request. We're going to import URL open for opening up the website. And then we have our BS4, that's your Beautiful Soup 4. We're going to import Beautiful Soup. And then our last one is our RE. That is for manipulating our regular expressions. So when we get to that part of importing our data, we have to do a lot of reformatting so it's something we can use. And the RE is one of those tools. We'll go ahead and run this and just bring all that in. So this is all imported. All these packages are now into our web scraping program program we're going to run. Now, if we're going to dive in and pull data, we should have a nice website to pull from. And let's go ahead and we'll use the HubberTiming.com results for the 2018 Martin Luther King race. And if we take this, you can actually just take this, where did we get this from? Well, you can go in here and find the website you're going to scrape from, and you'll see right here it says you just copy that link right in there, that HTTP. And this is the website that we're looking at. You can see right here all the information that we're looking at. Let's say we wanted to run some statistics on this. It sure would be nice to be able to pull it off of here. And if they don't have a direct API, that means we need to pull it from their website. Some of these will have a download, although if you've ever done it where you have a download click and maybe you're paging through 100 websites. In one case, I was pulling all the different United States bills that are passed to track who voted on them for a project. And you can imagine that there's hundreds and hundreds of those, thousands of these documents that they voted on, who voted on it. It goes through the Senate, it goes back to the Congress. So I opened up a website, pull all the links off of there that match a certain criteria, and we'll look at that in just a minute, how we go through the HTML. And then I had to reformat them, or I could hand download each one at a time, which would just be a nightmare. So it's nice to automate it. In this case, we're going to be pulling up this chart, and we want to figure out how to pull this chart off of this website. And so when we go back into our Jupyter notebook, I've got my URL, just our name for it, and it's just a string. That's all this is. Nothing fancy there. You'll notice that on the slashes, we now have // You can do a single forward, and HTTP is a double forward. This is just how you have to switch it to match setup in there. And then it's going to go ahead and use the HTML equals URL open URL. And that's from our URL library request. So it's opening a link to that website, or at least pointing to it. And if we run this just sets it up. So this is all set up. And then once we've done our setup, let's go ahead and create an object called soup. This will be, and if you remember up here, here's our beautiful soup that we imported from the BS4. And this is the package that we're working with. And so we're going to do our beautiful soup on here. And on this, we need to go ahead and send it our HTML so it knows what it's opening. And then the second part is we have to tell it how the format is coming in. And the most common one for your HTML polls is an LXML setup. And so almost all of them you'll end up using the LXML. There's a few other options. And because this is so common in the newer versions, a lot of times they just leave it out just because it's already on the default. We'll go ahead and leave it in here just to remind us that it's there, and we'll go ahead and run that. And on the newer versions, they actually default it to the XML setup and the HTML. We'll just leave it out and call it HTML. So it's just going to pull from this URL. And when we run that on here, we've now created an object soup that has pulled the website into it. So soup contains the information along with information on that website and what's going on. So let's just go over what we did real quick before we start digging into the actual soup, before we start scooping out stuff. We imported our different modules that we're going to use with our package, specifically the beautiful soup. We did install the beautiful soup. If I remember correctly, you have to call it beautiful soup 4 specifically, so it knows what you're bringing in. And this line right here is very key. From BS4, because that's how it installs the module, we're importing our beautiful soup. And then we found our URL. In this case, we're going to go pull information from the Martin Luther King Dream Run. And then we set our HTML to our URL open URL. And you can see right here we imported that. So here's our URL.request, import URL open. So we're requesting a connection. And once we send that connection into the beautiful soup, it creates an object called soup. And then this one, of course, we chose soup just because it goes with beautiful soup. I guess we could have chosen beautiful. And now we can start extracting information from our website because we've pulled it down onto our computer under soup. And we can start by looking at the title of the website, soup.title. And if we print title.text, you'll see this a lot in beautiful soup because title contains all kinds of information, and if we want just the text from that title, you add the .text on the end. And you can see right here we have our 2018 MLK Dream Run 5K race results. If you look at the tab, that's the actual title up here, 2018 MLK Dream Run 5K race. That's what the title is on the website. And then you might be curious, what's in title? What's the whole title that it's storing up there? Well, let's go ahead and print it out. Here's print title and print print title.text. And when we run that, you can see it has the HTML tags title on it, and then the / title to end it. And so we're really just pulling off this piece of the HTML code, and then we look at the text inside that particular part of the HTML. And earlier I mentioned links. What if you want to get all the links off this page? Well, that would be fun. We could do soup dot, and we'll do find _ all, put this in bracket, and then quotation marks, we'll go ahead and put A. A is the key find, and you'll start seeing a div and all the different options you have for finding these entities in a website. And then let's go ahead and just print our links, and you can see here that it now shows all the different links in here that are marked by A, because we did a find all A. And then we can also, because this is a little bit hard to pull off the H reference, so we can also add in our find all, fine tune that. In this case, the H reference equals true. We'll actually filter that out. And then finally, we might do a for link in links, and we can simply do something like this for each link. We want to actually find the H reference, because we know there's an H reference in it. And if I run this, you can see it just comes through and prints them out one at a time. Some of these are really useful. So you might be looking for something that has HTTPS in it, and you know that's a link running to something else. Or you might be looking for the mail to tag, so you know that's all the mail addresses. But either way, you can easily find all the links in your HTML document that you're paging through. And of course, any packages that have evolved over time, you can also do link.get hrefs, which should do the same thing as our other format. And you can see it certainly does. We get the same printout up here. In this particular case, we really want to get the data off the page. So let's go ahead and do that. Let's see what that looks like. And in data, let's call it all rows. There we go. Equals, and then we have our soup.find _ all. There's our brackets. And then if we're looking for each row in a database, you'll remember your HTML code, we're looking for the tag tr. So we want to find all tr. And we can take this, and let's go ahead and just take all our rows and do a print all rows. And about this time, you're going to guess that we're going to get a huge amount of information just dumped onto our page. And sure enough, we do. If you look at this, it just kind of goes on forever. But this is an array. Each row is considered an array. So because of that, we can do something simply as putting brackets and just print the first. Let's do the first 5 rows. So from beginning to 5. And you can see here's our first 5 rows on here. I sometimes like to just do, let's just do row 0. And we see that row 0 is finishers. Finishers 191. And just out of curiosity, if that's 0, what's row 1? Mail. Okay, so we're starting to see titles going across here. So if we come up here and we do rows, we did what, up to 10? Let's just take a look and see what 10 does again. And just take a look at that information that comes across. Place, bib, name, gender, age, city, state, chip paste, gender, and so on. So it comes all the way down here. We kind of have an ending right here, and then we have 1, and then we actually, it looks like we start to have information. So we have our 1, our 1191, Max Randolph, that must be the name, Mel 29, and so on. You can start seeing how the information starts getting displayed going down. So the next thing we want to do with this, and I'll go back up here and just edit the space we're in so it starts to make a little bit more sense. Keep it all together. And so we want to do for each row in all rows, we're looking at, what information are we looking at? Well, we have our TH up here, that's the header, our TD down here, which looks like the individual information. And we really are looking for the actual data. So we're looking for our TD tags in the rows. And we can do that because remember when it stores the row, it also stores the tags underneath that. So all rows have all the different tags in it. And you can see right here as you print each one of those out. And so when we look at each row, we can create another variable and we'll call it row list. And we'll set this equal to, in this case, row, because we've already pulled all the rows out of soup. So now we want to find for each row, and in there we want to find our TD. And if we go ahead and just print, I'm going to do it, if you notice I changed the indent, so I'm just going to print row list. What this does is the last value to go into row list, our last row is going to print now. And of course make sure you have an underscore instead of a period when you're typing. So row.find _ all TD, and if we print the last row, you can see I have all the data coming across here. We have our 191, our 1216, Zuma, Oakcho, Showa, I hope I said that right, female, I believe that's age 40, and so on. And then we can take our row list, and there's a lot of things we can do with the row list. But we'll do let's do object, or let's just do cell in row list. And so we're going to look at each cell, because this is, if you look at this, they have commas separated between the different objects. And then we're going to go ahead and print cell.text. Let's just take a look and see what that looks like. And we can see here for each row we get 191. There's our 191. There's our 1216, 1216, our individual who's in the race, and so forth all the way down for those different settings. And let's go ahead and create a new variable up here. We'll call this all, let's just call it data. We'll keep it simple. So here's our data. And then we have our row. We take our row and we break it up into individual cells. So we'll call this data row, and we'll set this empty to an empty row. And we're going to take our cells, tab this, and we know that each cell generates a text. And so what we want to do is I want to take my data row, let's just replace that. Let's take our data row and let's append our cell.text. So I'm going to add each row is going to be a row of the different text on here. And then once I create each row, I want my data, which is going to be everything, to append each row. And here's our data row. And then if we go ahead and come down here, and let's just print data. Now, if we were working with large data, we'd be very careful about just throwing all our data on the page. But you can see here, we throw the data on the page and we get finishers, 199, male, 78, female, 113, 1, and so on. And if you look at this, this is the headers on the file. We have finishers, male, female. It's just like some general statistics on the first one. And then we have actually an empty data set, and then we have our data that continues, which the actual information we're looking for. So we have 1, 1191, Max Randolph, male, 29, Washington, D.C., runtime, 1 of 78, and so on here. So we could really quickly get rid of that. A number of different ways to do that. One of them is just we're going to set, if we do data 2 on, we should get rid of everything, but we want to keep Randolph, so make sure Randolph is in there. Oh, we lost Randolph. Let's try 1 on. There we go. There's Max Randolph on there. So we can just simply redo our data on here, and we can do data. Probably want to do it in all rows from 1 on, but I'm just going to do my data equals data 1 on down here. There's reasons to split it this way. In data science, sometimes you don't want to touch the original data in case you need it, in case we do need the first row. So we'll put it down here, and maybe we'll just call this titles. Titles equals data of 0. And so we could do something here where we print, and we'll print up our titles, and we'll print our data. In this case, instead of 1 on, let's go -2. Let's look at the last 2 rows of data. So here we have our titles, and for some reason just put in finishers of 191. I was expecting a little bit more up there. And we have our last couple people, and they look like the data on these looks just fine on here. Turns out this is just some generic statistics up here. So we'll get rid of titles completely. It doesn't really do us any good. But we know that data comes in here, and we can look at our data and look at the very end of the data too, the -2 to the end. And we can see it pulls the data in pretty good. We don't have anything too funky in here we're looking at. It looks pretty clean. Now you got to be a little careful, because at some point we might have to come back here and clean up the data if we get an error for running data analysis. We might find out there's some unusual characters or something is misset in the data itself. And you also notice that everything is a string. So when we're bringing it in, we might have to do some conversions to test it out and convert them to whatever kind of data format we're working with. So at this time, we want to go ahead and bring in our pandas. And let's go ahead and call this df for data frame. We'll set it equal to, and if you remember correctly, we imported pandas as PD, and that's standard. You'll see that in most code examples where they import pandas as PD, and it is capital D, capital F for data frame. And we're just going to bring in our data. That's what we called it on here. And let's take this and we'll print. Now, when you're working with data frames, you're usually talking large amounts of data. And so you almost never want to print the whole data frame out. We're going to go ahead and do that anyway, just so we can see what that looks like. And you can see in here, it brings in our data frame coming in here. We just have a mess of information. This is our data. Let's go ahead and print df and see what that looks like in the data frame. And this is nice because it organizes it into a very easy to read table. And we have, they set the label 0, 1, 2, 3, 4, 5, 6, and so on. And then we have each row. We have Mel, 78, none, 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 none. Going across, when we get all the way down here, we'll see Max Randall about number 3. And the first thing this does is this flags me that I brought in a bunch of information up here that we really didn't want. It's from 3 on that we want. And we can clean this up in one of 2 ways. We can try to clean it up under the data, or we can clean it up under the data frame, depending on what it is we're trying to do. And so to fix this, I want to go ahead and just change it up here in the actual data pull in. We don't need that information. So I'll rerun it, reload our data from 4 on. And then when I run this, we see we have Max Randolph is right at the top of the list like he should be, and we have all the data going down. Now with the data frame, remember I said we don't usually print the whole data frame. We'll go ahead and do df.head, and this prints the first 5 rows, and you can see that we have 13 columns. Here's Max Randall all the way to Theo Kinman, and I usually also print df tell. And the reason I like to do these particular 2 setups, and I'm going to change it just to 2 rows, because you can do that, you can print as many rows as you want, is it's good to look at the first part and the end, because those are usually where you have extra data brought in, something's messed up. And you can also see that we have 190 rows in here. And it comes in with our Zulma, Lisha, and they're both on here on the list. So now we have a nice data frame, columns and rows. We can easily look at it, we can see the setup on here, and we can look at the names and everything. Now at some point you might be looking at these individual columns and find different information that needs to be re-edited. If you can, you try to do it with the whole column under pandas. You can, up in the upper part of the code where you went from cell to cell or row to row, you could look at individual cells, maybe find a marker in that cell that's something specific, like remove all colons or semicolons or something in there, or brackets. So there's a lot of options in there. But you'll find that this one actually comes in pretty clean on here all the way down. And the next thing we really want to do is we want to look at the headers. I don't know about you, but it doesn't make any sense to me when I have column 1, I don't know what 1191 is or 1080, need name Kaiser runner. I'm guessing that's column 2 is names. Third one, it looks like male or female, probably age, but I don't want to guess. I want this to bring in my column so I know exactly what I'm looking at. So how can we make Beautiful Soup do that for us? Well, let's take our column headers. We're going to set that equal to our soup find underscore all, and then we're going to look for our headers, our th files. And since we're in Jupyter Lab, in this case Jupyter Notebook, I can just type out column headers. If it's the last variable I have listed, it will automatically print it. So it's kind of a shorthand. And we can see right here we have place, I'm guessing that's bib, name, gender, age, city, state, chip time, chip pace, and so on. So we have all our headers right there. I shouldn't have to type them all in. And we'll go ahead and do it before. We'll go ahead and do a header list equals our empty array, and then we can do for column in column headers, and we can take our header list and just append. And what do we want? We want the text from the column, so we'll just do column.text. And then if we come down here and we print our header list, let's see what that looks like. If we did it right, we should get a nice list of all the different column headings we want. So we have place, bib, name, and so on. And then pandas, just because pandas is so cool, we can simply do df columns equals our header from our header list. We can simply set df columns set to df headers, and then if I print df.head, we'll take a look at that, and we'll see right here it has nicely placed our values on here. Place, bib, name, gender, age, and so on. So very quickly we've created this nice data frame. We have the data displayed in nice rows and columns and easy to read. And then as a data scientist, the first thing we want to know is the info. What is in these columns and rows and headers? And you see right here they all come up with non-null object. There's a big flag. So if I want to do anything with this, these are all coming through as strings or an object. I usually mean strings in this case, that they're a string variable. And we have, you can quickly read through this, 191 entries, date columns, total 14 columns. There's a total of 14 columns in the data, and it shows you all the different names and what type of column they are. And it's probably good also to look at the shape of the data. df.shape, we'll go ahead and just run that. You can see it's 191 by 14, 14 columns, 191 entries. This is more like the way you look at a NumPy array, 191 by 14 for the shape. And remember, this is a variable, so if I put it on, if it's the last variable or last value in the set of cells, Jupyter automatically prints it out. So if you're in a different IDE, you'd want to go ahead and use the print statement on here. And then one of the things you'd want to also go through, we'll create a second one, df2 equals df.dropNA. Now the axes is automatically equal to 0. So a lot of times you'll see something like axes equals 0, comma, how equals any. Axes equals 0 is default. That means we're looking at going down the rows. You could look at the column going across. Let's remove the how any because that's just going to confuse you. The axes is whether you're going down the columns or if you're looking at it row by row by row by row. Or you could be looking at it by column by column by column. This would drop any column and it would drop off the NA in any column. And how equals, and we want any. I always confuse all and any because they both start with A. All means that all of them have to be non-value, where any means that any of them can be there to drop it. So this would drop any column with a null value in it. But we want 0, and it'll drop any value with a null value. And then because 0 is always the default, we'll just leave it out. And then it's curious as to what the shape is now. Did we lose anything? Was there any null values in our df2 that we dropped from the df? And we'll go ahead and run that. And we see 191 and 14. So we didn't really drop anything. But it's always good to check. There's other ways you can also do, are there, let's see, any NAs? You can detect NAs in here. Null values, infinite values, that's another one you got to watch out for. We're working with data that we're going to do something with here in a minute. So you got to be a little careful also in the conversions. Are you going to convert something where people typed in weird characters to describe the data a certain way? So now we've got to this point where we have all our different columns, we have our different data, and at this point maybe you're asking, or maybe the shareholder of the company is asking, hey, can we look at the, based on the chip time, here's our chip time, can we plot that versus gender? How does gender versus chip time compare? And so we can do that. We can take that. And the first thing we look at is we say, hey, well, chip time came in as a string, and that's going to be an issue. Now, there's a number of ways you can change this. One of them is we could go all the way back up here where we created the data and find a way to tag it and say, hey, whenever this cell text, maybe instead of appending this, I noticed that anytime there's 2 colons in it, that's probably a time signature. And let's convert all the time signatures to date time field or whatever. A lot of times you don't get that. You don't get that option. And that's always a question in bringing in data. Whether you convert the data coming in at the beginning, or do you wait till you have it, open it up, and then convert it when you go to use it. We're going to go ahead and convert it after we got it into our data frame. So we have our df2 here. We've dropped all of our NAs. We have a shape. In fact, let's do this. Since there's no difference between df and df2, well, we'll just go ahead and use df2. So let's go ahead and take our df2, and we want to take that specific field and convert it into some kind of numerical value we can use. And let's add another column. A lot of times this is something you want to do is where you want to go ahead and keep all the original columns and just add a new column in there. And this new column is going to be based on the, if we remember correctly, we had chip time. That's what we're going to look at. Okay, we want chip time versus gender. If we go into our pandas, we find out we have pandas to delta, and this is actually time delta. And then we just want to take our df2, and we're going to use the chip time column. So this is going to say, hey, let's look at, let's convert everything in df2 chip time into a time delta format. That's the data type we're going to put it as. And we can go ahead and just run this. And if we go in here and we do info, df2, and we'll keep our, we're going to look at this particular column, but we want to keep it as a data frame. So this is a list of all the columns we want to look at. We'll just do .info on here and run that. And we do an info on that, you can see it's now a time delta 64 nanoseconds. Well, we really don't want nanoseconds. We actually probably want to do it in minutes. So let's take a look at that. And let's take this whole thing, df2. Let's just set the df2. We have our df2. This is a column we're working with here. And we can use the as type property in pandas. And so we can set this equal to df2. We'll take our same column in here, and we'll set it as type time delta second. So it's still a delta time here. So if I run this, you'll see that it still comes up as, where is it? Oh, it turns it into a float. So we're now at a float 64, so it's the number of seconds in that delta time. And then finally, we want to go ahead and turn that from seconds to, say, minutes. And you know, there's 60 seconds in minutes, and so now we divide by 60, we still have a float. We have our info that shows us as a float, and then we can go ahead and just do a print df2, and let's just keep it small. We don't want to look at all our data, we just want to do the head of it. And we run this, and you can see right here where we go to, it'll be the last one, here's our chip time in minutes. And a lot of times, just to make life easy for viewing, since we're only looking at this particular element, we can do chip time in minutes, and now we just see that, oops, we take off. We'll go ahead and take off our info. Done with that, and we'll run this, and you can see we have our minutes, 16.8 minutes, 17.51 minutes, and so on. It's a float number. Now keep in mind, this is 0.8. That's not 16 minutes and 80 seconds. That can always throw you if you're going through so many numbers you forget. So important to remember that. And we're also going to look at, the other one we're looking at is what? Gender. You want to look at gender to chip time in minutes. And so we can see here under the head we get male, 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 and a number of different setups. And let's switch this to tail real quick and just look at the end of it. And here we have female, female, male, female, female. So we have two different genders, and we have our chip time in minutes. And if you remember, we brought in our PLT. If you haven't used the plot library, the matplot library, you have a drawing place you're putting stuff on. So we have our PLT, we're going to do a bar graph, and we just want to simply use our df2 gender and df2 chip time in minutes. So that's going to plot the two bars. And to make it pretty, we'll go ahead and give it the X label gender, the Y label chip time minutes. And that simply is, remember, it always plots X and it plots Y. We have our gender, our chip time. Give it a nice title, comparison of average minutes run by male and female. And if we go ahead and run this with the correct titles in here and everything matches, you'll get a nice graph. We can see here the comparison of average minutes run by male and female. Here's our chip time in minutes. The men seem to be slackers in this particular case. And it's actually, there's a number of studies that show that women tend to have, as far as doing cross-country, there's a lot of women who have a longer endurance than men. So it's not too surprising. But we can see here the average chip time around 70, and for women over 100 minutes. And then another really cool thing we can do is we can describe the data. So df2.describe, this again is a pandas function, just like info is. And we're going to include np number, the numpy number. And if we run that, you'll see here it comes up and it says chip time in minutes, count, it gives you the average or the mean, standard deviation, the minimum, the maximum, all the different descriptive information you're going to want from your data set on there. And just because there's all kinds of fun ways, let's do a box plot to display your information. We can do a box plot where the column equals chip time in minutes. And let's go ahead and run that. Keep mistyping my chip time in minutes. And you can see it puts out a nice box plot showing you the information. We have our different values and floaters. And this is always interesting because this is a nice way of seeing where we have these floaters, one up here and there's two up above, and of course your nice spread on the box plot. And we can also modify this a little bit, and we can add in by equals gender, and then we'll just give it a blank title. I don't know why we're giving it a blank title. We'll just add a Y plot, Y label on there for runtime. And if we run this, you can see here box plot grouped by gender, chip time in minutes, and now we have our female and male, two different areas, and you can see how they vary. You have your two different your outlier up here, and you can also see how there's such an overlap between the two different values. So if I was looking at this, I'd be like, wow, I really could not draw a conclusive thing on this saying that women's runtime was more in general because they overlap too much. That would be one of the conclusions I'd have to come up with on here. And then we get to maybe the partners come in from the company and say, hey, we'd like to know the age versus chip time in minutes. That'd be something worth knowing on the statistics on this. And the first thought is we can simply plot it. And we can do this. We can actually plot the scatter plot, chip time versus df2 of age. There's our XY coordinates. But if you remember from df2 when we did the info, let's go way back up here, we're looking at a data object as far as our chip time on this and our age. Now we converted the chip time, but we also need to convert the age. And if we do it right here, we just plot it, and it'll actually let us plot it. It shouldn't. It should give us an error, but it does let us plot it. You'll see the ages come up a mess over here. because they're converting it to weird float numbers and all kinds of things. So what we want to do is we want to take our age, and we'll just call this age underscore I. So we're going to take our age and we're going to create another column for df2 age underscore I. And the I is just going to stand for integer. It's our own choice of values. There is a number of ways to do this, but we're going to do pandas to numeric is the best way in pandas. And the reason we're doing this is that numeric creates a float value. So right off the bat, we want all our stuff converted. It converts it to the least common denominator. So if they're all integers already, you'll get integers. As you can see from here, it's doing some kind of conversion that converts it to a float value. The other thing that numeric does is if there's a null value, or they put in like a blank line or a dash to represent no information, it'll convert it to a null. So it goes from like a string to a null versus just having some kind of made up number that Python somehow created for the graph we have below. And then we want to add our df2 age, because that's what we're converting to numeric, and then we want to coerce it. And there's a couple different options on this, like you can have it where it just doesn't process it in pandas, but coerce means that if it gets a weird value, that is a null value now. And since we're dealing with errors, this is what happens when you get an error converting it. We want to coerce it. There we go, and put the end bracket on there. And then finally we want to go ahead and round this off. So we'll put brackets around all the way around it, and this rounds off everything in this series. So what we've done here is I've taken df2 age, which is a D-type object, which in this case is mostly strings with a couple of blank ones in there, and we're going to convert it to a numeric, which will automatically go to float. And then we're going to take wherever there's an error, wherever it says, hey, this doesn't convert, and usually that's a blank string. Like I said, I've worked with so many databases where someone puts down none, someone types in space, some types in a dash to mean none, and you get this really weird conversion coming up. This covers all of that in pandas, so it's really a nice way of just coercing it and saying, hey, if we don't have a number in there, let's make it a null value, and then we're going to round it off. And then finally, let's go ahead and take our df2. Here's our df2, and let's drop those null values. Drop NA, and we want how equals any. So that means if there's any null values in the data set, now this might get you in trouble because you might have null values in a different column, and so you might lose data that way. At this point, we could also do like certain parts of like drop just certain columns with null values. There's all kinds of other options in here, but we're just going to do how. We're going to just drop any, and we want to do it in line equals true. So that means it's going to reassign it to df2. So df2 now has rounded out, so it's rounded to the integer. We didn't do any places. The age, and it's going to be age I, and then we've dropped all our null values. That way we're not going to get any errors when we try to plot a null value. And it also makes sure that data, by deleting out the rows, because that's what this does, it automatically does axis 0, which is your rows, axis 1 is your columns. By doing this, it automatically removes all the rows with null values. So it just cleans out the rows. And then when we go ahead and plot this, we see we have a nice clean data, and we have age all the way up to 70. So we have our chip time set, and then our age going across, and it makes a nice plot that you can easily show for display, and for and you can easily show that to your shareholders or whatever group you're working on. It makes a really nice and quick, easy display.
So the first question that probably comes to your mind is, what exactly is Bokeh? Bokeh is a Python library which is used to make highly interactive graphs and visualizations. This is done in Bokeh using HTML and JavaScript. This makes Bokeh a powerful tool for creating projects, custom charts, and web design-based applications. Now, Bokeh is a Python library for creating interactive visualizations for modern web browsers. It helps you build beautiful graphics ranging from simple plots to complex dashboards with streaming datasets. With Bokeh, you can create JavaScript-powered visualizations without writing any JavaScript yourself. This makes it a very powerful tool for data visualization. Next, let's take a look at scatter charts and how you can plot them in Bokeh. Now, scatter plots are a plot of each individual data point in the data. Two variables are plotted against one another, and each data point on the x-axis has a corresponding individually plotted value on the y-axis. As a result, the plot looks like a bunch of scattered points. These are some examples of scatter charts. Here, each point on the chart corresponds to a value on the x-axis and its respective value on the y-axis. Using scatter plots, we can see how two different variables correspond to each other. Now, let's see how we can plot scatter charts using bouquet. So the first thing that we're going to be doing is importing all of the necessary modules for our Python project. The first module that we're going to need is the pandas module, which is used to work on data frames. Next, we will also be importing the pandas bouquet module, which is used to implement bouquet on pandas data frames. Next, we will import bouquet.io, which we will use to show the various graphs that we are plotting. We will also import bouquet.plotting, which will help us in plotting all of the various graphs that we're going to be looking at. We'll also import glob, a module which will help us merge our files and get them in the required format. So the first line of code that we're going to be writing is pandas_bouquet.output_notebook. This is basically just a line of code which will help you see your output in the same notebook itself. Now let's see how we can plot scatter plots in bouquet. We already have imported the figure function from bouquet.plotting. The figure function contains most of the plots that we want to plot, such as line plots, scatter plots, bar charts, etc. So this is what we're going to be using. The first thing that you're going to need to do is create a figure. So how do we do that? Let's create a random variable p, and this we're going to be initializing to the figure function. Now within this figure function, we're just going to add a couple of parameters for our figure itself. So let's say we want the plot width to be equal to 400 and the plot height to be equal to 402. We're going to be plotting a scatter plot in the form of a square here. Next, we know that a scatter plot is nothing but various circles which are plotted on top of our graph. So that's what we're going to do. We're going to be plotting circles at certain coordinates which are going to be given by our lists. So the first coordinate is going to be the x-axis, and the next list that you're passing in is going to represent the y-axis coordinates. So over here, let's just plot this as 1, 2, 3, 4, and 5. And over here, let's start with 4, 7. These are all just random points. This is just to show you how exactly you can plot a graph in bouquet. And now let's just say that we want the size of the circles to be equal to 10 and the color of every circle to be navy. We're also going to give a random parameter called alpha and equate that to 0.5. This will just act as a placeholder. Now over here, you've initialized your figure function and given it certain parameters. And using this figure function, you're calling the circle attribute of it, passing in other parameters such as the x-axis coordinates and the y-axis coordinates, the size of the circle, the color of each circle, and a random parameter called alpha. So now we've imported all of our modules. And this is how you plot a scatter chart in bouquet. The same thing can be done when you look at the line plot. All you have to do is initialize your figure function and call the line attribute of it, pass in your x-axis coordinates and your y-axis coordinates, maybe pass in a couple of other parameters that are required, such as the width that you want the line to be and the color that you want the line to be, and finally all you have to do is show the plot. This is a basic overview of how you can use bouquet to plot graphs. And here we have a line plot. So the main difference between the scatter plot here and the line plot here is that the line plot has various different points which are connected to each other with the help of a line. So again, what exactly are line charts? A line chart is a chart that represents data as a series of points which are connected to each other with the help of a line. It is used to see trends in our data and track the way data changes over a period of time. So this is the same chart that we just plotted using bouquet right now. So as you can see, so the parameters that you know were passed in were 1, 2, 3, 4 and 5. on the x-axis and 3, 1, 2, 6 and 5 on the y-axis. So how exactly the line chart is plotted is that you plot each of these points and then you connect them or join them using a line. Next, let's take a look at pie charts and how they can be implemented in Bokeh. But first, what exactly is a pie chart? A pie chart is a circular chart which is divided into slices to represent how much of the data belongs to a certain category. It is a quick and easy way to see the categories in our data and the percentage of the data set that they represent. On the other hand, you have another type of chart called a donut chart. Donut charts are like pie charts with a hole in the center. And in this hole, you can use it to represent extra data, or you can draw a pie chart within that hole itself. So this is an example of a pie chart. Using this, you can easily get to know the various categories that our data is divided into and the percentage that each of these categories contribute towards our data. Like over here, we have a pie chart which represents crewmates and imposters in a game called Among Us. So using this, we can just say that around 75% of our data is crewmates and 25% of it is imposters. On the other hand, you have a donut chart, which is almost exactly the same as a pie chart, except the middle portion is missing values. And in this middle portion, you can do other things such as plot a pie chart or represent other data within it. So now let's see how we can plot our pie plots using Python Bokeh. But first, we need to import the data that we're going to be using to plot all of this. So the data that we're going to be looking at is the Among Us data. Among Us, as you might know, is a game that caused quite a frenzy in the past 2 years. So the data that we're going to be working at is the Among Us data set that you can find on Kaggle. Among Us was the new craze for people playing mobile games that suddenly exploded in popularity and became a hit video game during the pandemic. Now, Among Us is basically a multiplayer game where 4 to 10 players are dropped in an alien spaceship. Each player has their own role of imposter or crewmate. The task of the crewmate is to run around the spaceship to complete various tasks which are assigned to them and also to not get killed by an imposter. Players can be voted off the ship, so each game becomes one of survival. So let's load this data set and create more features. So now we've imported our data set. As you can see, our data set has over 2000 rows and 14 columns. The first column that I want to show you is the user ID column. The user ID column tells us which user the game data was collected from. Now there are 14 columns. The game completed data tells us the date and time of game completion. The team tells us if the player is an imposter or a crewmate. The outcome tells us if the game was won or lost. So over here, this is each game that a certain user has played. The user ID is used to represent the user who has played the game, and as you can see, we've collected data from 29 different people. And the number of games that these 29 people totally have played is over 2000. The outcome tells us whether the user has won or lost in this game. The task completed tells us how many tasks was completed by this user in this game. All tasks completed tells us whether the user was able to finish their tasks. Murdered tells us if the user was murdered. And imposter kills tells us the number of kills by the imposter. So if the user was not an imposter, we do not have data on how many kills was committed by the imposter during that particular game. That's why this column has a lot of missing values. Game length tells us the total duration of the game, and ejected tells us if the player was ejected or thrown off of the spaceship by their fellow players. Sabotage is fixed is basically the imposter within the game can create sabotages and it's the crewmate's duty to fix them. So this tells us the number of sabotages which was fixed by this particular crewmate. Time to complete all tasks tells us the duration taken by the crewmates to complete all the tasks, and the rank change tells us the change in rank after wins or losses of the game. The region or the game code tells us the server and the game code. Now first, let's just see how exactly the data is distributed. So this tells us how many counts each column has. So as you can see here, most of them have the same number of counts except rank change, which has a couple of missing values. Unique tells us how many unique values exist in each column. So obviously team, there will be 2 because there are only 2 possible outcomes. You can either be a crewmate or you can either be an imposter. Outcome also has only 2 unique values because you either win a game or you lose a game. Task completed has 12 different values, and this is because the number of tasks which have been completed probably range from 1 to 12. All tasks completed has 3 values, which is yes, no, and missing data. And the same goes for murdered. You have yes, no, or missing data. Imposter kills tells us how many kills the imposter has made. So in this case, the most kills that the person has made is probably 9. Game length, there are 988 different values, and ejected, again there are only 2 values because you can either be ejected or you can either stay in the game. Now the top value tells us the most frequently occurring value, and the frequency tells us the frequencies of all of the top values. Now let's create a feature called minute and extract data from game length. So we're going to be splitting the game length column, which is this column, and we're going to be converting it into minutes. And then we're going to be using that data and creating a separate feature column called minutes out of it. So let's do this. So these are the first top 2 values of our new minutes column. The 0th value is 7 because the first game length that you see here was of 7 minutes. So all that we're doing is that we're going to be splitting this value, which is 7 minutes 4 seconds, and we're going to be keeping only the first value, which is that of the minutes. The second minutes value is 16 minutes, and that corresponds to the second value in our minutes feature variable. Now let's take a look at the murdered column. The murdered column has yes no values and missing data set and missing values. So let's change those. We're going to be replacing no values with not murdered, yes values with murdered, and the simple dash with missing. And we're going to be doing this in place, which basically means that this is going to make a change to our main data frame. So this is done. Let's take a look at our data frame now. This is what our data frame looks like. We have a game's length column, we have a minutes column, and we also have made changes to our murdered column, which is represented here. So now we don't have any missing values or dashes in our murdered column. We have all of it represented as categorical data. And this is one of the main columns that we're going to be using to plot our pie plots. So now let's see how we can plot a pie chart. The first thing that we're going to be doing is that we're going to be getting the total value counts in our team column here. So we're going to be plotting a pie chart with the help of this team column, and we're going to be getting the value counts of each unique value in the team column. So you can do this with the help of the value counts function that Pandas data frames provides us with. And now that we have the value counts of each unique value which is present in our team column, let's plot it in the form of a pie chart. We're going to be doing this with the help of the plot bouquet function. And the type of chart that we want to plot is a pie chart. Let's give it the title as ratio of imposters versus crewmates, and let's run this now. And this is what your pie plot looks like after you've plotted it. So now the same thing can be done to plot a donut plot. The first thing that we want to see is if there are more crewmates or imposters murdered or not in the game. To do this, we will add two more features, angle and color, which are going to be used in the chart. So to get angle, we're going to be importing pi from math, and we're going to be converting our angle in the form of radians. And as for the color feature, we're going to be having 3 different shades of blue. So this is basically what our murdered data frame looks like. So over here you have not murdered, the total value counts of which is 894, and the angle that this gives us is 2.522302, and this is the corresponding color. The same goes for murdered, which is 867 values, and we've converted that into an angle in radians and given it its own color. And finally we also have missing values, of which there are 466. The angle is 1.314756 and it has its own corresponding color. So this is a data frame that we're going to be using to plot our donut chart. So from bouquet.transform we import cumulative sum, and the cumulative sum is what we're going to be using to find the start of our angle, or basically to find how much portion of our donut chart is going to be occupied by the angle. So the donut chart can be plotted using the angular wedge function from figure. So the x-axis here is 0 and the y-axis is 1. The inner radius is the radius that you are going to be giving to the inner smaller circle, and that we've given as 0.15. The outer radius is the radius of the bigger outer circle, and the direction in which our data is going to be plotted is in the anti-clockwise direction. So let's run this. And this is what our donut chart looks like. So the not murdered is this dark blue color portion of our donut chart, and when you hover over it, you can see how many values are present in the not murdered column. The same goes for murdered, and because we've plotted our data in the anti-clockwise function, this is how it's being plotted. So murdered, not murdered, and then finally you have the missing values. The way that you can interpret this graph is that you can say that most of the people were murdered during the game, but most of the data is missing. So we can't say for certain whether the majority of the people were murdered during the game or not, because the number of missing values can make a huge difference. And the number of people who were not murdered and the number of people who were murdered are very close to each other. Like their total values are very close to each other. Next, we will create a data frame of sabotages fixed and minutes and change the column name and add T in them. So this is basically what we're doing. We've created a data frame which has the number of sabotages fixed and the minutes. Now let's just take the 3 sabotages which were fixed, which is 0, 1 and 2, and create a data frame out of all of these. So each of these individual data frames just contains these individual columns. To make a simple scatter plot with only one legend, we can pass the data and use scatter to make the charts. So basically we're just plotting the scatter chart in bouquet here. And this is what our minutes scatter chart looks like. Now we're plotting this for 1t. We're plotting the minute at which one sabotage was fixed. And another cool thing about bouquet charts is that you can always zoom into them or zoom out of them to better see where your data is plotted. So this is a scatter chart which has only one variable, which is 1t, and the minute at which it was plotted. To make a scatter chart with more variables, we are going to need to use circle, which is a method of figure object which we've already seen before. The circle is one of the many plotting styles which are provided by bouquet. You can also use triangles or many more. You don't have to make each point a circle. So we're gonna be plotting the sabotages fixed and the minute at which they were fixed. And we're gonna be plotting 3 different circles of 3 different colors. I mean, each of them correspond to how many sabotages were fixed at what time. 0 sabotages at what time, 1 sabotage at what time, and 2 at what time. So let's run this. So as you can see here, when 0 sabotages were fixed, these were the times. When 1 was fixed, this was the time at which it was fixed. And when 2 was fixed, this is the time that it was fixed at. Now the x-axis is our minutes and the y-axis is the sabotage. When you hover over it, you can see various information about where each circle is plotted. So this has an index of 10. The data xy will tell you the exact x coordinate and the y coordinate, and the screen xy will tell you the screen pixels on which it is plotted. So now we've taken a look at pie charts. Let's move on to histograms. So what exactly is a histogram? Histograms are used to plot numerical data according to the range that they fall into. The data is plotted in the form of bins or rectangles, and the y-axis corresponds to the amount of data present in a certain range or at a certain point. So this is what a histogram looks like. This is a histogram of the distribution of minutes. So the x-axis has the range within which this data falls. Like over here, the first range is from 0 to 2.9 and the second one is from 2.9 to 5.8. Each range has a value of 2.9 and the corresponding y-axis or the height of the bins tells us how much data is present within this range. So this is how you can read histograms. Now let's see how we can plot them using Python bouquet. Now let's see the distribution of minutes in the Among Us game. We will use his to plot a histogram. So basically just going to be plotting the minutes of our game. We're going to be using the df min column for this, and we're going to be converting it into an integer. So this is the column that we're going to be plotting. Let's plot this. Again, we're going to be using the plot bouquet function here because it makes plotting data frames very easy. The kind of data frame that we're going to be using is the histogram or hist, and the title of our graph is going to be distribution of minutes. So let's run this. Now this is what our histogram looks like. Now this is when we've only plotted one variable, which is minutes. Yeah, so another thing that you can plot is a stacked histogram. A stacked histogram is when you plot various histograms on top of each other. So let's see how this works. For a stacked histogram, we want to see if the game length has a correlation with the amount of imposters and crewmates in our game. So to do this, we're going to be creating a small data frame which has the game length and the team columns combined. So let's do that. And this is what this looks like. So all you have to do to plot this in the form of a stacked histogram is use the hist function again. So let's see how that is done. And let's give this figure a size of, say, 750, 350 size. So let's run this again. And this is the stacked histogram that you get. We have two different columns which are plotted on top of each other versus the game length. So basically this tells us that when the game length was between 0 to 0.9 minutes, the number of imposters was way higher than the number of crewmates. And the longer the game went on, the number of imposters decreased and the number of crewmates just kept getting longer and longer. Now, obviously, you can say that the number of crewmates is decreasing as the game goes on too, but this is because the imposters would have killed off most of the crewmates. As you can see here, towards the end, there are no imposters, which means that most of the imposters were rejected and the crewmates won. So now we've taken a look at histograms. Let's move on to bar plots and understand how exactly they're different from histograms. So in histograms, you have plotted numerical data distributions as of yet. In bar plots, you plot for categorical data. It also uses bins to plot the amount of data. When the bins are stacked on top of each other, it's called a stacked bar chart. This is basically what a bar chart looks like. The difference is this does not have its own range. Each bar is used to represent a categorical data, and the height is used to tell us how much of that categorical data is present. So now let's see how we can plot a bar plot. So again, we're going to be making a small data frame of the task completed and the value counts of how many tasks have been completed. To plot a bar plot, we're going to be using plot bouquet again, and the kind of plot that we want to plot is bar. So let's run this and see what we get. So here is your bar plot. The task completed in this case is categorical data, and the counts basically tells us how many value counts fall into each category. So 0 tasks completed are 69, 1 task completed is 117, 2 tasks completed is 10, and so on. From this bar chart, you can say that the most number of tasks completed is 7 and the least tasks completed are 10. Now let's create a stacked bar chart and let's see who wins, imposters or crewmates. To create a stacked bar chart, what we're going to be doing is that we're going to be creating a different smaller data frame of team and outcome. To make sure that the bar chart is stacked, all you have to do is include a stacked attribute in your bar function and change its value to true. So let's run this and see. And here you can see that we have a stacked bar chart. So you can see that crewmates who have a lot more data have won 981 times and lost 780 times, while imposters have lost 205 times and won 216 times. So the crewmates have won significantly far more than the number of times imposters have won. Now let's take a look at stacked vertical bar charts. So far the bar charts that we've been looking at have been horizontal, which means that the data goes upwards. For a vertical bar chart, we're going to be seeing if all tasks have been completed or not. So in the data frame column, all tasks completed, we're going to be replacing the values of yes and no with tasks completed and tasks not completed. We're also going to be creating a smaller data frame of the outcome column and the task completed column. To plot a stacked vertical bar chart, you are going to be using Python bouquet.bar h function, and you're going to be changing the stacked attribute to true. This is what a stacked horizontal bar chart looks like. So over here we can see that the missing values is represented by blue, task completed by orange, and task not completed by green. Here you can see the total outcome. You can see how many wins, how many tasks are completed, and how many tasks are not yet completed. And the same goes for losses. You can see how many losses have occurred, how many tasks are completed, and how many tasks were not completed. This is a very good way of representing a lot of data in a relatively smaller area. Now, the way we can interpret this graph is that we can say that finishing the task will automatically ensure that the crewmates have won. So there's a higher number of people who need to complete the task to win the game. Another very unique type of bar chart that you can have is a bidirectional bar chart. So let's plot a bidirectional bar chart in which the bars will be going both ways, to the left and to the right. We're going to be plotting a horizontal bar chart over here to make it easier for you to see. To have a bidirectional bar chart, you need positive values and negative values. The center is going to be at 0. So here we're going to be making the loss feature as negative by multiplying the loss feature with the -1 value. So here we go, the losses are all negatives and the wins are all positives, right? Now let's run this and see how many losses and wins have occurred for each user. So user 1 has 42 losses and 58 wins, but you can easily see whether they have won more or lost more by comparing the height of the bars for the wins and the losses. So we can easily say that in this scenario, user 1 has won more times than they've lost. The same can be said for user 2, where the wins bar is significantly higher than the losses bar. So this is how you can plot and understand a bidirectional bar chart. So we've taken a look at how we can plot bar charts and the various types of bar charts that are available to us in Python Bouquet. Now let's take a look at area plots. Area plots is a combination of the line and the bar chart when the area below a line is shaded. Using an area chart, we can see how the values of different groups change over a period of time. The area chart has different baselines to show the vertical range of data. Here we've plotted the sabotages fixed versus the minutes at which they were fixed at, right? So these are the minutes, and the sabotages fixed are of two types, 0t and 1t. So the number of minutes that we're considering here is somewhere around 28-ish, right? And 0t, as you can see, has a way higher value. So one really good thing about area plots, especially in this case, is that they have two ranges. And they have another range on the y-axis, which tells us how the number of sabotages fixed is ranging. So 0 sabotages fixed, you can see how the value keeps fluctuating and how the value changes for different minutes. And the same can be said for 1t. Now 1t has a baseline which is over here, which is just above the 0t baseline. This doesn't necessarily mean that this is where 1t starts and this is where it ends. This just means that it ranges from 0 all the way here, and we can compare very easily how 0 sabotage is fixed and 1 sabotage is fixed range or change with respect to each other at the same time. Now the first thing that we're going to be doing to plot our area chart is that we're going to be creating another data frame. This is called df minutes, which is going to be comprising of the minutes column of our data frame and the sabotages fixed column of the same data frame. For df min, we're going to be renaming the columns to 0t and 1t. And the only columns that we're going to be considering out of the 5 different columns that we have are the 0t and the 1t column. We're going to be combining all of these together in a format which can be plotted by using bouquet, and column data source helps us do this. It helps us convert our various data frame columns into lists. Next, we're going to be using the figure function, and we're going to give our figure a width of 400, a height of 400, and the title of sabotage is fixed versus the minutes at which they were fixed at. To plot a stacked area graph, you're going to be using vArea underscore stack function from the figure module. You're going to be passing in your y parameters, which is y0 and y1, because we have 2 different y parameters here, and the x parameter, which is df minutes. The color that you're going to be using is gray and light gray. The legend labels are the names that you've already put here, which is 0t and 1t, and the source of your data is going to be this column data source. Now let's run this and see how our area chart looks. So this is our area chart. We've gotten 2 different sabotages here and 2 different times at which they occur, which is 0t and 1t. The minutes tells us how many sabotages were fixed at each time, basically how long it took to fix a sabotage, and the minute during the game at which they occurred. Now let's take a look at the layout function of our bouquet library. The layout function will let us build a grid of plots and widgets. We can have as many rows and columns or grids of plots in one layout. Using the layout function, we can see various graphs at the exact same time. Mainly used for designing dashboards, it lets you build grids of plots. So this is basically what your layout function will help you do. This is going to look very good in a website because it's going to arrange our plots in a way that we can easily see all of them and understand all of them without any loss of data. This is also arranged very neatly, which is exactly what the layout functions allow us to do. So now let's take a look at how the layout function can be implemented in Python Bouquet. Now of the layout functions, there are many different layout options which are available. You have the column function, which allows you to display plots vertically. And you have the grid function, which lets you display plots in the form of grids. Now, for example, let's say that we want to make a dashboard layout in Bouquet. We are going to be considering 3 different charts. The first one that we're going to be considering is a lollipop chart, which is done here. The next one that we're going to be considering are 2 pie charts. So this is how you plot a lollipop chart, and I'll show you what exactly a lollipop chart is in just a minute. The first thing that you need to know is that the first graph that we're going to be plotting is going to be a graph which has the user ID versus the outcome of the games plotted on it. So what we're going to be doing here is that we're going to be creating a single data frame which has all of the user IDs present in it along with the user and the wins that the user has obtained. Now using this, we're going to be plotting it in the form of a plot in decreasing order, where we have the top 10 users who have won, which basically means that the users who have won the most number of games out of all the users in consideration. So figure 1 segment will basically help you plot a line which has a width of 2, and a circle will be at the very top of this segment. So lollipop chart is going to be a horizontal line with a circle at the very top. Sorry, the next graph that we're going to be plotting is going to be a murdered and not murdered and missing values pie chart. And the last thing that we're going to be plotting is a donut chart of the teams. and the value is within them. So these are the three different graphs that we're going to be plotting, and these are just us creating the graphs and plotting them. The main logic is over here. The main logic is that you want to set a layout in Bokeh as to how you want to see the charts. So the layout that we are going to be looking at is that we're going to be having a lollipop chart at the very top and two smaller pie charts at the bottom, right? So we have three figures here. And the first thing that we're going to be doing is that we're going to be giving these figures a line color of none. The axis is not going to be visible and the axis labels are not present for these figures. This is the main function that you're going to be looking at. This is your layout. Using the grid layout function that you've imported here from bokeh.layouts, you're going to be creating a grid. And how does the grid know where the figures are? So you've divided the grid into two. This is evident because you have two main figures here, which are separated by a comma. So this tells the grid that the page is going to be divided into two. The first figure, which is on top, is going to be figure 1, and the figure at the bottom are figure 2 and 3. This means that the bottom half is going to be further split into vertically. Let's run this and see what our layout looks like. So here you have it. Your entire page is divided into two. The first one has the figure 1, which is the lollipop chart, and the bottom half of our page has two figures, which are the two donut charts. The bottom half is divided exactly into two, as you can see here. This is because that is the grid layout that we wanted. So this is how you can use the layout function in Python Bokeh. It is extremely easy. All you have to do is create a layout by using the grid function, or you can also use the column function. The column function will plot it in the form of a single column vertically. Using the grid function, you can plot figures vertically as shown here. So when you separate them by commas with respect to each other, they will be plotted vertically, and when you group them together and separate them with commas internally, they will be plotted horizontally. So now we've taken a look at how we can use a layout function. Now let's see how we can make interactive graphs with the help of Bokeh. Over here, we're going to be using Bokeh to design a dashboard which is used to represent the horsepower in cars. We are also going to make our graphs interactive and see how maximum information can be conveyed with the help of a single graph. So here we have multiple different cars, and along with the cars we're also going to be given their horsepowers, a little bit of other information about them, and their images. And over here, as you can see, we have a very simple vertical bar chart. But let's see how we can make it interactive and convey all the information that we have in our single data set on this one bar graph. So the first thing that we're going to be doing is importing all of our important necessary modules. We're obviously going to have the pandas modules, which is going to be imported to work with the data frame that we've given. Apart from this, we're also going to be importing figures, output file, show, save, and column data source from bokeh.plotting. We already know that the figure function is used to plot different types of graphs which are given. Output file is just used to see our file. The show is used to display our graphs, and save will help you save your graph. Now, the column data source is the core of most Bokeh plots. It provides the data to the glyph of your plot. When you pass sequences like Python lists or NumPy arrays to a Bokeh render, Bokeh automatically creates a column data source with this data for you. So this is basically what you're going to be using to pass data onto your Bokeh glyphs. Apart from this, we're also going to be using a hover tool function, and from the transform function, we're going to be importing factor CMap. We're going to be importing a palette color, which is going to be various shades of blue. And we're going to be importing components from the embedded function of Bokeh. Let's just see how we can use all of these and the different things that they do. the first thing that you're going to be doing is reading in your car's data frame and creating a column data source so that you can easily parse this data onto your bouquet glyphs. So let's run and import all of our various required functionalities and import the data as well. So this is what your data set looks like. We have 8 different values in our data set, which are the names of different cars, their horsepower, their price, and a hyperlink of an image. This is what our data set looks like. We have only 8 columns. So using this data set, we're going to be plotting a horizontal bar graph. Again, we're going to be calling our figure function and we're going to be giving y range to our car list. The y range is basically just going to have the different values which are going to be present on the y-axis. We've given the plot a width of 800 and a height of 600. The title of the plot is Cars with Top Horsepower and the x-axis label is horsepower. The tools that we're using here is pan, box select, zoom in, zoom out, save and reset. So these are tools that you're going to be getting on the right side of your plot. Now let's render our glyph or render our graph. The graph that we're going to be using here is the horizontal bar graph. So the y-axis is going to have cars and the right, or basically the height of the entire bar, is going to depend on the horsepower. The left is going to start from 0 and the height of each bar is going to be 0.4. The color that we're going to be giving is going to be a palette of blue. So each different car will have a different color of blue associated with it, and the color of blue which is associated with it will depend on the car list. Now fill alpha 0.9. The source is your source data that you have over here, which is the column data source of our data frame. And the legend is going to be car, which basically means that your entire plot is going to have the legend of car. Now we're going to be adding the legend. This is us giving the legend its orientation. So the legend is going to be vertically oriented. The location is going to be on the top right, and the font size of the text car of our legend is going to be 10 px or 10 pixels. We're also going to be adding a hover tool. Inside this hover tool tips will basically tell you what you're going to be seeing in the hover tool box. So we're going to be creating this with the help of an HTML format. The first thing that you're going to be seeing is the name of the car. The next column will have the price of the car, the horsepower of the car, and the image. Now the image is in the form of a hyperlink, and this is going to be auto-populated in your hover tool. The width of the image is going to be 800. So we are going to add all of these hover tools to our P image, and we're finally going to be showing you the graph and what it looks like. So this is your bouquet plot. Here the title of the plot is Cars with Top Horsepower. This is your legend, which is cars. The name of each car is given here along with the color which is associated with it. Here are the different tools that we have. You can save this, you can reset it, you can zoom out, you can zoom in, you can select the boxes, and you can pan your image. So here we're zooming in, here we're zooming out. If we save this, the plot automatically gets downloaded in your system, and if you reset it, the image goes back to exactly what it looked like when it was first opened. Now here you have the names of the different cars on the y-axis, and you have the various horsepowers on the x-axis. Let's take a look at our hover tool. So here you have the name of the car which is on top, you have the price, and you have the horsepower, and as you can see, you have the image which is populated instantly from the hyperlink that was available to us. Now the color palette associated with each car gets darker the more the horsepower of the car increases. So here we have cars with top horsepowers which are arranged in an ascending order from the top and a descending order from the bottom. So this is another way that you can use Bouquet to create extremely interactive and informational graphs. Here in just half a page, and this is us making a huge plot, right? We can also decrease the size of the plot if you want to. But basically in half a page, we've conveyed all the information ranging from the name of the car to its model to the horsepower that it has, its price, and also its image. And this is also a very good way to compare it. So these are just some functionalities which are provided in Bouquet itself. No other data visualization library will let you work so well with graphs and will let you customize your graphs to this extent.
Spotify is a Swedish audio streaming and media services provider founded in April 2006. It is the world's largest music streaming service provider and has over 381 million monthly active users, which also includes 172 million paid subscribers. The total number of downloads on the Spotify app in the Android store exceeded 1 billion in May 2021. So millions of people listen to music all day. Even I am hooked to music. As an analyst, what's better than exploring and quantifying data about music and drawing valuable insights? Before I move ahead, I have a quiz question for you people. The name Spotify comes from a combination of two words. So which are those two words? Please let us know your thoughts in the comment section below. I would like to repeat the question again. The name Spotify comes from a combination of two words. So what are those two words? We would love to hear from you. So please put your answers in the comment section below. Now let's use Python libraries and functions to analyze and visualize our dataset. First, I'll show you the two datasets that we'll be using. So here is the first dataset that we'll be using for our demo, and then I have my second dataset called Spotify features, which is essentially about the genres of the different soundtracks. Now these datasets have been downloaded from kaggle.com. Now the links to the datasets have been provided in the description box. Please go ahead and download them. Now let me just go ahead and brief you about the columns that are present in our first dataset, which is about tracks. We have our column A, which is ID. This is the unique ID for each of the songs. Then we have the name column, which is essentially the name of the song. Then we have a column for popularity. So the popularity ranges from 0 to 100. Then we have duration in milliseconds. This is the duration of the track in milliseconds. Next, we have a column called explicit. Now we are not bothered about this column because we are not going to use it in our analysis. Then we have artist. So the name of the artist who has composed or sung the song. Then we have ID of the artist. Then we have a column for release date, which is basically the date on which the song was released. Then we have a column for danceability. So this describes how suitable a track is for dancing based on a combination of musical elements such as tempo, rhythm stability, beat, strength, and overall regularity. The value ranges between 0 and 1. Next, we have a column for energy. So the energy is a measure between 0.0 to 1.0 and represents a perceptual measure of intensity and activity. Typically, the energetic tracks feel fast, loud, and noisy. Higher the value, the more energetic is the song. Then we have a column for key. So key is the pitch, notes or scale of song that forms the basis of a song. There are 12 keys ranging from 0 to 11. Moving ahead, we have loudness. So the overall loudness of the track in decibels, it ranges from -60 to 0 decibels. Then we have mode. So songs can be classified as major and minor. 1.0 represents major, or 1 represents major, and 0 represents minor. Next, we have speechiness. So speechiness recognizes the presence of spoken words in a track. more exclusive speech like the recording, example talk show, audiobook or poetry, the closer to 1.0 the attribute value. Then we have a column for acousticness. So a confidence measure of 0 to 1 of whether the track is acoustic or not. So 1.0 represents high confidence the track is acoustic. Then we have other information about instrumentalness. Then we also have a column for liveness. So liveness detects the presence of an audience in the recording. Then we have a column for valence. So valence is a measure between 0.0 to 1.0 and describes the musical positiveness conveyed by a track or a song. And finally we have the columns for tempo and time signature. Now even in the second data set we have almost the same columns, just that we have an additional column that is about the genre of the songs present in the data set. Cool. Now let's head over to our Jupyter notebook and we'll start with our analysis. Okay, so one more thing to remember, our data has information from 1922 onwards, so all the songs from 1922 till 2021. Cool. Okay, so I'm on my Jupyter notebook. So you can see I have a few cells that have already been filled up. So we'll start with our analysis. First of all, let's go ahead and import the necessary libraries. So I'm importing NumPy, Pandas, Matplotlib and Seaborn for my analysis and visualization. I'll hit Shift Enter to import the libraries. Alright. And in the next cell, I'm going to load my dataset using the pandas read_csv function. I have my location already put here. Let me show you the location where the data files or the data sets are located. So this is my location under Chrome downloads. I have a folder called Spotify datasets. Okay, so let's import and check the first 5 rows in the dataset. So for that I have used the head function. There you go. So here you can see I have my first 5 rows of information from the dataset, and on the top you can see the different columns. You have ID, name, popularity, artist, then we have the release date, danceability, energy, key, loudness, liveliness or liveness, valence, tempo and other information. Cool. Now let's check for null values in the dataset. I'll just give a comment as null values. Every time when you download a dataset from an open repository, there are chances that the dataset would contain null values, so it's better to check them beforehand. So I'm going to use the isNull function present in the pandas library. PD I'm using because I had imported pandas as PD. So pd.isNull. Then I'm going to use the variable name df_tracks because I imported my dataset and stored it in the variable df_tracks. So I have my data frame under df_tracks variable, and then I'll use the sum function to check the total number of null values present in the dataset for each of the columns. If I run it, there you go. So here you can see my name column has 71 missing values or null values, and we don't have any null values for the rest of the columns. Okay. Now let's use the info method that will give us the total number of rows and columns in the dataset, and we'll also check the data types and the memory usage. So I'll say my data frame name, that is df_tracks dot info. If I run it, you can see here. Now if you mark, there are total 5,86,601 names or the names of the songs present in the dataset, while the rest all have 5,86,672. So clearly there are total 71 song names or soundtracks missing from our dataset. And below you can see the data types. We have float, integer and object, and then you can see the memory usage. Cool. Now before I move ahead with our next analysis, I have another question for you. Which artist or musician has the most number of followers on Spotify? I repeat, which artist or musician has the most number of followers on Spotify? Please put your answers in the comment section below. We would be happy to hear from you. Now let's move ahead and do our first major analysis in this demo. We are going to find the 10 least popular songs present in the Spotify dataset. So I'll create a variable called sorted_df that will be equal to my data frame name, that is df_tracks dot. I'm going to use the sort_values function and say my column name is popularity. So I'm going to sort the values based on the popularity and then say ascending equal to true, since I want only the least popular songs. And then I'm going to say head of 10, which means I want the top 10 least popular songs. Now let's go ahead and print sorted_df. If I run it, you can see we have the list of 10 least popular songs on Spotify. You can see that popularity is 0, and you can see the names of the songs. Some of them are songs which are not in English language, and you can see the artist names as well. Cool. Now moving ahead, let's see some descriptive statistics for the numerical variables that are present in our column. So I'll say df_tracks dot describe, which is the function to get some descriptive statistics, and I'm going to use the transpose function after that. If I run it, there you go. So we have the statistics about count, mean, standard deviation, minimum value, 25th percentile, 50th percentile, 75th percentile, and the maximum value for these columns like popularity, duration in milliseconds. Then we have energy, key, loudness, mode. Cool. Now if you see this popularity column, the minimum value is 0 and the maximum value is 100, and you can see the 50th percentile is 27, which is essentially the median. You have the standard deviation as 18.37. Then similarly you can check for the other features as well. Cool. Now we'll see the 10 most popular songs which are greater than 90. So we are going to check for the top 10 songs with popularity greater than 90. Let me show you how to do it. So in this cell, I'm going to create a new variable called most popular, and I'll say df_tracks dot. This time I'm going to use the query function that is part of pandas library again. I'll use the column that is popularity, and we'll set the condition popularity should be greater than 90. I'll give a comma and say in place equal to false, because I don't want to change my original data frame. And then I'll say sort_values, and I'm going to sort it based on popularity in descending order. So I'll say ascending equal to false, and then let's take only the top 10 popular songs. So I'll say most popular, use square brackets, and we'll then pass the slicing operator and say :10. Now if I run this, there you go. So here you can see the 10 most popular songs that is present in our Spotify dataset. So first we have Peaches by Justin Bieber, Daniel Caesar and Giveon. Then we also have a song name called Driver's License, Astronaut in the Ocean, Save Your Tears. We also have The Business, Streets, and Heartbreak Anniversary. So these are the most popular songs that are present in our dataset based on their popularity. You can see Peaches has the highest popularity with 100. Alright. Now moving to the next cell. So here we are going to set the index to be release date column in the main data frame. So I am setting my index using the set underscore index function. I have passed in my column name as release date and I'm saying in place equal to true, which means I want to change it in my original data frame, and then I'm changing the value to date time format, and let's print the head of the dataset. So you can see here we have successfully changed our index. Now here you can see instead of 0, 1, 2, 3 we have the release date column and the rest of the columns are intact. Cool. Now let's move ahead. So suppose you want to check the artist at the 18th row in our dataset. You can use the index location method for that. Let me show you how to filter only specific rows of information from the dataset. I'll use my data frame df underscore tracks, and using double square brackets I'll say my column name, which is artist, and I'll use the index location method and say, let's say I want to check the artist who is present in the 18th row in my dataset. So I'll use ilog18. If I run it, the artist's name is Victor Boucher. Cool. Now let's move ahead. We are going to convert the duration in milliseconds to just seconds. So if you see our dataset, we have a column called duration in milliseconds. So all our songs are present in milliseconds. Let's convert them into just seconds. So for that, I'm using the Lambda function and dividing the values in milliseconds by 1000 so that they get converted into just seconds. I have used in place equal to true, so I want to change it in my original data frame. Let's run it and do the necessary changes. Alright. Now we'll print the head of the dataset just to check the duration column. So I'll say df underscore tracks dot duration dot head. If I run it, there you go. So you can see the values have now been changed to just seconds. Cool. I have the final quiz question for you. Who has the most monthly listeners on Spotify? Please put your answers in the comment section below. We'd be glad to hear from you. Now coming to the next cell. So here we are going to create our first visualization that is going to be a correlation map. We are going to drop 3 unwanted columns, and those are key, mode, and explicit. And then we are going to apply Pearson correlation method. Now I have set my figure size to 14,6, and then we are using the Seaborn heat map function to create our correlation map. I have put the variable that is correlation underscore df. You can see above we had created this, and then I'm setting annotation equal to true. So this will write the data value in each cell. I have set fmt equal to .1g. So this is a string formatting code to use when adding annotations. Then I have set my vmin and vmax. So these are the values to anchor the color map. Otherwise they are inferred from the data and other keyword arguments. CMap here stands for color map. You can just search for SNS CMap. You will get the documentation. So you can choose whichever color palette or the color map you want. Here I have used Inferno, and I have set my line widths and line color. Finally, I am giving a title to my correlation map, and I have set the xtick labels. Let's go ahead and run this to get our first visualization. if I scroll down, there you go, we have got a nice correlation map. So here on the right side you can see the scale. It ranges from -1 to +1. -1 means the variables have least or negative correlation, while the values which are above 0.0 means that the variables have a positive correlation. Now here you can see there are values like -0.7 for energy and acousticness, which means if the energy is high, the acousticness is really low. Again, for loudness and say speechiness, if the song is loud, the speechiness is low, so there is negative correlation. But if you see for energy and loudness, there is really high correlation between these two variables. You can see the value is 0.8. So if the song is loud, this implies the song has really high energy and vice versa. Now if you see for a few other variables, there is negative correlation between acousticness and danceability. There is negative correlation again between valence and acousticness. Similarly, there is positive correlation between energy and valence, which is 0.4, and even for danceability and valence, that is positive correlation, which is 0.5. Cool. So from the correlation heat map, you can note that acousticness appears to have a strong negative correlation with energy. So if you see for acousticness and energy, there is a strong negative correlation, and there is a moderately strong positive relation between loudness and popularity. So if you see for popularity and loudness, the color is orange, which means it lies in this positive region. And there is also a moderately strong positive relation between danceability and valence. So if you check for danceability and valence here, there is a moderately strong positive correlation. Alright, now let's move ahead. We are going to sample our data and take just 0.4% of the total data, and we'll create 2 regression plots using this data. So let me first sample my data. So I'll create a sample data frame using my original data frame, which is df_tracks, and say sample. I'm going to use the int function and say 0.004 multiplied by the length of my original data frame, which is df_tracks. Alright, now let's run this and we'll print the length of my sample data frame. If I run it, you can see 0.4% of my total data set is 2346 rows. Cool. Now we are going to create a regression plot between loudness and energy. Now in our correlation map, we saw there was a positive correlation between loudness and energy, which was 0.8. Let's plot it in the form of a regression line. So I'll use plt.figure. I'll set my figure size equal to, let's say, 10,6. I'll say SNS dot regression plot. So I'm using the function called regplot, and I'll use my data as sample_df, give a comma, and say in my y-axis I'll have my column loudness, and in the x-axis we'll have energy. I'll give a color to my data variable. Let's say the color is C. Then I'll set my title to loudness versus energy. Let's say correlation. Alright. Let's make sure everything is fine. Now we'll run and see our result. There you go. So you can see here clearly there is a very high positive correlation between loudness and energy. On the y-axis we have loudness and on the x-axis we have energy, and you can see all the data points or the songs are in one direction. So if the energy increases, the loudness of the song also increases, and similarly if the loudness of the song decreases, your energy of the song or the track also decreases. So there is a very high positive correlation, and you can see the regression line here. It has gone and is increasing gradually. Cool. Now similarly, I'll just copy this code and we are going to see another regression plot, this time for two different features. Let's say we have popularity in the y-axis. So I'll say popularity, and then in the x-axis we have, let's say, acousticness. I'll change the color to, let's say, B, which stands for blue, and will set the title to popularity versus, I'll have acousticness correlation. Just scroll down and we'll run it to see the result. There you go. So I have the different points for the songs, and here you can see the regression line is downwards, which means if the acousticness of the song increases, the popularity decreases, and similarly if the popularity increases, acousticness decreases. You can see the downward trend of the regression line. Alright. Now in the next cell we are going to create a new column called year from our release date column, and I have changed this to date time format. Let me just run it. Cool. Now after that we are going to create a distribution plot to visualize the total number of songs in each year since 1922 that is available on the Spotify streaming app. So I have used my Seaborn library and dist plot function. Now one thing to remember, you need to update your Seaborn library to this version if you haven't done it. So use this command pip install --user Seaborn and the version. So here in the distribution plot we are going to plot a histogram. So I have used kind equal to hist, which stands for histogram. Let's run and see the result. Okay, so here you can see I have my distribution plot. So the plot tells us that the number of songs for each year in the dataset according to their release date have increased in the recent years since music became more accessible to people globally with technological advancements. So earlier you can see there were very few songs available in the 1920s. Later on the number of songs increased rapidly, and now you can see we have a lot more songs available for people to listen. Cool. Now we are going to see the duration of songs over the years. For that again we are going to create a bar plot. So I'll first create a variable called total duration equal to df underscore tracks dot, I'll use the duration column that we created with seconds, and then I'm going to set my figure dimensions. So I'll use figure underscore dims for dimensions equal to 18,7. After that, I'll have my figure axis defined. So I'll use the matplotlib subplots function, and I'll set the figure size equal to my figure dimensions, and then I'll say figure equal to SNS dot, I'll use the bar plot function and say my x-axis to be years, my y-axis will be total duration or total underscore dr that we created here. I'll set my axis equal to ax, and then I'll set error width equal to false. Let's set the title for my plot as title equal to year versus duration, and finally I'll say plt dot xtix. I'll rotate it by, let's say, 90 degrees. Alright, let me just recheck once if everything is fine, and then we'll go ahead and run it. I have my axis, error width, title. Okay, let me just run it. We'll see the result in a moment. If I scroll down, you can see we have the bar plot for the different years and the duration of the songs in seconds in the y-axis. So earlier in the 1920s, you can see the duration of the songs were less, and later it increased around late 1930s, and this remained consistent until 2010, where the duration was high. But after 2010, you can see the duration of the songs have started decreasing. Now in the next cell, I'm going to create a line plot to analyze the average duration of the songs over the years. It is going to be similar to our bar plot, just that now we are going to visualize it in terms of a line. So I have my code ready. You can see here I've used my Seaborn library and the line plot function. In the x-axis I have years, and in the y-axis I have total duration. I've set my title to year versus duration, and I'm rotating my x labels by 60 degrees. Let's run it and we'll see the output. There you go. Now if I scroll down, you can see we have a nice line plot, and on the x-axis you have the years, and on the y-axis we have the duration. You can see that the songs from 1920s to 1960s have comparatively shorter duration, since most of the songs tended to be more singing based rather than instrument based. After 1960s, you can see the duration of the songs started increasing until, I would say, 2010, and in the present day the duration of the songs have started declining, since the attention span of the average listener is also declining. Alright, now let's move to our second data analysis project, which is based on genres of the songs. So I am importing my dataset using the pandas read underscore csv function. I have given my location, and here I have my dataset name followed by the extension of the type. So this is a CSV dataset. Let's go ahead and run it. Okay, now let's print the first 5 rows of the dataset. I have stored my dataset in a data frame called df underscore genre. I'll use the head function to get the first 5 rows of information. I'll hit shift enter to run it. There you go. You can see here I have my genre column, artist name, track ID, popularity, acousticness, duration in milliseconds again, and we have the rest of the other columns that we saw in our first dataset. Just one thing to note, here key is present in terms of C, D, E, C minor, F minor, and not in terms of numbers between 0 to 11. Now we'll see the duration of the songs for different genres. For that, I'm going to create a bar plot. So I'll start with setting the title for my plot as duration of the songs in different genres. I'll use the Seaborn library and I'll set my color palette to, let's say, rocket. I'll give a comma and say as CMap equal to true. This would be color palette. Now I'll say SNS dot bar plot. In the y-axis I'll have genre, and in the x-axis I'll have my duration column, which is in milliseconds, so duration underscore ms, and then I pass my data frame using the data argument. So I'll say data equal to df dot genre. Next we'll set the x labels, so I'll say plt dot x label. Let's say my x label is duration in milliseconds, and then I'll say plt dot y label as genres. Now let's go ahead and run this. There you go. So here you can see we have the different genres on the y-axis, and on the x-axis you have the duration in milliseconds. And if you see the graph for classical genre and for songs that belong to world genre, the duration of the songs are more compared to other genres. Now if you check for children's music genre, the duration is less or the least. Cool. And finally we'll move to our last demo where we'll see the top 5 genres by popularity. So I'll say SNS dot set underscore style. I'll set my style to dark grid, which will be my background, and then I'll say plt dot figure. I'll set my figure size to 10,5. Then I'll create a variable called famous, since I want to take only the most popular songs based on the genre. So I have created a variable called famous, and I'll pass my data frame name, that is df underscore genre, and I'll sort the values based on my popularity column. So I'll say popularity, and I want to sort it in descending order. So I'll say ascending equal to false, and I'll take the first 10 values. I'll tell you the reason why I'm taking the first 10 values and not 5. Then I'll say SNS dot bar plot, and in the y-axis I'll have genre. In the x-axis we'll have popularity, and I'll give a comma, and using the data argument I'll say my data to be famous, which is this variable that we created, and then I'll set my title as top 5 genres by popularity. Alright, now the reason why I took head of 10 is because there are a few genres which are repetitive. So if you see this, we have children's music appearing twice, so hence we have taken 10 instead of 5. Let me just go ahead and run it. There you go. So here if I scroll down, you can see I have my top 5 genres based on the popularity. So we have dance, pop, rap, hip hop and reggaeton. So these are the 5 genres which are most popular based on the data that we have collected from Spotify. The Olympics is one of the biggest sporting events on the planet. It is held every 4 years. The first modern Olympics took place in Athens, Greece in 1896. As per National Geographic, the original Olympics took place in 776 BC. So they began as part of an ancient Greek festival which celebrated Zeus, the Greek god of sky and weather. The rings in the Olympics logo represent the 5 continents: Europe, Africa, Asia, the Americas and Oceania. From 1924 to 1992, the Winter and the Summer Olympics took place in the same year, but now they alternate every 2 years. Before I move on, here is an interesting question for you. Only 2 people have ever won gold medals at both the Summer and the Winter Olympics. Who are those 2 people? Please share your answers in the comment section of the video. We would like to know from you. The Summer Olympics in Tokyo began on the 23rd of July and recently concluded on the 8th of August. We got to witness some thriller matches that went down to the wire, some amazing victories, and sadly there were a lot of heartbreaks as well. Winning and losing are part and parcel of any game. Fans across the world were really happy to see this global event happen this year following last year's postponement due to the coronavirus pandemic. With our Olympic fever high, let's take this opportunity to work around a project to perform exploratory data analysis using Python to analyze and visualize past Olympics data and answer specific questions. In this video, we will be using specific Python libraries such as NumPy, Pandas, Matplotlib and Seaborn to make sense of our data and extract meaningful information. We are going to visualize our results with different charts and graphs. Before I show you the dataset that we are going to use for our analysis, I have another general question for you. Which is the first Olympics where all the participating countries sent female athletes? I repeat, which is the first Olympics where all the participating countries sent female athletes? Put the year and the city name where the Olympics was held in the comment section of the video. We'll be more than happy to hear from you. Now, let me go ahead and show you the datasets that we'll be using in this video. So here you can see I have my Olympics dataset folder that has 2 datasets. These are CSV files. One is called the athlete_events and the other one is called NOC_regions. So we'll be using these 2 datasets. These datasets can be downloaded from Kaggle. We will post the dataset links in the description of the video. Please go ahead and download them. These datasets have been directly taken from the internet. Now I'll show you the datasets. So this is my first dataset. You can see on the top athlete_events. So I have around 15 columns. You can see the count here, and there are nearly 2,71,116 rows of information. So this is a huge dataset that we are going to use. The other dataset we are going to use in this demo is called NOC_regions. Now here one thing to note is NOC stands for National Olympic Committee. This is a 3-letter code that is given by the Olympic Committee. You have the region names, so AFG is for Afghanistan, you have ALB for Albania, ALG for Algeria. We have also a column called notes. You find some notes about the region. For example, here Antigua is actually Antigua and Barbuda. Alright, let's move to the first dataset that I showed you. This is our primary dataset for our demo. So these datasets have been directly taken from the internet and were not validated. So the results that you will see in the demo is purely based on the data that we have collected. So the file athlete_events.csv contains nearly 2,71,116 rows of information, and there are 15 columns. So each row corresponds to an individual athlete competing in an individual Olympic event. So here ID is actually a unique number for each athlete. Then we have the name, which is basically the athlete's name. We have the sex or the gender, which is male or F for female. Then we have the age of the athlete, which is in terms of integers. We have the height in centimeters of the athletes. Then we have the weight in kilograms. We have the team name. These are the country names. You have China, Denmark, Netherlands. There are around 200 country names. Then we have the NOC. As I said, NOC is a 3-letter code that stands for National Olympic Committee. We have the games. This games contains the year and the season. You can see here 1992 summer. You also have the Winter Olympic information. Alright. Then we have a specific year column to tell you in which year this event had occurred. Now the year column is also an integer column. We have the season, so whether it was Summer Olympics or Winter Olympics. Then we have the city name. This is the host city. Then we have the sport name. You can see here we have basketball, judo, football, tug of war, speed skating. There are so many. Then we have another column called event, which is the complete event name. As you can see, the sport name is basketball, but the event name is basketball, men's basketball, to be very specific. Again, for speed skating, you have different categories like women's 1000 meters, 500 meters. Alright. Now the final column is the medal column. So it has the information about the athlete, whether the athlete had won a medal, be it gold, silver, bronze, and NA means the athlete did not win any medals. So we'll use these two datasets. Now let's get started with the demo. We'll be using Jupyter Notebook for our analysis. So I'll take you to my Jupyter Notebook right away. I've opened it on Chrome. So this is my Jupyter Notebook that we are going to use. You can see here Olympics dataset analysis. I have already have a few cells that have been filled with some piece of code, and you can see there are some comments written as well. We are going to use this dataset. So let's get started. First and foremost, we'll import the datasets. So we are going to use NumPy, Pandas, Matplotlib, and Seaborn. Let me hit Shift Enter to import all the libraries. Alright. Now the next thing is to load the datasets using Pandas read_CSV function. So I'll create a variable called athletes. I'll say equal to pd dot. I'll use the read_CSV function, and inside this function we'll give the location of the files. So I'll copy this location and here I'll paste. Make sure this is within quotations, and these are all /. I'll give another /, and after that I'll give the file name, that is athlete_events.csv. I'll close the quotation. Let's run it. Okay. Similarly, we will load the second dataset. I'll create another variable called regions. So it will have my data frame. I'll use the same function pd.read_csv. I'll just copy this file path till here. We'll paste it, and I'll give my second file name, which is noc_regions.csv. You can verify here. The first one is athlete_events, the second one is noc_regions. Okay, I'll close the quotation and we'll run it again. Okay, there seems to be some error. I think this is the regions. Cool. Now moving ahead, let's see the first few rows of both the datasets. I'll use the head function for that. I'll say athletes.head. So this will print the first 5 rows from my dataset athletes. You can see here from 0 to 4 you have 5 rows of information: the ID, name, sex or the gender, age, height, weight. If I go to the right, you have games, year, season, sport, event and medal. Now let's see the second dataset that we imported or loaded. I'll say regions.head. It says regions is not defined. Let me cross check it. Okay, I have taken it as region. Let's make it regions. Cool. Now let's run it. There you go. So these are the first 5 rows from our second dataset. You have NOC, region and some notes. Alright. Now the next step is to combine both the datasets. So we'll join the data frames using the pandas merge function. Let me show you how to do it. So this is going to be a horizontal join. I'll create a variable called athletes_df. Then I'll use my first variable, which is athletes. I'll say .merge, which is my function name. I'm going to merge the regions data frame. I'll use the how parameter. In how, I'll give my value as I want to do a left join, and my common column in both the datasets is actually NOC. So I'm going to use the NOC column as my common column to merge both the datasets. Now let's go ahead and print the merged data frame. I'll say athletes_df.head. Let's run it. There you go. So if you see clearly, if I move to the right, you can see here we have added 2 more columns that were present in the second dataset, which was regions. So we have regions and notes added to my first dataset, that is athletes_events. Cool. Now one thing to note here is, see, the column names are not consistent. If you see here, the rest of the columns start with a capital letter, but if you see the last 2 columns that we just added now start with a lowercase letter. So we'll use the rename function to make the column names consistent. But before that, let's see the shape of the data frame. So I'll print the shape of the data frame to know the total number of rows and columns. I'll say athletes. If I hit tab, you will see it will give me the prompt. I'll select athletes_df. I'll use the shape attribute. Let's run it and see the result. You can see here it gives me the total number of rows. So 2,71,116 rows, and earlier we had 15 columns in the first dataset, and now that we have added 2 more columns, so the total number of columns becomes 17 now. Cool. So now it's time to make the column names consistent. So I'll show you how to do it. I'll say athletes underscore df dot, I'll use the rename function, and then I'll say columns equal to, I'll use curly braces, my first column, that is region, I want to change it to region, but the R should be capital now or uppercase. I'll give a comma and then say my second column, this should be region actually, my second column, that is notes, I want to change the first letter to uppercase, so I'll say capital N, the rest all remains same. I'll give a comma here and say in place equal to true, so it will change the column names and will reflect in this athletes underscore df data frame. Let's run it. Now to verify, you can again use the head function. I'll run this again. Let me scroll down and move to the right. You can see the difference. There you go. So we have successfully renamed the last two columns, region and notes. Alright. Now moving ahead. Now I'll show you how you can use the info method to print information about a data frame, including the index data type, the column data types, non-null values, and memory usage. So for that you just need to use the info function. So I'll write athletes underscore df dot info. Let's run it. There you go. So here we have the data columns. You can see total 17 columns. You have 2,71,116 rows or entries. Then you have the different column names, and it says non-null and the data type of the column. Below you can see some information about the memory usage. Alright. Next, the describe method is used for calculating statistical information such as mean, standard deviation, the percentiles of the numerical values of the data frame, and much more. It analyzes both numeric and object series and also the data frame column sets of mixed data types. So let me show you how using the describe function you can display some statistical summary. I'll just write describe and give parenthesis. Let's run it. Okay, if I scroll down, you can see here by default the describe function will only give information about numerical columns. So here you can see we have the total count, the mean of each of these columns, you have the standard deviation, the minimum and maximum value, and then we have the 25th percentile, the 50th percentile, and the 75th percentile value of the columns ID, age, height, weight, and year. Alright. Now one thing to notice here is, if you see the year column, the minimum year is 1896. So this is when Olympics started, and until recently the Rio Olympics, that was held in 2016. Alright. Now moving ahead. Now let's check if there are any null values present in the columns of the dataset. So first I am going to create a variable called nan values, give equal to, I'll say athletes underscore df, and the function to check is, I'll say is na. I'll create another variable called nan underscore columns, and here I'll use the any function. I'll say nan underscore this variable, which is underscore values dot, I'll say any, and I'll print my nan columns variable. So this will display the result in terms of Boolean values. So if there are any null or nan or missing values in any of the columns, it will say true, otherwise it will say false. Let's display the result. There you go. So if you mark here clearly, so there are nearly 6 columns where we have missing values. You have age, height, weight, medal, region and notes columns that have missing values, so hence it has given us true. The rest of the columns do not have any NaN or missing values, hence they are false. Alright, let me scroll down. Now let's see the total number of null values for the above 6 columns. So I'll say athletes underscore df dot, I'll use the function is null, and again I'll use the sum function. Okay, this should be is null. If I run it, you can see it here. So our age column has 9474 rows where we have null values. Then we have some null values for the height column as well, for the weight column. So these are the total number of rows where we don't have any information regarding age, height, weight or region. Notes, this medal is self-explanatory because a lot of the athletes who participate in Olympics don't win any medals, so for them the value is NA. Now before I move ahead, I have a question for you people. So the question is, I want you to print the column names containing null values or missing values in the form of a list. So please answer this question and put it in the comment section of the video. We would be happy to know your approach. So the question, I'll repeat it again. I want you people to print the column names containing null values or missing values in the form of a list. So basically on the top we saw there were 6 columns that had null values. I want you to print these 6 columns in the form of a list. Alright, now moving ahead. Now let's see the data for specific countries. Let's say you want to see the athletes who have participated in the Olympic Games from the beginning for India. For that, you can filter your result using a function called query. So let me show you how to do it. I'll say athletes underscore df dot, we'll use the query function, and then I'll say team, which is my column name, should be equal to, and the value I'll give is India. Now let's display the first 5 rows of information or the details for the athletes who are from India. If I run this, okay, there is some error here. Okay, so we need to make sure this entire expression or the condition should be within single quote. I'll just delete this single quote from here and we'll add it in the end. Now let's run it. There you go. So here you can see we have the top 5 rows of the athletes who are from India. You can see here the region is India, you can see the NOC is India, the team is India, and let me go to the left. You can see the name of the athlete, the sex, age. So for age you have some missing values, you have the weight, team, year and everything. Alright, similarly you can also check for Japan. Let me just copy the above code, I'll paste it here, and instead of India I'll say Japan. I'll run it. There you go. So if you see here, you can see all the details are for the athletes who are from Japan. Alright, now moving ahead. Now I want to know the top 10 countries who have participated since the inception of Olympics in 1896. So for that I'll create a variable called top underscore 10 underscore countries. I'll say equal to, I'll use my data frame, that is athletes underscore df. I'll say dot team Then I'll use the function value underscore counts. I'm going to sort my count in ascending order. Just mark the way in which I'm writing the functions. Any error in terms of syntax or the flow will throw you an error. I want to display the top 10 countries. Now let's go ahead and print it. I'll say top underscore 10 underscore countries. Alright, let me run it. Okay, it has given us an error. Let's debug it. Okay, so this should be value counts and not count. Let's run it again. Another error. Okay, so this should be short underscore values and not value. Let's run it again. There you go. So here you can see the top 10 countries participating in Olympics since 1896. You have United States, then we have France. So these are the number of participants who have taken part since 1896. So the most number of participants have come from US, then we have France, Great Britain, Italy, Germany, Canada, Japan, Sweden. We also have Australia and Hungary. I'll scroll down. Now we are going to convert this table that we got, or the output that we got, in the form of a graph. So I'm trying to create a bar plot to plot the top 10 countries who have participated in Olympics. So here I'm using the figure function to give the figure size. So these are the dimensions 12,6. Now I'll tell you what this pltxtix means. Just wait for a while. I have given a title to my plot saying overall participation by country, and then using the Seaborn library and the bar plot function, I am plotting the x and the y axis. So my x axis has top. I should make this top 10 countries because above we used top underscore 10 underscore countries. Similarly for y axis I'll make it top underscore 10 underscore countries, and then I'm using a color palette called set2. Let's run it. There you go. So if I scroll down, you can see here we have a nice bar plot. This is a vertical bar plot, and here you can see the bars which represent the different country names. First we have United States, which has the highest participation since the beginning of the Olympics. Then we have France, Great Britain, Italy, Germany, Canada, and we have the rest of the countries. Cool. Now moving ahead, the next visualization we are going to see is the age distribution of the athletes. So for this we are going to create a histogram. I'll be using the matplotlib library specifically for this visualization. So I'll say plt.figure will give the figure size using the argument fig size equal to, and this will be a tuple actually. My size is going to be 12,6. I'll say plt dot title. Now you can give any title that you want. I'll say age distribution of the athletes. Then we'll also give the x labels. I'll say plt dot x label. This will have age. Then we'll say plt dot y label, and this will have the label as number of participants. Next I'm going to use the hist function, so I'll say plt.hist, and I'll pass in my data frame, that is athletes underscore df dot age, which is my column name, comma, I'm going to pass in the bins. For that I'm going to use the np.arange function. So np is for numpy, and inside this I'll say 10, 80, 2. So my bins will start from the value 10 and go until 80 with a size of 2, comma, I'll give another parameter that is going to specify the color of the bins. I want my color to be orange, and then I'll use the edge color to separate the bins. I'll say edge color, this is the parameter or the argument name, and the color I want is white. Let's give a semicolon here, and this should be edge color. There's a spelling mistake here. Now let's run it and we'll see the output. So there you go. So this is a nice histogram that shows the distribution of the age of the athletes. You can see the title age distribution of the athletes. On the y-axis you have the number of participants. On the x-axis we have the age values ranging from 10 to 80 with a size of 2. And if you see this, we have most number of athletes who have an age between 20 to 30. You can see here. So early 20s we have maximum number of athletes participating in the Olympics. We also have a few athletes who are beyond 40 years of age. You can see here we have a few athletes even closer to 60 also, and similarly we have a few athletes who are under 18 years of age. Alright, now you can see here the bins we had taken orange color, so all the bars are represented in orange color, and the edge you can see here we have the white color. Alright, now moving ahead. Now in the initial slides of the video we discussed the Summer and Winter Olympic Games. Let's look at the different sporting events that are part of the Summer and Winter Olympic Games. Just to give you a heads up, the Winter Olympic Games are held once every 4 years for sports practiced on snow and ice. So here I have my variable name winter_sports, so I'm extracting for season equal to winter, and I am going to display only the unique values. Now let me run this cell. Okay, so you can see here these are the different winter sports that are held during the Winter Olympics. Now similarly, let's see for Summer Olympics. So what I'm going to do here is I'll just copy this cell of code and we'll edit the variables. I'll say summer_sports, athletes_df remains the same. Here season we'll change it to summer.sport.unique remains the same, and here I'll say summer_sports. That should be small. Now let's run it. There you go. So here you can see we have more number of Olympic sports that are held during the Summer Olympics compared to Winter Olympics. So these are the sports that are played on snow and ice, and these are the sports that are played during summer. Moving ahead, now it's time to analyze the total number of male and female participants who have taken part in different games since 1896 till 2016 Rio Olympics. Alright, so I'll say gender_counts, which is my variable name. I'll use my data frame, that is athletes_df dot my variable name, that is sex, dot value_counts, and then we are going to print gender_counts. Let's run this. There you go. So since the inception of Olympics, we have more number of male participants than female participants. Now here in this current cell you can see we are trying to plot a pie chart for male and female athletes. So I have given my figure size, then I have my title as gender distribution. I'm using the matplotlib library and the pie function. I'm using the variable gender counts that we used here. Then I'm giving my labels as gender_counts.index. Now I'm using this auto PCT. The auto PCT parameter enables you to display the percent value using Python string formatting. So this is my string formatting that I have used, and I'm initialized my start angle for the pie chart as 150 degrees, and I'm also giving shadow to my pie chart. So I have written shadow equal to true. Let's run it. Alright, so you can see here this is my pie chart that shows you the distribution of the male and female participation. So for male it is 72.5%, for female so far it is 27.5% as per the dataset that we have. Now we can change this start angle to, let's say, 180 degree, and it will change the pie chart to this direction. Cool. Now moving ahead, this time we are going to find the total number of medals that the athletes have won. So I'll use my data frame athletes_df dot, and then my column, that is medal, I'll say dot value underscore counts. Let's run it. There you go. So you can see the gold medals, the bronze medals and the silver medals are very much similar to each other. The numbers are pretty much the same. Alright, now it's time to focus on the total female athletes who have taken part in each Olympics. So I'll create a variable called female_participants. I'll say equal to, and then use my data frame name, that is athletes_df. Using square brackets, I'll say athletes_df dot, the gender should be equal to female, and I'll use ampersand. I'll say, just copy this, paste it here. I'll say dot season equal to, we'll check for Summer Olympics, and I want to extract only the gender column. So here it is sex, comma, my year column, which is year. Okay, and then I'll say female underscore participants equal to, I'll just copy this, paste it here, and then I'll use the group by function. Say group by, which is part of the pandas library. I'll say year, and then I want to find the count. I'll reset the index, say reset underscore index is a function, and finally we are going to print female underscore participants and let's say the head. Alright, so what we are trying to do is I'm trying to filter my data only for the female athletes for Summer Olympics, and here I am printing the participation based on each year, so I'm finding out the count. So here we need to add one more square bracket. Alright, now we'll run it and see the result. There you go. So you can see here from 1900, 1904, all these years you can see the female participation. Let me change it to tail so that we have the recent data of the Olympics. You can see it here. For the Beijing Olympics, 5,816 women athletes participated. In 2012 London Olympics, we had 5,815 Olympics. Similarly, for the 2016 Rio Olympics, we had more participation than the London Olympics. So 6,223 women athletes had participated. Alright. Now here, this is another way in which you can filter your data for female athletes. So I'm using two parameters. My gender should be equal to female and season is Summer Olympics. Let me just run it. I have stored it in a variable called Women Olympics. Now here I am trying to find a count plot, or I am trying to create a count plot using my Seaborn SNS library. I have set my style to dark grid. Then my figure size I have given as 20,10. My count plot will have the x-axis as year. The data is Women Olympics, and palette I'm using as spectral, and then I've given a title Women Participation. Let's run and see the output. There you go. If I scroll down, you can see on the top I have the title for my count plot, which says Women Participation, and on the y-axis I have the count, and at the bottom you can see the different year values from 1900 till 2016, and 2016 had the highest number of female participation. Cool. Let me scroll down. So in this cell of code we are trying to plot a line graph. Let me run it and show you the output. So this line graph shows the trend, which says plot for female athletes over time. So here you can see the line graph. So gradually the women participation has increased in Olympics since its inception. There was a slight decrease here. This is around 1950s, and again you can see here there's a decrease with the women participation in 1980, but since then, since 1980, there has been continuous increase in the participation of female athlete numbers. Cool. Now coming to the next section of our analysis. Now we are going to filter the data to see the details of the athletes who have won gold medals. So I'll create a variable called gold medals. It's equal to, I'll use my data frame as athletes underscore df, and within parenthesis I'll use my data frame name, which is athletes underscore df dot, I'll use the condition medal equal to, and my value would be gold. Next I'm going to say gold medals dot head. Let's run it. There you go. So here we have the top 5 rows of the athletes who have won a gold medal. You can see all the records have medal as gold. Now we are going to use this subset of the data and perform some more analysis. So here I want to take only the values that are different from NaN. So I'm going to use is finite function, and inside that I have set gold medals age. Let me just run it. Cool. Now I want to see the athletes who have secured a gold medal beyond the age of 60 years, which is very rare. So we'll see the total number of athletes with more than 60 years of age having won a gold medal. So here I'm going to say gold medals. I'll use my column as ID, and then I'll use my variable gold medals, and then I'll say age should be greater than 60, and then I'll close my square bracket and say count. Okay, let me just verify if everything's fine. Yeah, I'll run it and we'll see the result. So there are total 6 athletes who have won a gold medal having age more than 60 years. Cool. Now let me check for which sport these 6 gold medals have come. So I'll say sporting underscore event. This is going to be my variable name, equal to, I'll use the same variable name, gold medals. I'll going to choose my sport column and then I'll give my condition age greater than 60. Now let's go ahead and we'll print the variable sporting event. If I run this, you can see it here. So for art competitions, even for archery and shooting, and this one called rook, we have had gold medals from athletes who had an age more than 60 years. Now we are going to plot this result or the table that we achieved on the top. So I'll say plt dot figure. I'll give my figure size equal to, let's say 10,5. Then I'll say plt dot, we'll use the tight layout, say tight underscore layout. Then I'm going to use the Seaborn library and create a count plot for my variable sporting underscore event. Then I'll say plt dot title. I'll give the title as gold medals for athletes over 60 years of age. Let's run it, and if I scroll down, you can see here we have a nice count plot. I have my title gold medals for athletes over 60 years, and since for archery we had 3 players who secured a gold medal having an age more than 60 years. You can see here archery is 3, art competition 1, rook is 1, and shooting we had 1 medal. Alright, now we'll see the total gold medals from each country. So for that I'll say gold medals dot, we'll use the region column, and followed by that I'll use the value underscore counts function, and I'll reset the index with name equal to, I'll provide the medal column. Then we are going to print the head for the top 5 countries. Let me run it. You can see it here. So USA has secured the most number of gold medals. Then we have Russia, Germany, UK, and then we have Italy. Cool. Now in this cell I am going to create a plot to visualize the table that I got above. So I've used my labels, my titles. I'm using the cat plot function that is present in the Seaborn library. I have my x-axis, my y-axis, the data which is total gold medals. Let me just verify. Okay, and we'll run it. If I scroll down, you can see this is a different palette that I had used, which is a rocket, and you can see USA has got the most number of gold medals. Then we have Russia, Germany, UK, Italy and France. Now we also have included France here, which was not present in this table. The reason being I have used head as 6. So it will give me the top 6 countries. Alright. Now we will analyze and look at the data for the most recent Olympic event that is present in our dataset. I'm talking about the 2016 Rio Summer Olympics. So first of all, I'll create a variable called max year, which will be equal to my data frame name athletes underscore df, my column name year, and I'll use the max function. Then let's go ahead and print my max year. I'll just show you the output. You can see here my max year present in the dataset is 2016, the Rio Olympics. Next, we will create another variable called team underscore names that will be equal to my data frame name athletes underscore df. Within square brackets, I'll give parenthesis and then say athletes underscore df dot year should be equal to my output, that is max year, which is actually 2016, and then I'll say ampersand. I'll just copy this, we'll paste it here. This time I'll use the medal column and say equal to gold. I'll say dot team, then I'll say team underscore names dot value underscore counts dot head, and will display the top 10 countries. Let me run this. There you go. So in Rio Olympics, United States secured the most number of gold medals. Now the reason this is 137 is we have also counted the team events, for example basketball. Similarly, Great Britain had 64 gold medals in total, Russia 50, we have Brazil 34, Argentina 21, France 20, and Japan 17. Alright. Now using the above result, we are going to create a bar plot. I'll just change this team underscore list to team underscore names. Similarly here also I'll make the corrections as team underscore names. Cool. Now we'll run it, and you can see here we have a nice horizontal bar plot. So we have United States at the top, Great Britain, Russia, Germany, China, Brazil. So here I am displaying the top 20 nations since I have used head as 20. So these are the top 20 nations who secured the most number of gold medals in the Rio Olympics. Alright. Now in the final section of this video, we will create a scatter plot to visualize the height and weight of male and female athletes who have won a medal. Now it can be a gold medal, a silver medal, or a bronze medal. But before that, we need to filter the data only for athletes who have won a medal. Now if you had noticed here, our medals column also had a few null values, so we are not going to consider those null values here. We are only going to consider for the athletes who have won a medal. So for that, I'll create a variable called not underscore null underscore medals equal to, I'll say athletes underscore df, then I'll give my, let's make it df, I'll give my condition, Let me just copy this. I'll paste it here, and then I'll give my condition height and use the not null function, and then I'll say ampersand, create another parenthesis. I'll say athletes underscore df. This time we'll consider the weight column. Again, I'll use the function as not null, and I'll close the parenthesis. Okay, I had missed one s here. Cool. Let me just run it now. Alright. Now we are going to create our final plot. I'll say plt.figure. I'll give my figure size equal to, I'll say 12,10. I'll say axis equal to SNS dot. We'll be creating a scatter plot to plot the height and weight of the athletes who have won a medal. I'll say scatter plot. In my x-axis I'll have height, comma. In my y-axis I'll have weight, comma. My data should be not underscore null underscore medals. So this is what we created here, not underscore null underscore medals, comma. I'll use hue equal to my sex column. Cool. Finally, I'll say plt dot, I'll give a title to my plot saying height versus weight of Olympic medalists. Cool. Now let's see our scatter plot. This might take some time to give the result because there are so many athletes present in a dataset who have won a medal, and also we are filtering in terms of hue, which is for male and female. There you go. So if I scroll down, you can see here we have a nice scatter plot. On the top we have the title of the plot saying height versus weight of Olympic medalists. You can see our age as the hue. So blue points are for the male athletes and orange points are for the female athletes. And on the y-axis we have the weight in terms of kilograms, and you have the height in terms of centimeters. Cool. So that brings us to the end of this demo session on Olympics dataset analysis. So we used two datasets to carry out this exploratory data analysis, and we created some visualizations to analyze and visualize the data. So in this video, we'll be using two datasets to perform our analysis. Now let me show you the CSV files. So this is my IPL dataset folder which is on my desktop, and these are the two files that we are going to use. The first dataset has information about matches played between 2008 and 2020. Let me open this dataset. Alright, you can see here there are total, let me just go to the top and I'll show you the number of rows we have. We have around 817 rows of information. Alright, you can see this is the match ID. So these are all unique IDs of the matches held between 2008 and 2020. Then we have the city in which the match was held. We have the date on which the match was played. We have the player of the match, which is man of the match basically. Then we have the venue column that is the name of the stadium where the match was conducted. We have a column called neutral venue, whether the venue is neutral or not. Then we have the teams, team 1 and team 2. We have information about who won the toss. Then after winning the toss, whether they decided to field first or bat first. Then we have the winner who won the match. We have the results, whether it was won by runs or by wickets. Then we have the margin. So these big numbers are basically runs, 140, 33, all these are runs. If you see here, one of the match was a very close contest where the winning team won by just 6 runs. We have information about whether the match was an eliminator or a league match. We have a method, whether there was any DL method applied for deciding the result. And we have information about the 2 umpires. These are basically field umpires. Next, coming to the second data set. Now in the second data set, let me open it. Alright, so this dataset has all the information for each ball bowled since 2008 till 2020. You see you have the match ID, then we have the information about innings, whether it was a first inning or a second innings. We have which over it was, then we have which ball it was, basically the number of ball in an over. Then we have the batsman who faced the delivery. Then we have the batsman who was at the non-striker end, or the player who was at the non-striker end. Then we have information about who the bowler was and how many runs were scored of that ball, whether there were any extra runs, and the total runs that were scored in each ball. We have whether it was a boundary or a non-boundary. Then we have whether there was a wicket taken in that delivery. Now we have information about player dismissed. Let me apply a filter and show you the values that we have. You can see here these are the players who have been dismissed. Now similarly, let's see for extra types. You have byes, leg byes, no balls, penalty, wide deliveries. Then we have the batting team and the bowling team. Alright. So we will be using these 2 data sets to perform exploratory data analysis and answer particular questions like the total number of matches played in each season, the total number of runs scored in each season. We'll also look at the number of tosses won by each team, the toss decision for each season. Then we'll see whether the team opted to bat or to field first after winning the toss. We'll also understand how a certain player has performed so far in IPL, the player who has scored the most number of runs, and who has won the most number of Man of the Match awards. Alright, so let me take you to my Jupyter notebook. So this is the Jupyter notebook we'll be using for our demo. I have already written a few lines of code. You can see it here. Alright, so let's begin with the first step, which is to import the necessary libraries. So to perform our data analysis on the IPL dataset, I would need the NumPy library for numerical computation. We'll also need pandas library, so I've imported it as PD and NumPy as NP. Then we have 2 visualization libraries, matplotlib and seaborn. The next step is to load the dataset. So here I am loading 2 of my datasets, which is match_data and the balls dataset. So to load the dataset, I'm using pandas library and the read_csv function, and within this parenthesis I'll pass in my file location followed by the file name and the extension of the file. So here I have my dataset. Now let me copy this location and I'll paste the location here. We'll convert all the backslash to /, and finally I'll give my dataset file name. Let me just copy it and I'll paste it there. Okay, followed by the file name extension, which is .csv. Now I will just copy this, and similarly I'll paste for my second dataset. We'll replace the file name. I'll copy this file name and I'll paste it here. Okay, now let me go ahead and first run the first cell to import all the necessary libraries. You can see we have successfully imported all the libraries. Then let's run the second cell, which is to load the datasets. So the first dataset, which is IPL matches, I'm storing in a variable called match_data. This will be stored in the form of a data frame. And the second dataset, which is IPL ball by ball, I'm storing in a variable called ball_data. Let's run it. Okay, there is some error. Alright, we need to put these within double quotes. Don't forget to put the location on within double quotes, otherwise it will throw an error. Now let's run it again. There you go. So I have successfully imported my datasets. Now let's print the top 5 rows from both the data frames. Now to print the top 5 rows, I'll use the head function. First I'll write match_data, which is my variable name for the first data frame, followed by the head function. If I run this, you can see I have the top 5 rows from my matches dataset. You see here we have the ID, the city, date, player of the match. If I scroll to the right, you can see winner, result, result margin, eliminator, method, and the 2 umpires. Similarly, let's see the top 5 rows from the ball dataset. So I'll write ball_data, which is my variable name, followed by the head function. Let's run it using Shift Enter. There you go. So we have the top 5 rows from the ball by ball dataset as well. Next, let's check if there are any null values in both the datasets. Now to check for null values, you can use the isNull function, and to find the total number of null values, you can use the sum function. So I'll write match_data dot. I'll use the isNull function to see if there are any null values, and to find the sum, I'll use the sum function. There you go. If I scroll down, you see here there are 13 null values or missing values in the city column. Then you have 4 null values in the player of the match column. Method, you have 797 null values. Similarly, you have some null values for eliminator and result margin as well. Let me just copy this. Now we'll check for null values present in our ball dataset. I'll replace this by ball. Let's run it. There you go. If I scroll down, here you can see for dismissal_kind, then you have player_dismissed, fielder, extra types. These all have a lot of null values. Okay. Now you can print the shape of the data frame and also all the columns present in it. For that, I'll use the shape method. I'll write match_data.shape. You see here in our match dataset we have 816 rows of information and 17 columns. Similarly, if you want, you can check for the ball dataset. There you go. So the first value represents the number of rows, and then we have the number of columns. Now if you want to print all the columns present in a dataset, you can use the columns attribute. You can see it here in the result. We have all the columns printed that are present in the match dataset. Now let's look at the total number of matches played so far, the cities where the matches have been played, and the team which have participated. So for this I will be using 3 print statement. So I'll write print match played so far. I'll give a colon, and then with a comma I'll write my variable name, which is match_data, and I'll give shape as 0. Let's print this. You can see matches played so far is 816. I'll write another print statement. This is to check the cities in which the matches have been played, and I'll only print the unique cities. So I'll give a \n. I'll write cities played at. Let's give a colon now. and I'll use my variable which is match underscore data, and within square brackets I'll give my column name, that is city, so that it will extract only the city values, and I'll give my function as unique since I want to know only the unique cities in which the matches have been played. If I run this, there you go. So these are the cities in which the matches have been played from 2008 till 2020. You have Bangalore, Chandigarh, Delhi, you have Durban, Port Elizabeth, you have Centurion, there's Ahmedabad, Cuttack, Nagpur, Kochi, Kanpur, Bangalore, Dubai, and other cities as well. Okay, now we'll print one more result, that is the total number of teams that have participated so far. So I'll write print, within single quotes I'll give \n so that there's a space. I'll write teams participated, give a colon, and then I'll give a comma. I'll pass in my variable name which is match underscore data. Then within square brackets I'll give team1, and again I'll use the unique function. If I run this, in the result you can see these are the teams that have participated so far. You have RCB, the Kings 11 Punjab, Delhi Daredevils. Last year there was Delhi Capitals. You have the Rising Pune Super Giants, Chennai Super Kings, Kochi Tuskers, Deccan Chargers, and other teams as well. Alright, now we will add a new column to our table that will have the year value extracted from the date column of the matches data frame. Now if I go to the top, I'll show you what I want to do. So in this matches data frame you have a column called date which has all the date values in which the matches were played. From this date value I want to extract only the year. So let me show you how to do it. Now to extract the year value from the date column, I'll use a function which is datetime_index. Now let me show you how to use it. I'll write my variable name which is match underscore data, and I'll create a new column called season. Now this season column will have only the year values. I'll give pd dot, and I'll use my function datetime_index, and within this function I'll pass in my variable which is match underscore data, and within square brackets I'll give my date column. I'll come out and I'll give my attribute which is year. Now in the next line let me print the head of the data frame. Now I'll write match underscore data dot head. If I run this, scroll down a bit and I'll go to the right, you see the last column we have added a new column called season which has only the year values. Now we will use this column which is the season column to perform multiple operations. Okay. Now let's look at the total number of matches that have been played or held each season from 2008 to 2020. So I'll give my variable name which is match per season equal to, I'll write match underscore data dot, here I'm going to use group by function which is present inside my pandas data frame. So I'm going to group all the season values. So basically I'm going to group all the year values so that I can know how many matches have been played each season. Now I'm going to count all the match IDs for each season. So I'll pass in my ID column dot, and I'll use my count function. Then I'll reset my index using the reset underscore index function, and then I'll rename my column. So I'll write rename, within brackets I'll give columns equal to I'll pass in a dictionary. So I want to convert the ID column to matches. Alright, let me just see it again if everything is fine, and I'm going to print my new variable that I have created, which is matches per season. Let's run this. Some error has occurred. Let me check. It says match per season not defined. There's a small typo here. I have missed a S. So I'll run this again. There you go. You can see in the result we have all the seasons starting from 2008 till 2020, and here we have all the matches that were played in each season. So you can see here in season 2013 there were the highest number of matches that were played, which was 76. Then in 2012 there were 74 matches. Similarly in 2011 we have 73, and if you see this result, in 2008 less number of matches were played overall, which was 58. Oh no, it's actually 2009 where 57 matches were played. Okay. Now we will visualize the above result by creating a bar graph that will show the number of matches held each year. So I am going to make use of this table, and using this table we'll create a bar graph. Now to create a bar graph, I'll use my Seaborn library which I had imported as SNS. I'll write sns.countPlot, which is to count the number of matches. So I'll pass in my data frame, which is match underscore data, and I'll give my variable as season, or the column name as season. Next, we'll use our matplotlib library. I'll write plt.xticks, which is an attribute to edit our x labels. I'll give the parameters rotation equal to 45, and I'll give my font size as, let's say, 10. Similarly, I'll use plt.yticks, and I'll give my font size as 10. Now I'll edit my x labels. I'll write plt.xLabel. In the x label we'll have the season values. I'll give my font size as 10. Then let me just copy this. We'll have our plt.ylabel, and our y axis would have the count. Font size, let it be 10. Then we'll give the title to our bar graph. So I'll write plt.title, and within single quotes I'll give a title to my plot, which is total matches played in each season. We'll also give a font size of, let's say, 10 again, and I'll use font weight as bold. Alright, let me now run this and show you how our graph looks like. There you go. So we have a nice bar graph. On the top you can see the title of the graph, which says total matches played in each season. On the y-axis we have the label as count. On the x-axis we have the label as season. And now let me show you what I meant by x-ticks and y-ticks. So I had rotated my x values by 45. So you can see the year values have been tilted and printed with 45 degrees. And then I had set my font size to be 10. So this is font size 10, and similarly count also we have font size 10. Now let's say if I want to rotate this by 90 and I print it, you see here the year values are now rotated in 90 degrees. Now what happens if I just remove this parameter and we'll only have font size. If I print it, you see this has been printed in horizontal order like we have it in the count column. I'll just paste it here again. Okay, now let's run it. So I have my year values. Okay, we'll move ahead and perform some more analysis. So in my current cell, which you see here, I'm merging two columns from the matches data frame to balls data frame using a left join. So here I'm adding the ID column and the season column present in my match underscore data frame with the ball data frame, and I'm using a left join, and I'm joining using the common column which is ID, which is present in both the tables or both the data frames, and then I'm dropping my ID column. Let's go ahead and run this. Okay, you see here I've added my season column to my ball underscore data frame. Now we'll use this data frame now to perform some analysis. Now in the current cell which I have selected, let's visualize the total runs scored in each season. So what I have done is I have grouped my season values and applied a sum function to the total runs column, and then I have reset my index, and I'm plotting a line graph. You see here I've used sns.lineplot, which means I'm plotting a line graph to see the trend of runs scored each season. I have set my face color as black. We have a title called total runs in each season. I've given a font size, a font weight. Now before I run this cell, let me change my face color from black to gray so that my plot is clearly visible. Again, this palette you can choose whatever you want. Let me show you how you can select the Seaborn palette. If I search for SNS palette, there's a nice blog or an article from Seaborn, and here you can see we have all the palettes here. Whichever you want you can choose. There is hustle, we have set to, paired. There are so many. You can use whatever you like. Now let me go back. Let's run this cell. There you go. So here we have a nice line graph. Now if you see this line graph, in year 2009, least number of scores or minimum number of runs were scored compared to other seasons. We had the highest number of runs scored in 2013, which responds to this. So more than 22,000 runs were scored in 2013. Similarly, we had a drop in 2014, which was around 19,000 or less than 19,000 runs were scored in 2014. And if you see for 2020, which was last season, more than 19,000 runs or nearly 19,500 runs were scored in 2020. Okay, now moving ahead, let's see our next operation that we want to perform. I'll scroll down. Now I want to find the runs scored per match in each season. To do this, I'm concatenating the match per season data frame with the second column's season data frame. So I am dividing the total runs scored each season. You can see it here. So I have divided the total runs by the matches played per season. Now I have set my index to season and I am printing runs per season. The result I am storing it in a variable which is runs scored per match. Let's just run this. There you go. If I scroll down, you see we have the seasons, the different seasons from 2008 till 2020, and you have the total matches that were played in each season. You have the total number of runs that were scored in each season, and then we have our last column which is runs scored per match. So here you have the total number of runs or the average runs scored in each match. Okay. Now we'll look at the number of tosses won by each team. For this, I'm finding the count of toss winners and then I'm creating a horizontal bar graph. So I'm using the value underscore counts function and I'm counting the toss winners for each of the teams. And here I have used my face color as gray, and then you can see I have set my title to number of tosses won each season. My X label is number of tosses won. On the Y label I have the teams. Let's just run this. Okay, if you see here on the Y-axis I have the different teams, and on the X-axis I have the number of tosses won by each team. You see Mumbai Indians so far have won the highest number of tosses, followed by Kolkata Knight Riders, then we have Chennai Super Kings, then we have Royal Challengers Bangalore, and if you see at the bottom we have Kochi Tuskers and Rising Pune Super Giants. Alright, the next cell of code will help us analyze the toss decision across different seasons. So if you want to find out whether the teams decided to bat or bowl first, I'm using a count plot or a frequency plot. Let me just run this and show you the results. So this is how the distribution looks like of the toss decisions across seasons. The purple color represents field and the red or the orange color represents batting, which means after winning the toss the team decided to bat first, and the purple color represents after winning the toss the team decided to bowl first. Now let me explain you what this graph tells us. In most of the seasons, the team that won the toss decided to field first. Only in certain cases, for example in 2009, the toss winning team decided to bat first. Similarly, if you see for season 2013, most of the teams preferred to bat first. And do we have anything else? No. If you see the other season, even in 2010, if you see, most of the teams preferred to bat first after winning the toss, but the rest of the seasons, be it 2008 or be it 2011, be it 2016, 17, 18, 19 and even 2020, most of the teams preferred to field first after winning the toss. Okay. Now we will look at the match results to analyze how many matches have been won in terms of wickets, meaning that the chasing team won the match. We will see how many matches have been won by runs, meaning that the team batting second could not chase the target. We will understand how many matches have been a tie so far. Now to get that result, I'll just write one line of code. I'll give my data frame name, which is match underscore data, and I'll use my result column, and then I am going to use my value underscore counts function. If I run this, okay, there is some error here. This should be value underscore counts and not count. There you go. If you see, most number of matches have been won by wickets, which means the team batting second won the highest number of matches, and there are less number of matches that have been won by runs, which means the team bowling second won the match, and then we had 13 ties so far from 2008 to 2020. Alright, now let's address some more questions. For example, if you want to know which stadium is best for winning by wickets, so I'll write match underscore data dot, I'll use the venue column which is present in my match underscore data frame, and then I'm going to use my condition as result not equal to runs, and then I'll use the mod function. If I run this, you see here Eden Gardens is the best stadium for winning by wickets. So you have higher chances if you bat second at Eden Gardens, you'll win the match. Now see, you want to know which stadium is best for winning by runs. To do that, I'll just copy my above line of code, and instead of not equal to runs, I'll write not equal to wickets. If I run this, it says Firozshah Kotla. So Firozshah Kotla is the best stadium for winning the match by runs. So you have higher chances if you choose to bat first. Alright, now we want to know for any given IPL team which stadium is best when they win the toss. So to answer that question, I'll use my data frame, which is match underscore data. Again, I'm going to use my column, that is venue, and then I'll write match underscore data dot toss underscore winner. Let's say I'll write equal to my team I'll select is, let's say, Kings 11 Punjab, and then I'm going to use another square brackets and give match underscore data dot winner equal to I'll write again Kings 11 Punjab. Let me copy this, I'll paste it here, and then I'm going to use the mod function. If I run this, you see here the result is Punjab Cricket Association Stadium, Mohali, which is the home ground for Kings 11 Punjab. So for any given IPL team, if you want to know which stadium is best when they win the toss, most of the times you will find it is going to be their home stadium or the home ground. Now let's verify this with another team. Let's say I want to know in which stadium Mumbai Indians have won the maximum number of matches. So I'll choose my team as Mumbai Indians this time, and let's see which stadium it returns. If I run this, there you go. It says Wankhede Stadium, which is again the home ground for Mumbai Indians. Let's see for one more. Now I want for Kolkata Knight Riders. I'll copy this and I'll paste it here as well. If I run this, again it says Eden Gardens, which is the home ground for Kolkata Knight Riders. Okay. The next question I want to answer is, which is the best chasing team, that is the team that has won the maximum number of matches batting second. So for that, I'll write match underscore data dot, I'll use my winner column, and within square brackets I'll write match underscore data dot result not equal to runs, and then I want to use the mod function. If I run this, the result says Kolkata Knight Riders and Mumbai Indians are the best chasing team, which means they have won the maximum number of matches batting second. Now if you want to know the best defending team, that is the team that has won the maximum number of matches batting first, I'll just copy this line of code. Let me scroll down, I'll paste it here, and instead of result not equal to runs, this time I'm going to use result not equal to wickets. If I run this, it returns me the result Mumbai Indians, which means Mumbai Indians is the best defending team, that is the team that has won the maximum number of matches batting first. Now this one typical question that I want to answer now is, does winning the toss mean winning the match? To answer that, I'll create a variable called toss equal to, I'll write match underscore data, I use my column, that is toss winner, then I'm going to compare it with equal to match underscore data, and then I'll see the winner. So here I'm choosing who won the toss and whether the same team was the winner. I'll create a plot here. I'll write plt.figure. I'm going to give a figure size. I'll write fig size, which is my attribute present inside the matplotlib function, and I'll give my figure size as 10,5. I'll use my count plot function present in the Seaborn library, and I am going to count the toss, and I'll display it using plt.show. Let's run this. Okay, we have a nice bar graph which says winning the toss doesn't necessarily mean winning the match. You can see we have a lot of false values here, which means after winning the toss the team did not win the match, but there are a lot of true values as well. Now I want to answer one more question, which is, does choosing batting or bowling first help in winning matches? So for that I'll create another bar plot. I'll write plt figure. I'll give my figure size equal to, let's say, 12,4. Then I'll write sns dot count plot. I'll write match underscore data dot toss underscore decision, which is my column. Then I'll write match underscore data dot toss underscore winner equal to match underscore data dot winner. Then I'll just plot it or display it using plt.show. Let's run this. If I scroll down, you can visualize the result. We can say that choosing to field first for the toss winner helped in winning the match than batting first in IPL from 2008 to 2020. So there are higher chances if you choose to field first, you will win the match. Okay. Now we will use our ball by ball dataset to see how a player has performed throughout IPL. Now for all these visualizations that we have created and we have seen so far, we were using the match dataset, which had information about the matches played from 2008 to 2020. From now on, we are going to use our ball by ball dataset. So the first thing I want to do is we'll analyze a performance of a player throughout IPL. So I am going to take one of the popular players in IPL, that is Suresh Raina. So I'm going to create a variable called player equal to, I'll use my data frame name, that is ball underscore data, and then within square brackets I'll write batsman equal to I'll give SK Raina, because that is the name present in our dataset for Suresh Raina. Then I'll write data frame underscore Raina equal to ball underscore data. Within square brackets I'll write player. Then let me print the head of the data frame. I'll write df underscore Rana dot head. There is an issue here. Let me debug the issue. Instead of dot, this should be an underscore. Let's run it. Now the key here should be capital and not small. Let's run it again. There you go. If you see here, we have created a data frame only for the player name, that is Suresh Raina. You can see here SK Raina. Cool. Now moving ahead. Now in the current cell of code tells us how Suresh Raina has been dismissed throughout the IPL in all the seasons. So here I'm using the value counts for dismissal kind, and I'm going to use a pie chart. So let me run this. If you see here, okay, we have the dismissal kind and there is a nice pie chart. Now this pie chart tells us that Suresh Raina has been caught for 68.8% of the times, and then he has been bowled for 10% time. He has got run out 7.5% of the times, been caught and bowled for 5%, he has been stumped for 5%, and he has been given leg before wicket for 3.8% of the times. Alright, now moving ahead. In the next cell of code, we are trying to find the runs scored by Suresh Raina in 1s, 2s, 3s and in boundaries, that is 4s and 6s. So for that I am creating a user-defined function called count, which will count the runs scored by Raina. I'll just run this so that you get an idea. Alright, if you see the results, Raina has scored the maximum number of runs by a boundary which is 4. Then he has scored the second highest number of runs by taking singles. Then he has scored the third highest number of runs by hitting sixes, and has scored the least number of runs by running a triple. Okay. Now if you want to know the details of the match that had the biggest win in terms of run margin, let me show you. If you want to analyze the match that had the biggest win in terms of margin, so you can use match underscore data, and then within square brackets I'll write my variable name again, match underscore data. Again I'll give a square bracket, I'll say result underscore margin. I'll give a condition equal to match underscore data. Then I'll say result underscore margin. I'll use my function, that is maximum. If I run this, okay, so we have the details of that match. So this match was played in 2017 in the city Delhi. So I'm assuming this match was played at Firozshah Kotla, which is the home ground for Delhi Daredevils, which is currently known as Delhi Capitals. The player of the match was Simmons, who is from West Indies. You see here we have the venue, which is Firozshah Kotla. It was played between Delhi Daredevils and Mumbai Indians. The toss was won by Delhi Daredevils, but they lost the match, and the match was won by Mumbai Indians by runs, and the result margin was 146 runs, which is a huge number when it comes to T20 cricket. And you can see the season as 2017. Okay. Now let's find the players who have scored the maximum number of runs so far in IPL. To do that, I'll create a variable called runs equal to, I'll use my ball underscore data, and I'm going to use my group by function. So here I'm going to group the batsmen. So within single quotes I'll use my column, which is batsman, and then I'm going to use the sum function over the column, that is batsman runs. I'll write batsman underscore runs, and I'll give a dot and use my sum function, and I'll reset the index. Okay. Now in the next line I'll write runs dot columns. I'm going to create two new variables, which is batsman, and the second column would be runs. Next, I'm going to give a variable called y, which is runs dot, I'm going to sort it. I'll write sort underscore values in terms of runs. So I'll write by my new column, that is runs, comma, I'll give ascending equal to false, which means it will order my result in descending order. I'm going to find the top 10 batsmen in IPL who have scored the maximum number of runs. I'll write reset dot index, and then I'm going to drop my index, and I'll give axis equal to 1, which means I'm going to drop it in terms of columns. Let's print y. So what I'm doing here is, first I'm grouping all the batsmen, and then I'm going to find the total runs that they have scored. So I'm using the sum function. Then I'm creating two new variables or columns called batsmen and runs. I'm sorting the runs scored by the top 10 batsmen in terms of runs. Let's run this. Okay, let me check what is the error. It says column not found, batsman underscore run. This should be batsman underscore runs. Let's run it again. There you go. So we have Virat Kohli, there's Suresh Raina, David Warner, Rohit Sharma, Shikhar Dhawan, then we have Grayscale, De Villiers, Dhoni, Uthappa and Gambhir, who are the top 10 batsmen in IPL that have scored the highest number of runs. Okay. Now we will visualize the top 10 players who have scored the highest number of runs. So this is the code I have written already. Now you can use whichever palette you want. I have used face color as gray. Let's just run this and visualize the result. There you go. You have a nice bar plot, and on the top it says top 10 runs scorers in IPL. On the y-axis you have the total number of runs they have scored. On the x-axis you have the player names. So the first player who has scored the maximum number of runs is Virat Kohli. If you see, the runs he has scored is close to 6,000 runs. Next we have is Suresh Raina. The second graph or the second bar is for Suresh Raina, followed by Warner, Sharma. We have MS Dhoni, Uthappa, Gambhir and other players. Cool. Now coming to our final visualization, where we'll see the players who have won the Man of the Match award maximum number of times. For that I'm using my column, that is player of the match column. Let's run it. If I scroll down, you see here AB de Villiers from South Africa, who currently plays for RCB, has won the highest number of Man of the Match awards, which is actually more than 25, I believe. Next we have Grayscale, Rohit Sharma, David Warner. You have Yusuf Pathan, Suresh Raina, Virat Kohli and Gautam Gambhir, who have won the highest number of Man of the Match awards. Okay, so let me go to the top and just give you a brief on what we did in this IPL data analysis demo. So first we imported our two datasets, match underscore data and our ball by ball dataset. Then we checked using the isNull function to see whether there are any null values present in any columns of the datasets. We used the shape function to display the shape of the dataset. We printed the total number of columns that are present in one of the datasets. We saw how you could extract the season or the year value from a date column. Then we printed the total number of matches played in each season. Then we converted that same result into a nice bar graph. Then we merged two columns from one of the datasets to another dataset, which was ball data. Then we saw the total number of runs in each season. We also saw the runs scored per match in different seasons. Now we visualized the number of tosses won by each season. We saw the toss decision across all the seasons, where we found out that most of the teams preferred to field first. Then if I scroll further, you saw how to answer different kinds of questions. Then we also learned how you can analyze a particular player and their performance throughout IPL. We saw for Suresh Raina and the dismissal kind. We also checked the pattern in which he has scored the runs. Finally, we found out the top 10 run scorers in IPL and saw who has won the highest number of Man of the Match awards. So if you want to get the source code files and the datasets we have used in this demo, then please put your email IDs in the comment section. We will share the files over email.
And with that, we have come to an end of this full course tutorial. I hope it was informative and interesting. If you have any question about the topics covered in this video, feel free to put them in the comments section. Our team will help you solve your queries. Thank you for watching, keep coding, and stay tuned to SimpliCode.